A warm welcome to one and all gathered here on this day to witness the inaugural ceremony of KIAN 2K19 on nanomechanics of biological systems. Global Initiative of Academic Networks is an initiative by Human Resources Development to give Indian students knowledge about international research. For any event to turn to a success, it is essential that the blessings of the Almighty is sought. So let's begin this event with a prayer song by Ms. Madhumita from final year B.Tech Biotechnology. Thank you for the devotional song, Madhumita. For any event to turn to a success, it is essential that the blessings of the Almighty is sought. So let's begin this event. Next to God, it is to welcome the ignited minds present here and to welcome them. I now call upon Dr. Ananta Subramanian, Professor and Head, Department of Biotechnology, PhD College of Technology.
Good morning. Should I say warm welcome? It's going to be cold and it's inside the room actually. Right. So let me officially welcome you all for this program, Global Initiative of Academic Networks. So let me welcome special address speaker, Professor Prakash, Principal in Charge, PhD College of Technology. This is the first interaction with him in this kind of a setup after he assuming the charge. Of course, he is not new to our department. In the initial days of setting the department, he was very much instrumental in helping us in taking classes and shaping our program as well. So welcome you, Professor Prakash. Speaker of this occasion is Professor Delphine Lee, Professor of Engineering, Bioengineering, Clemson University. She almost traveled 2 days to meet you all. So it's a pleasure having you here, madam. And first of all, I have to thank you for accepting and being here for a week to deliver the talk. More about her will be addressed by Professor Rani. So I welcome all of my colleagues, students, and faculty and students from the department. So this GIAN, this Global Initiative of Academic Network, this is a brainchild of the Ministry of HRD quite some time back towards initiating interactions between faculty and students of academics in India and with outside of the world. And this is the one which we actually have to apply and get approval from the government through Indian Institute of Technology, Kharagpur. And we have been successful in this because this is the third one in the series. The first one was in 2017 where we had invited Professor John Price from Victoria University. He was addressing on cancer metastasis. And last year, 2018, we had Professor Schmidt from University of Applied Science Hall, Germany. He was talking about water treatment, industrial wastewater treatment with bioreactor, high flow rate bioreactors. And this is the third one in this. So we have been successful in getting this from government. And the third one now today is on nanomechanics of biological systems. So we have been working on these areas, whatever I was saying about. We have been working with cancers, we've been working with industrial wastewater, and so is something related to nanomechanics, particularly on mechanobiology. So that actually helped us to get into this field. And nanomechanics is something which I remember a decade back, this was rated as the top 10 best technology. And this is particularly when Subra Sureshwaran, he was in that time MIT, now he is in present MIT in NTU. He was addressing more into it. So we all know that we, as a system, when we look at a human system, then you get into an organ system, then you get into tissues, and then you get into cells, and then you get into macromolecular. Understanding this mechanics or the dynamics is quite tricky unless you have a technology that you can't do it. So that speaks about the kind of technology that we have, we are able to get into. Like you talk about AFM or optical tweezers or nano indentations or force microscopy. So we are lucky to have Professor Delphine here to talk about all those things, and I'm sure you all will be benefited by this. And besides Professor Delphine, we have two of our speakers. Dr. Viveka, she talks about mechanobiology, particularly in a gut system. Right? And Professor Rani, she's going to talk about cell mechanics of the AD or Alzheimer's disease. So this short note, let me welcome you all again, and I hope you all have a fruitful interaction with her and get as much as input from. Thank you.
I would now request Dr. Prakasan, Principal PhD College of Technology, to honor the chief guest with a bouquet. I next like to call upon the reason behind all this, our mentor, guide and our leader, Dr. K. Prakasan, Principal PhD College of Technology, to deliver the special address of the day.
Professor Anandasubramanian, Dr. Delphine Dean, Dr. Rani, Dr. Viveka, the participants of this program and dear students. Very good morning at the outset, and I think it is cold. So I extend a very warm welcome to all of you, along with Professor Anandasubramanian, HOD of Biotech. As indicated, I used to teach a few courses in the beginning, but slowly because of the workload, I moved out and did something else. But those days were enjoyable, and some of the students who returned from abroad, they used to meet once in a while and share their experiences in their current position and in the academics what they have here. So I think all of you will do well. And with this, only 2 minutes I will use for this occasion. The objective of GYAN, many of you would have read the global initiative on academic networks, but in our Sanskrit, the word GYAN means knowledge. The word Gi Shanta, they said it is Jnanam, that is knowledge. So if you read the website of this particular portal, the details given you can easily go through and its relevance. I think about 1,839 courses are approved so far, and 1,451 courses have been completed with the participation of 188 institutes. That is the data as on date. So it shows the growth of this particular thought, and one main intention behind this is to increase the footfalls of the foreign professors who are experts in some domain in India, and the cascading effects of that, like research students doing courses which are latest in the website or in the international research arena. So that is objective. I think PhD is also doing it. Last, I think there were a few courses organized by PSG alone, and even there are host institute in many other activities. The research is also growing in the Department of Biotech. It is very heartening to know that we have some of the eminent professors in this area, Dr. Delphine Dean, Greg Granite Pillai, Associate Professor of Bioengineering, Clemson University, Our students are also doing some courses in Clemson, but not in this department, they are in mechanical. I have a few students in Clemson doing their MS. The research in biotech, I think, or the biology, that is going to be the ultimate. It is a never-ending mine of knowledge, so intricate, maybe starting from DNA or much beyond atoms or molecules or elements. I was reading the website of California Institute of Technology recently for some purpose. You know, it's a very small university, but it's a technology. It's not like university, you can say. They have only 300 faculty members in their institute, but out of that 39 are Nobel laureates. Student strength is also not very high. So somebody interviewed the president of the university and asked how you are number one in the world, in the Times Higher Education or any ranking you see, they will be number one. He said that we are very small, that is the reason. When you are small, you develop special properties. Like in macro world, you can see much bigger systems in nano world, or still, I don't know what is the next level of what you call reduction in size. We say cosmos in one side, now we say nano. It can be still small. So as it becomes smaller, I think you see bigger things since you don't see the macro world. So there are a lot of things published in their website. One was interesting. It is the skeleton for cell. You may be knowing it, I am new to that. So I was surprised. You will not be surprised. Cell got a skeleton. It is true. And they have shown a photograph. It is some, not animation, it is some experimental data. A cell deforming and moving, an immune cell to kill some disease spreading virus or something. So how it is moving through this, then I asked my son, he is doing medicine, is it true? He gave so many words, cytotubes and so many things, micro, a lot of words he used. He said it is true, but I asked, have you seen it? He said no, it is in book, but you need some sophisticated equipment to see this. I think you can try in all our nano facility got a very good visualization and measurement places, you can try that. So I think the future research is going to be on all this, as Professor told in IAC Bangalore, Professor Ananda Suresh, he came here once and he talked about the stress and strain in the cells. So when it gets infected, how the strains are developed, that can be calibrated or measured in some disease, I think. So these are all very fundamental and very nice that the department is doing fundamental study. In our campus, the scientific inquiry will be only with the bio group. I always used to tell, it is not engineering, it is science. When Galileo started his physics proposals, Earth is rotating, one question was, if it is rotating, I drop something, how it falls exactly at the foot of this particular pillar? Can anybody answer it? If Earth is rotating, we put something, then why that object is not falling away from this? It should go away when it is rotating. So the proposition is very fundamental, which we never create this type of questions in the class. I used to tell students to put this type of intriguing questions to the teacher, then they will also be alert. It can be repeated any number of times. If I learn, it is only my learning. Somebody has to put the same question again and experience it himself, then only he will learn that. So the answer is, this horizontal velocity, it has already having because of rotation on Earth. It is not affected by the gravitation. Only the vertical velocity gets changed. This will be always same. So with the minimum deviation, it will be always moving and it will fall exactly at the foot of that particular object. This has to be answered using the concepts of velocity, acceleration, force, etc. As you make it more and more elegant, people will enjoy the subject. So I am very sure you will have a very good time in learning very basic queries on human systems, cells, which will be always fundamental. One thing I didn't see that is lunch break was written big, but I didn't see test. For every session there should be a test also. That is very important. Hope it will be there. Assessment is very important in the not end of that every session or somewhere. You can I mean, it's only my suggestion. I should not say that. It's only a suggestion. Any process should be having a good assessment. Then you will learn it, and the top scorer will be motivated with some a small gift. This is a suggestion to the head of the department and the organizers. With these few words, I wish you all the best and good learning. Thank you.
As per the famous saying, Atithi Devo Bhava, I now call upon Dr. P. Rani, Professor, Department of Biotechnology, who is also the program coordinator and the organizer of this course, to introduce our beloved speaker.
Good morning, one and all present here. It's my honor and pleasure to introduce Dr. Delphine Dean, a key resource person for our program on nanomechanics of biological system. As William Arthur Ward says, the mediocre teacher tells, the good teacher explains, the superior teachers demonstrate, and the great teacher inspires. Here we have Delphine Dean, who has inspired many such young minds, not only in US, also in underdeveloped countries like Tanzania. She used to visit very often in most of the underdeveloped countries and interacted with lot of such young minds. Dr. Delphine is a great grandmother, associate professor of bioengineering at Clemson University. She earned her PhD in electrical engineering and computer science from the Massachusetts Institute of Technology in 2005 and started her faculty position at Clemson in January 2007. Her research interests focus on nano to microscale characterization of biological tissues, force microscopy, and mathematical modeling. Dr. Delphine's scientific accomplishments are many, with the most well-known being the technological solution for Tanzanian clinical settings. Her team has been recognized with several awards, including 2014 Lemon Shaw MIT Undergraduate Cure IT Prize. Other awards include the Award of Distinction from Clemson National Scholars Program in 2013, Murray Stuckley Award for Excellence in Teaching from Clemson College of Engineering and Science in 2012, Outstanding Academic Faculty Award from the President Commission on the Status of Women from Clemson University in 2012, Phil and Mary Bradley Award for Mentoring in Creative Inquiry in 2011. She has made important contribution in many areas of bioengineering with more than 50 refereed international publications. Today we are here to Dr. Delphine's outstanding talent as a teacher, mentor, and also as a researcher. Those students lucky enough to take classes from her have always been amazed by her ability to make even most complex concepts a simple one. She currently mentors 12 undergraduate creative inquiry research and design teams. These multi-year undergraduate project teams have focused mainly on several areas, including the redesign of medical training simulators, investigating the use of robotics for solving biomedical problems, and developing medical technology for resource-poor countries. She is a member of American Chemical Society, American Physical Society, Material Research Society, Biomedical Engineering Society, Society for Biomaterials, American Society for Engineering Education, and Orthopedics Research Society. She also has a patent on devices that cooperate with ultrasound for musculoskeletal evaluation and related systems and methods. She also has several utility patent applications. Without further delay, I am happy to welcome Dr. Delphine and all the other participants for this program. I hope all of us have a very interesting interaction with Dr. Delphine for next few days, and I hope all of us get benefited. Thank you all.
Now I would like to invite the one who has worked from nanometer to microvolt. Our speaker, Dr. Delphine Dean, Greg Brandwell, Associate Professor, Department of Bioengineering, Clemson University, USA, to take over the stage.
Hi. So thank you so much for the invitation. I'm tall, I'm sorry. So thank you so much for the invitation, everyone, and particularly Dr. Rani, thank you so much. I'm very excited to be here and I guess share my passion a bit about nanomechanics. I do a lot of research in a lot of areas, and before coming here I actually looked, and so I do a lot of atomic force microscopy, and I've been doing AFM for over 20 years now. And as I was preparing this course, I realized how much has changed and how much the technologies that we kind of take for granted today, when I started, were these big hairy things, but now I think it's very accessible to everyone. So I'm very much looking forward to this course. I hope it can be interactive, so please ask questions and I will have questions for you. And hopefully we'll all learn together, and I look forward to it. Thank you.
We work for cause and not for applause. With this thought and motive to work, I call upon Dr. Viveka Ji, Assistant Professor, Department of Biotechnology, to conclude the inaugural ceremony with vote of thanks.
Good morning, one and all. There's a famous saying in Tamil literature which goes, Thiraikadal Odiyum Diraviyam Thedu, which means you can travel across the globe, across the seas to fetch knowledge. But thanks to such initiatives like YAM, you don't have to travel across the sea. So it's there for you here today and for this week. So I thank first the Ministry of Human Resource Development, the Government of India for coming up with this initiative. And I thank our beloved principal and the management of PSC College of Technology for all the support and encouragement, and for making possible this course and providing the opportunity for the students to gather knowledge from such experts from around the world. And I thank our beloved HOD and the faculty, teaching and non-teaching staff of Department of Biotechnology. I thank the local GYAN coordinators, Dr. Manoharan and Dr. Kannamal, for helping us with conducting this course. And I thank Dr. Rani for making this course possible. And I thank all the students and the participants from various institutions for being here, for being with us for this week. I hope this you find this course very useful. And this is a very emerging course, and I hope we have a very good interaction with Dr. Delphin Dean. And as Principal said, let's have a cascading effect, and let's take this forward with many more interactions. Thank you.
We'll now break for 15 minutes and then start with the course.
Good morning, congratulations here. We are going to start the session with the introduction to nanomechanics. Each day we have 2 sessions in the morning and 2 sessions in the afternoon. After each session, please note that we will be giving the lecture material. We have given a lecture material only for today's program. We will be giving it the then and there whenever the material is available. And after each session, there will be a question and answer session, just to know how things are going on, or we are all in a line or not. And at the end of the 5th day, we have an examination session, which will be mainly conducted to grade you for the program. So we'll start the session, today's session with a lecture by Dr.
Hi. Yes, I'll start here. So thank you all for being here. I hope this is going to be interactive. So, okay. So if you have questions, please raise your hand and ask. Yes. Okay. So I wanted to do a short intro, kind of overview of nanomechanics, why it matters, so kind of frame the course. And then today, after that, I was going to talk a little bit about some imaging techniques and how they work with nanomechanics. So we'll talk about electron microscopy, and atomic first microscopy in the context of imaging. Tomorrow we'll do some techniques for actually measuring directly nanomechanical forces. So this is me. That's me. I just got my credits, not the full credits. And there's my email address. So if you're shy and you don't want to ask a question in class or come talk to me, you should come talk to me. But if you're shy, please also you can send me an email. As was mentioned, I do a lot of different research topics at Clemson. So if you don't know, Clemson is a public university in South Carolina. That the red state there, that's South Carolina, and the little arrow, that's where Clemson is. Please come visit. Also, we have a really good bioengineering program, so if you're an undergrad, want to go to grad school, please apply. If you're a grad student, you're looking for postdocs, let me know. If you're a postdoc and looking for faculty positions, we'll be hiring next year. So please come talk to me. So just to background a little bit on how I got to where I am in the field of nanomechanics. As was mentioned, my degrees are in electrical engineering and computer science. That's what I did my undergrad in. And then in graduate school, that's what my degree is in, but I was working in a biomedical engineering kind of lab with people from lots of different disciplines. And we were looking at cartilage, the whole lab was focused on cartilage mechanics. So cartilage, when you're walking, it makes your bones not hurt. And trying to understand where the properties came from. And my advisor came and was asking me if I would be interested in trying this new project on a new instrument that he just got, which was an AFM, to try to directly measure the molecular components of the tissue. As an electrical engineer, I was initially like, isn't that a lot of chemistry? But you learn. But in terms of, it crosses over a lot because a lot of the computational modeling approaches and things were things I had gotten used to looking at semiconductors and things like that. And so that's how my journey into nanomechanics began. At Clemson, there's lots of professors like here that do lots of different research and topics, and actually I ended up coming to Clemson and started collaborating with folks on all sorts of different things, and so my areas of research have kind of expanded. So we do a lot of more basic science research on nanomechanics, particularly with the cardiovascular system, so looking at vascular cells and cardiac cells, how the forces are generated, how to measure them, how they respond to different stimuli. We also look at ionizing radiation, so X-rays and things, and how they interact with different cells and molecules and how that affects mechanics. And then as was mentioned, I have another side of the lab that's very, very applied and actually does design of sensors and devices for medical diagnosis, disease management, and some environmental applications for low resource settings, both in the state of South Carolina as well as abroad. Primarily go to Tanzania because that's where my collaborators are. And so it seems like maybe these two areas of research don't really overlap a lot. But it was the nanomechanics side that got me into this very applied area. When I started at Clemson, I was very much, I'm going to do some AFM, I'm going to do some modeling. And over time, I've done some applied research that came out of that work. We started looking at different molecular interactions with a collaborator that was looking at specific molecule and bacteria interactions, and that turned into trying to design a sensor so we could detect that bacteria in different environments, and that kind of kicked off a lot of things. So in my lab, and kind of in this course, we'll talk about mechanics over lots of different scales. So if you think about tissues in your body, right, you classically think about tissue mechanics. You look at the tissue as a material, very much in the classic engineering sense. I can take a bone and bend it and find out what kind of material properties they have. I can take a tendon, stretch it. I can you know, like I can poke on people and find out how much fat content they've got. So that's very much a bulk measurement. If you go down in scale from macroscopic down to microscopic, now you're looking at things on the cell scale. And a lot of tissue interactions happen at that, and we're interested in that area because I think later today or tomorrow there's a talk on mechanotransduction. Because tissues aren't static materials, right? They're not like the material from your desk. They are constantly being remodeled, constantly being built and broken down by the cells, and the cells react to mechanical forces to then determine how to build up the material, and it's a feedback loop. So if they're sitting in a very stiff environment, the cell might get stiffer and respond, or it might get softer and respond differently. And then where do all these forces come from? Well, they come from the constitutive parts that make up tissues. So they come from molecular interactions, right? This is the molecules that make up your tissue. It's not actually continuum. It's lots of discrete proteins and filaments and things. Also, if you're really interested in materials and implantable materials and things like that, it's important to keep in mind molecular mechanics and interactions, because that's what causes a material to be bioactive, bioinert, or something that may have reactions in the body, right? It's what proteins and things stick to the material that make the cells have their different reactions. So that's a little bit about me and what I want. But before I go on, I wanted to find out who all of you are. So as a first class, I wanted to do like maybe a show of hands. So are there undergraduates in class? Raise your hand. Grads. Okay. Grad students? No. Yes. Hey, don't be shy. And then I think there's some faculty. There's faculty. Look, faculty. Oh, look, yes. I have faculty all taking up the front row. What fields are people in? So I know there's biotechnology. Yes. Okay. Is there other engineering kind of disciplines? What field are you all? Somebody? Am I gonna have to call on people? What fields? Biomedical? Okay. Very apropos. Yes? Mechanical? Okay, good. Are there biology? It's just biology or molecular biology? Okay. Okay, that gives me a good background of kind of how to pitch. Did I not cover something? Was somebody in a field that I didn't cover? Physics, yes. That's very easy for the molecular stuff. It's all physics. So hopefully I'm going to try to tune the course to make it work for you all, but please give me feedback if you have things that don't make sense, or you're bored because it's going too slow. Let me know. So a little bit about nano and nanotech. So I'm sure you've all thought about length scales a lot, right? Because freshman year or first year of college, you start working on things, you think about length scales, centimeter, you keep going down. Just to have an idea, I think it's nice and useful to have kind of a picture of what is a nanometer. So if you look at, on the slide, a glucose molecule, sugar, is about a nanometer, a little bit under a nanometer. The carbon nanotubes, right, are about nanometer in diameter. Large proteins are in the nanometer scale. If you go to like tens to hundreds of nanometers, you're talking about viruses and things like that. Large molecular assemblies. And then if you get to like 1 micron, 1 micron is about the size of E. coli, bacteria. If you go up to like 10 to 20 microns, we're talking more like mammalian cells, our cells. And then, of course, hair is about 100 microns in diameter. I think a good analogy to get an idea of what length scale we're talking about. If you're talking about an atom, right? An atom is about an angstrom. If an atom was the size of an apple, then an apple would be the size of the Earth, right? That gives you a sense of scaling. I use this because I think in school we learn about length scales pretty good, but it's hard to conceptualize force. So just to help, so here again is some things we've done with atomic force microscopy on different length scales. So the little bumps on that first picture are atoms of mica. The big thing there that's hundreds of nanometers long, that is the molecule I did my graduate work on. It's from cartilage. It's a large molecular cartilage. And then the last picture over there, that is a human hair, actually from one of my advisors in grad school. She has really thick hair though, so I feel like it's not that representative. My hair is a lot thinner. So I think hers is like 100 microns, I think mine's like 50. But what's a force? So the thing I like to think about is a Newton of force, right? Is if I take a big apple, I put it on my hand, the apple is being pushed on with gravity by 1 Newton. It's easy to think about because, you know, Newton thought about gravity with an apple falling on his head. It's all 1 Newton of force. A nanonewton, of course, is much smaller. So how much force is a nanonewton? So in the world of nanomechanics and molecular interactions, it's actually quite a bit of force. Nanonewton is about the amount of force you would have to give to break a chemical bond between two carbon atoms. So if you want to yank hard enough to break a covalent bond between two carbon atoms, that takes about a nanonewton of force. So why are we studying nano things? As was mentioned in the introduction, there's been kind of this proliferation of nano and nanomechanics. Where did they all come from? So there's a lot of key things. I started doing AFM things in 1998, I think. Yeah, something like that. So I'm at that bottom of that list. But things precursor to that, people have been thinking about nanoscale things for quite some time, right? So, Rutherford discovered atomic nuclei in early 1900s. Richard Feynman at Caltech gave a famous speech in 1959, which I highly encourage you all to read. It was titled "There's Plenty of Room at the Bottom," and it was kind of postulating that the next wave in technology would be really focused on that very small scale, and that it would enable a lot of the technological advances that we want to see. And so sometimes people refer to Dr. Feynman as the father of nanotechnology. Lots of people have been working on nanotechnology before and after him. It's just that he kind of coined a lot of the terminology that we use. 1969, the surface versus apparatus was invented, and you're going to talk about that technique a little bit. But it's one of the first techniques that actually let you directly measure nanomechanical forces. And then in 1981, the scanning tunneling microscope, which is AFM is a variation of that, was invented by Rohr and Binning at IBM Zurich, and they won a Nobel Prize for it in 1986. So if you keep going down, by the early 90s, there were commercially available tools for measuring nanomechanical interactions, and that spurred a lot of experiments that were very basic science focused, but led to a lot of discoveries that then led to technologies that we all know. And that had kind of made an exponential growth in just the science coming out in terms of nanomechanics. So if you look at now, there are whole journals on this area. If you type nanomechanics into your favorite, either Google Scholar, PubMed, whatever you used to look up journal articles, there's thousands and thousands of journal papers that are out. And in part, that's because in the early 2000s, many governments and agencies in the US and abroad started putting money and grant funding specifically for nanotechnology and nanosciences to really push the innovation. And so that really led to huge proliferation in results. And just to put a plug into why you should look into this area, in terms of commercialization, global nanotechnology is expected to reach something like $125 billion by 2024. So it's a good time to go into this field. As I mentioned, Richard Feynman, Nobel Prize laureate, did a really cool talk that kind of is an inspiring way of looking at nanoscale things. In 1959, he was 41 years old at the time. I'm 41 years old. I did not have a Nobel Prize, but you know, I still have lots to do, so maybe. But really, he had some key points that really I think are interesting, and why I put a link to some of his videos of why you want to look at this field. He talked about that there is a need to scale down devices to look at things like specifically like biology, where up to this point it had been very focused on larger scale things that you can see using a microscope, but that a lot of things were happening at a scale below that, and that we need to focus on that area. He also postulated that sometime in the future we would have nano manipulators, or I think he called them an army of hands that can move things around. And as you'll see, we do have that now, so we have lots of technologies to be able to move things at the nano scale. And that upcoming was things would be built using physical synthesis means as opposed to chemical synthesis. So chemical synthesis is, you know, what we traditionally think about in the lab, right? You put some chemical A, you put chemical B, you stir it and you put it at some temperature, and then it does stuff, and then you pour it and you cook it some more, you know, and then you get a material. Physical synthesis and what he was talking about is some of the things we do now in terms of, you know, semiconductors and lithography and things like that. You have a material, and now you're going to blade away the pattern you want. You're going to build something. Some of the reasons that it took so long to get to where we are was some of the technical challenges to actually do those things. And the advent of computers and things like that really spurred a lot of this innovation. So people up to that point, lots of people had theoretical framers, lots of physicists, lots of models, but there weren't tools to actually measure those things. And so really that's what happened. So yeah, I have the link to Time Machines. Highly recommend watching the movie. And if you're bored, not bored, if you have time, you should read Dr. Feynman's autobiography, which is Surely You're Joking, Mr. Feynman. It's a collection of his stories from when he was a child all the way to Caltech. It was an interesting photo. So the kinds of things he was postulating, right, is that you can either manufacture things, you can build stuff, either from the bottom up or top down. So if you think about biology and tissues and how we get built up, it's very much a bottom-up kind of process typically, right? Your cells are there, they're going to put down some, let's say, collagen. On top of collagen, there's another protein that attaches, and the whole thing gets built up. And you have these amazing structures that they're self-assembled, and they have very intricate structure at the macro scale, right, the bone and its shape. And then if you go down the micro scale, it has trabeculae, but so inside the bone, right, there's a trabecular network that helps distribute stress around your bone so that it doesn't break. There are channels for blood vessels. And if you zoom in even closer, you'll see right? You'll see there's I was afraid of like actually making it go. So, oh, look at that. along the direction of where the compression would come, right? Comes from the top. And then these are arranged in cylindrical fashion around osteons. But if you look even closer, the individual plates, it's not a continuous mineralized matrix. It's actually a series of plates held together by kind of molecular glue. And that in turn helps distribute the load so that if you do get a small fracture, not, like, oh my gosh, I fell off the podium and my shin broke. But, I whacked my knee on this table. I might have nano and micro scale fractures, but because of the structure, that fracture doesn't propagate along the whole material, right? It gets dissipated, and there's time for it to get repaired. Biology is very good at making these beautiful self-assembled structures that are highly complex. People, we're making our own stuff. If you're trying to engineer something like this, right? Nope. Aha. If you're trying to engineer something like this, it's pretty complicated. However, we're getting pretty good at making a little bit simpler, but we're starting to get there. And so how that happened wasn't just trial and error. It was a lot of actual characterization of these materials and how they're made and how we can engineer something that simulates that environment. So that's how biology does it. A lot of time for engineering, we do it the other way. We do talking, right? We have a material. I'm going to etch away at a thing and make a structure, and then I'll glue a different thing that I etched away. And that's how you can do all sorts of cool things. This I liked because it's a tiny guitar. It's about 10 micrometers. And this was done using electron beam, I think, etching. But it actually, like, if you plug the string, it would produce 10 megahertz sound, which we can't hear. But this is the kind of cool engineering thing that we're very good at. And nowadays, we're trying to make materials and things for different applications that actually vary both approaches, right? You probably can't make cool things a lot with self-assembly, and it would take too long to make everything by top-down approaches where you're going to lay away things. So trying to do both to kind of get a material that does what you want is kind of the approach to space. So nanomechanics, we're going to talk about this course. There's a couple things to keep in mind. When you're at the nano scale, so if you have all the mechanical engineers, right, you have your traditional materials mechanical test. I squish it, I stretch it, I break it, and I get numbers out, right? I get modulus, I get stiffness, I get yield strength, all these kinds of things. These are very much measures of material in a continuum sense. I'm giving a number that represents how soft or stiff, how squishy, how viscous a material is on average. And that works great when you're talking about the macroscopic scale, because at that light scale, everything gets averaged out. However, when you start looking at forces and interactions at smaller and smaller scale, there comes a point where it's really hard to think about materials as continuum. So if you're thinking about a cell, this is like very much textbook cell, which like very few cells actually look like. Have you always noticed this? They like the textbook cells like this big, blob with all these organelles. Like if you've ever worked with cells, very few cells actually look like this. Different cells have completely different structures. But the point is they have discrete things in them that are on the micro and nano scale. And so it's kind of hard to think about materials when you're making these measurements as continuums, right? Depending on if I'm like actually, let's say I'm doing an indentation probing test, like this kind of example, right? I have a material, I squish down. Here's my material, and I get an average property. If I do this with a cell, I take the thing and I squish it down. I can average the properties I get, but if I make a small enough probe, if I poke at different areas, I'm going to feel different things, right? It's a heterogeneous, non-isotropic material. And obviously, if you're actually pulling on individual molecules, that's very much getting into the realm of quantum physics and things matter. Now, I put this out there because you have to think about these things. I thought about those things a lot in graduate school. I was making computational models of that crazy molecule from cartilage that I had a picture of. And in the end, what I found now is most people have this statement in their papers that's like, okay, nanoscale things are not continuums. We should think about them as not a continuum. But as a first approximation, we're going to approximate it as a nice uniform blob. And that works pretty good. And so in this class, we'll talk a bit about those approximations and why they're useful and when they work and when they don't work. But it's important to keep in mind that, especially now, because the techniques have gotten kind of commonplace, so you'll see a lot of papers, particularly with, like, say, cell mechanics, where the point of the paper is, let's say, looking at a cancer cell and how it goes from a tumor into metastasis and how the cell changes as it becomes metastatic. There's a lot of structure that happens that change. They have lots of beautiful images. They have a gene expression profile. And in there, they might add an AFM measurement to measure the stiffness of the cell as it goes through that transition. And what you'll find is a cell that's in a tumor tends to be a lot stiffer than a metastatic cell, right? Why? Well, the metastatic cell has to, like, squish and get through places to go travel all over the place. And so it's a paper very focused on the biology, and it might have, like, we did AFM, and we found that the elastic modulus of the cancer cell from the tumor is, I don't know, 5 kilopascals, and the metastatic cell is 50 pascals, and that's what they'll report. And that is true. It's a nice way to kind of conceptualize that, but of course there's a lot more happening. So if the focus of what you're interested in is really the nanomechanics, you'll want more of those details. If it's really just an extra step to kind of really show that there's a change in mechanics, but you don't want to get into the nitty-gritty, first order linear approximations work well. So we'll talk a bit about those things. Also in this class, we'll cover a couple different kinds of techniques and both experimental and quantitative modeling. So the first, and I think what a lot of people might think about when you're talking about nanomechanics, is molecular interactions. And a lot of those are kind of non-contact force interactions. So how molecules interact, how we measure them, you don't actually physically touch stuff. So we'll talk a bit about those kinds of things, but for instance, a lot of times with, as I mentioned, implant materials and biofouling, if you're designing one of those, you would like to know which proteins will attach to that material first. You want to measure intermolecular forces between the molecule, your protein of interest, and your surface. Those are longer range interaction forces that happen before the protein actually sticks. Once the protein sticks, that's it, right? I've got protein gunk on my nice material surface. So if I'm trying to avoid having the protein sticks, I want to understand the forces above the surface. How do I change that to make maybe the protein not stick or only stick certain types of proteins? So those are non-contact type forces. We'll talk a bit about electrostatics, which are charge interactions, as well as van der Waals forces. Van der Waals are attractive forces. When you're close enough, everything sticks together. So we can try to prevent things from sticking, but if I push hard enough, it will stick. It always does. And then there's contact things. So contact interaction type forces are more like traditional mechanical tests, right? You can do, you can actually push, pull, grab, move things around on a small scale now directly. So you can directly probe and interact with the surface. The easiest one to think about is nano-indentation. So this is actually a nano indent into bone. So these kind of, but you can actually like measure individual cells, all sorts of tissues, and directly probe them. So I have this slide mostly as kind of an overview to help. I'm not going to cover all of these things in this class, but it's a nice way to, like, if you have a problem and you're trying to understand, I would like to measure protein unfolding and that kind of thing, which tools might work the best for different things. So it's important to remember that not every technique works for everything. It's important for me to remember that because, as I mentioned, I do a lot of atomic force microscopy. I think the analogy is when you have a hammer, everything looks like a nail. So if you talk to me, I'm always like, well, we can stick it in the AFM and do stuff, but that's not necessarily always the best technique, right? In particular, depending on what you want to do, you can directly measure forces using some of these tools, and we'll talk about kind of the limitations and why they're hard or easy. But you might actually just want to use an imaging technique, and that might be easier and still get you the kind of data. Okay, so that's kind of my brief intro. So a couple caveats about the class. As I mentioned, number one is I am an AFM person. I do a lot of AFM. I do use a lot of other techniques, but if you want to find out more about different techniques that I might not have covered, I think you have the schedule. Please let me know because there's time we can adjust. But I really do need feedback. So please tell me if you want to have things covered differently. I don't bite, come talk to me. Or if you're super shy, that's okay. Here's my email address. You can also email me, but please come talk to me or tell me what you want. In particular, since there's kind of a bit of a diverse background, and I don't know what everyone has covered, if it's a little too much or too little, please let me know. And then what I would like everyone to get from this class is hopefully by the end of the class, a couple of things. I think the first one is really important in science. If you're reading other people's work in journals and things, you want to be able to understand what they did and why they chose what they did. And then once you're at that step and you want to do an experiment, you need to know which tool you're going to use. And so hopefully I'm going to cover different tools and how they work so that you can be an informed scientist and make those decisions, but also importantly, read other people's work and make your own judgment on their work, whether you agree, disagree, or how to interpret their data. Hopefully also by the end, you should all be excited about nanomechanics. You should all want to do nanomechanics. And we'll talk about some of the latest developments, particularly on Thursday, some of the things. So I have a review article for everyone that we're going to email. Yes, we're going to email you all the review article. I think it's a good background. It's from 2017, I think, or 2018, so it's fairly recent, of kind of different techniques. We will cover all this, but I'm hoping everyone can read it so that maybe tomorrow morning, if you have questions or you want to cover certain things, you'll let me know. And then also this came out recently, and I don't know if people have seen it. It's A Boy and His Atom by IBM. Have people seen this video? Oh, we shall click. I'm going to click it so we can watch it. It's so cute. I think. No, there's no internet. Oh. It's fine. Okay, well, as it's going, it's the world's smallest movie. It is a movie of a person, a boy, interacting with a ball that's an atom, all at the atom scale. And so this movie was made frame by frame by researchers at IBM by individually moving atoms on a grid. And so, I threw a monkey wrench. So hopefully we'll watch it. If it doesn't work, that's okay. I'll send the link. But there's the link to how they made the video, which talks about the techniques they used. As I mentioned at the beginning, kind of historical perspective, in the early 80s, IBM researchers invented the scanning tunneling microscope and the AFM. And so this was made using scanning tunneling microscopy and AFM. And it kind of highlights how powerful these techniques are, because you're making each frame in there is actually atoms being moved around. Now, it's cool. I can't imagine how long it took them to actually do this. But if you see the video, I think that will help. So, questions? Yeah.
So this nanomechanics, nanomechanics.
Yes.
Are they two different?
I use them interchangeably. However, I think there's nanomechanics of biological materials. That tends to be bio-nanomechanics. And then nanobiomechanics tends to be a lot of, when people say nanobiomechanics, it tends to be a lot of like the mechanical interactions of tissues at a small scale, whereas the other way around is more molecular, but they get used interchangeably, I think.
How is it different from mechanobiology?
How is it different from mechanobiology? So, mechanobiology is the study of how cells respond to mechanical forces, right? So, if I stretch a cell, what does the cell do? That's mechanobiology. It's the translation of mechanics to some kind of chemical translational response on the cell. Nanomechanics of cells is actually how stiff is the cell itself. So what is the mechanical response of a cell to different environments? So you could put in a chemical thing and see how the cell mechanics change. You really can't do one without the other, but it just depends on your focus. So I would say in my lab we do nanomechanics of cells. I work with a colleague who does mechanobiology, right? So I do a lot of nanomechanics of the cells in the cardiovascular system. You have an artery and it has dysfunctional smooth muscle cells. The mechanical properties of the artery change. The cells themselves cannot generate the same amount of force. That's very much cell nanomechanics. If I'm looking at how the cell responds to a different pulsatile flow, that's mechanobiology, and they should feed back to each other. Right? It's hard to decouple them, but that's kind of yeah.
Talk about this. Talk about this synthesis.
Yeah.
Biology is synthesis.
Mm-hmm.
How much of that is
Right.
actually?
Yes. Yeah. We'll talk a bit about it. Yes. So bottom up versus top down. I don't know if people heard in the back. So the question was, in biology, tends to be bottom up, and engineering traditionally has been top down. And how could I have gotten at engineering things bottom up? That is a question. The answer, I think, has changed a lot if you had asked me 10 years ago. I think now there are a lot of applications and things that people have made that are very much bottom up. There are polymers that you can assemble into very complex structures automatically that are being used as foam fillers for bone because they have more micro structure than previously done. We've gotten pretty good at bottom-up engineering on the micro side. Getting nanoscale biology is very good at that. We haven't gotten that good at it for commercialization. We'll talk about some techniques where you can actually engineer things very much at the nanoscale to be very highly patterned and things like that. But growing that up to do it in bulk in a big setting is difficult. So, as an example, as a side project, in my lab, we studied spider silk. So, spiders make spider webs. They have all sorts of really cool materials. They're very biocompatible. We would love to use spider silk for all sorts of materials. However, anyway, as this is going, unlike silkworm silk, you can't grow spider silk commercially because if you put two spiders next to each other, they will eat each other. So we were trying to find ways of synthesizing spider silk. And so I had a friend who genetically engineered tobacco plants to make the monomer that makes up spider silk. And so the tobacco plants started spewing out this protein. We have the protein precursors to make spider silk. Now, if you look at the inside of a spider, how it assembles that structure is very complicated and it's not quite understood. But we had this vat of protein and we had native spider silk. We had students actually pull the spider silk. And we worked a lot on different ways of trying to engineer systems to replicate some of that. And we got some of the, again, how large the silk was and everything, but the actual internal structure, we haven't been able to do that. My goal was to be Spider-Man. I had vats of spider goop. I was trying to explain to my students, they made all these like very well engineered things to pull fibers. I was like, I want like a thing to squirt out this way. I never got one of our students. They're too conscientious. They didn't see my vision. So yeah, but yeah, so it's getting there. And I think actually some of the things with genetic engineering are kind of marrying too, because you can engineer systems now, biological systems, to actually do the work for you.
Yeah, as you mentioned, one of the challenges is the way these studies actually do it.
Yeah.
The polymerize just
Yeah.
deeply and how you can just
Right. And so I think, yeah, the inside of a spider is very complicated. There's like a whole bunch of pH changes that happens and progressively smaller nozzles and all sorts of things in the spinnerets, and then they have four spinnerets that actually spew out little profilaments that then make the whole fiber. Yeah, we haven't quite gotten there yet.
Especially modifying this molecular mechanics, usually because I am basically I'm a computational physicist, so earlier days to like quantify the molecular mechanics between two molecules, especially molecular interactions, we use different force fields.
Yes.
Basically from Leonard-Jones potential and by the radius approximation. But in our point of view, it is like it is applicable for a smaller system, especially at molecular level. But then when we take aggregation of molecule, really is a bottleneck now. So I hope in the next lectures we will have how to overcome this and how this instrumental technique, which can be the interface
Yes.
between the computational thing, and so that it can be applied for a little larger system.
Right. And so actually yes, we will touch upon those things. As an AFM person, I think one of the nice things with atomic force microscopy is you can change the tip on the system. So you can actually measure individual molecule interactions and then whole assemblies of molecules, which was the reason we did it for cartilage, because cartilage is a highly dense polymer kind of network. And we had some basic models of how single side chains interact, but then you put them together, and it was just, how to do that. And so, yeah, we'll touch upon that. And I think a little bit it gets to my point earlier about moving to continuum, right? At some scale, you have to think about individual molecules as individual molecules. Then you put more molecules, maybe there's salt in there and all sorts of things. And at some point, you can think about them as an assembly. It's bridging that gap that has been tricky in the past, but we're starting to get there. Yes? How to study the change in cancer? Yeah, so yes, the properties change frequently, and so I'm not a cancer biologist, that's my precursor. I do nanomechanics, and we've looked at kind of the mechanical changes that occur during different transitions, different types of cancer. I think that has a lot of importance both clinically in terms of how the disease works. So the example I gave of metastatic cells being able to go from the tumor all over because they suddenly become this kind of very soft, almost fluid-like thing where they can squeeze between pores is really important. But also there's actually diagnostic applications. So looking at tumors, how stiff and soft they are will help for trying to find them. Also, it has been shown for how to get things into tumors. A lot of people have been doing that. So yeah, it's kind of, we're getting there. One of the biggest issues I think with studying cancer, and again, this is my personal opinion, is we can study cancer in people and animals, but when you take cancer cells out and you put them in a dish, they don't behave the same way that they did in the animal. And so there's a lot of work going on now on trying to make more realistic culture systems that take into account some of the micro-nano environments so that the cells, these cancer cells, look the same. Because the idea is if you could get a biopsy from somebody, make accurate mini tumors, then you could screen for a lot of cancer therapies before you give it to the patient, for that patient, right? So you'd have a better personalized medicine approach. We're not quite there yet, but I think there's a lot of work in that field. Yep. Oops, sorry.
For continuum, you had include the heterogeneity.
Yeah. It's easy. So,
Example for pores here.
sorry?
Example pores here.
Yeah, so you can think about porosity in terms of a number that you can apply to the whole thing. So like it's 90% porous, but you don't have to think about, there's a pore here versus there on the material. So that's the idea of a continuum, is that kind of an approximation about uniformity of in general how it
Great
is.
complexity.
Right, and the key thing there is I think, if you think, let's take a cell. It has a cytoskeleton and all these organelles in it. But if I'm looking at things on a more microscopic, I don't really care, right? I want to know how the cell will respond. I don't care the fact that there might be space between two parts.
For nano indentation,
Yeah.
there is difference from what indentation we do for mechanical
Yes.
materials, or is it same?
It depends on the material, and we'll talk about
Techniques,
it.
for normally we use speaker hardness.
Yeah.
Are they same or?
Yes, yeah, so for a lot of materials, people still do that. So like if you're doing bone, things like that. If you start looking at very soft biological systems, it doesn't really work anymore because they're like over 50% water. But yeah, we will actually do that.
So as the nanomaterial enters into the cell, it is always surrounded by a protein core.
Yes,
Will the forces will drastically change when the nanomaterial is alone?
versus in the cell. Yeah. So yeah, I actually will talk about that on Wednesday. So kind of one of the big things I've seen in nanotechnology and people making nanomaterials is if you look 10, 15 years ago, lots of people published lots of papers with like, we have created this beautiful nanoparticle, it's beautiful, we're gonna put it in humans. And then you stick it in people and you suddenly have all this protein gunk that's around your material. I think that's changed, right? So now, if you're saying that, you have to show how the particle interacts with the proteins and how that affects how that interaction goes. So some of the tricks that people have done, kind of similar to what I was talking about before for material and proteins, you can make coats on the outside of your nanomaterial that kind of help that the nanoparticle interact with certain protein and not others. But you have to know kind of what the first are. So that's kind of the techniques.
Different surface modifications.
Yeah. If it's not working, it's okay. Okay, cool. I was gonna say we can take a break and I can show it at the beginning of the next one. It doesn't like YouTube. I love YouTube. I'm sorry. Did anyone have other questions? Things you want to know? I was told I was supposed to mention that besides doing all the science things, I also like to do ballet. So if you're ever in South Carolina in December, I Oh, yeah, it'll get corrected, yes. Okay, I was told we are starting again. So, as I mentioned, I wanted to today maybe talk a bit about imaging and kind of how to see things at that scale, so that gives a context of what you can do for tomorrow when we actually measure the forces. So the first technique I want to talk about is electron microscopy, because at least everyone is more familiar with electron microscopy. You've all seen pictures. But I wanted to talk about how electron microscopy works, because I think that's very important to understanding what you can see with electron microscopy, what you can't see with electron microscopy, how to use it for different things, and kind of how powerful of a technique it is, but kind of what are its limitations. So, the first thing I wanted to do was to talk about wavelengths. So, as a show of hands, so we had, like, no one has used electron microscopy, but everyone's seen electron microscopy pictures. How many people have used an optical microscope? There we go. Okay, right? So we have all used optical microscopy. So you know how that works. Well, why can't we use it to visualize things smaller, much smaller than a cell, right? The smallest thing you can usually see with a standard optical microscope is like a cell, maybe the nucleus, right? Bacteria, and that's pretty much the limit, right? You can't see molecules. So this is the visual, this is the electromagnetic radiation spectrum. That colorful band in the middle, that's visible light, right? If you look at wavelengths of visible light goes from about 400, right, nanometers to about 700, so if you go from blue to red. And if you get shorter than 400, you're in ultraviolet, and then bigger than 700, you're in infrared. So that's visible light, that's what we can see with our eyes. So the question is, why can't we see molecules? So, if you think about a usual visible light microscope, what's the smallest thing you can see? And I have multiple choice, so we can all raise our hands. We have 40 microns, 4 microns, 0.4 microns, 40 nanometers, or 4 nanometers. Okay, so how about we do it this way? How many people think you can see something that's 40 microns with an optical microscope? Yes, we can see, right? Yeah, so 40 microns you can see, right? That's the size of a cell. How many people think you can still see 4 microns? Right? The 4 microns, that's the size of the bacteria cell. You can see that. How about 0.4 microns? Okay. 40 nanometers? 4 nanometers. Okay, so technically 0.4 nanometers or so, 0.4 microns, so 400 nanometers, that's about the resolution limit of an optical microscope. There are tricks you can do to get better than 400 nanometer resolution. So if you use confocal microscopy, you can go to like 250 nanometers. There's other tricks. We'll talk a little bit about some of the super resolution microscope, but with the standard microscope, about 400 nanometers. And that's because, again, visible light is 400 nanometers. Anything shorter than that, we can't see. So that kind of gives you the limit of what optical techniques tend to be able to see. So in order to be able to see things smaller than the wavelength of light, we need to use something that has shorter wavelengths. And that's what electron microscopy does. So the idea with electron microscopy, it's been around for a while. So in the 30s, they realized that electrons can act like light. So you can have a beam of electron, it can have a wavelength, it can travel in a way that's similar to light, and then you can use magnetic fields to actually move the electron beam around the way you would with lenses for light. So the shortest visible light, as I said, is about 400 nanometers, but wavelength of an electron beam accelerated at 100 volts is 0.12 nanometers. So with an electron beam, if there was a way I could visualize what the electron beam is interacting with, I should be then able to visualize and see things much smaller than what I can with visible light. So that's the principle of electron microscopy. Again, you want to remember that electron beams, they're particles, right? Electrons are particles. So if they hit a target, they'll scatter. But they do act like waves. They travel in straight lines. They make shadows. If I, put something thick enough, the electron won't travel. They won't make it through. But they can pass through thin metal foils and things like that. So we can manipulate electron beams using magnetic fields. So I'm sure everybody's done basic physics, right? You have your electron, it travels into the magnetic field, right? And as it comes in, you have a force, you do a cross product, and this is, I don't know, they do this the same way, but we do the right-hand rule, right? Figure out which way the force goes. And then there's that one kid in class that's using his left hand, and you're like, oh, that's not good. So right-hand rule tells you which way the force is pointing, right? This actually is how old television monitors work, right? It's a cathode ray that scans across the screen. Obviously, we have nice fancy monitors now. We don't have those giant TVs anymore, but that's the working principle. If you do have a giant old school TV, fun experiment, which I did when I was a kid, is you have the TV and you have the image. If you put a magnet on the TV, then the whole image skews because the electron is no longer going the way it should. Okay, but how do you generate an electron beam? You use what's called a semionic gun. Basically, you get a tungsten filament. You pass enough current into the tungsten filament that you pop electrons off. And then you use an electric field to direct the electron and accelerate it to your target. I know I could use the pointer, but this is easier. So here I have my filament. I excite it really hard, put lots of current through, poof, I pop out electrons. And then I have an electric field, so I put an electrical potential between the cap and the anode plate. And the electrons accelerate down. And then I have a pinhole, so it kind of has a more small shape, and then the electrons pass through. That's how I generate an electron beam. Really, it works the same as an incandescent light bulb, right? Incandescent light bulb, I send current through and I pop off photons. Electron beam, I just send more current through and I pop off electrons. So the initial electron beam comes out, and then you can actually focus it and move it using magnetic lenses. So basically, I use magnetic fields to focus my beam the way I would with lenses on an optical system. And then my electron beam interacts with my sample here. Now, one thing to note, and why electron microscopy facilities tend to be in some big room somewhere, is that you have to actually use vacuum with the electron beam to interact with your sample. If I don't have a vacuum, say this is my sample here, the electrons from the beam come out. The electrons come out, and then here there's air. They're going to interact with the molecules in the air and scatter everywhere, and I won't be able to see my sample. And so a lot of the bulk expensive things having to do with electron microscopy is the vacuum system. So the system, the microscope, has to pull enough of a vacuum to really get rid of any air and contaminants in the chamber so that you can actually image your sample. So this is just a little bit better schematic. So you have your electron beam that comes out. You use magnetic fields to make lenses to focus your beam. So if you've ever looked at an optical microscope, it has an objective, focusing condenser, same thing. This works the same in electron microscopy, you just use magnetic fields instead of a glass lens. And then you can use metal apertures the same way you would in a microscope with a pinhole to change the light. You can use metal apertures to make kind of a pinhole for the electron beam. So in terms of the setup of an electron microscope, they're bulky, but they're really set up pretty much the same as your standard lab optical microscope, but with magnetic lenses and an electron beam instead of a light source and glass lenses. So if you do that, you'll do what's called transmission, TEM, transmission electron microscopy. So when you do that, you send your electron beam onto your sample. The electrons hit the sample. Some of them go through, some of them don't go through, and you get these kinds of pictures. So the same way you would with transmission optical microscopy, right? Light goes through, and you see what light comes out. So typically these use pretty high power beam. You're imaging through the sample. You get exquisite resolution because again, my beam now has a wavelength of fractions of nanometers. So I'm able to see with TEM a lot more things than I could with optical microscopy. So with TEM, you can actually see atoms very easily. You can look and see, so this is a bacteria. So you've done optical microscopy in the lab. What does a bacteria look like in an optical microscope? It looks like a dot, right? In TEM, you can see the surface coating, the surface of the external surface of the bacteria. It has all sorts of structure. Inside, there's DNA and things inside the bacteria. So you can see all those things with TEM. There's a couple of drawbacks of TEM, and most of those have to do with sample prep. So the biggest thing with electron microscopy is you have to pull a vacuum. So I can't just stick cells in my electron microscope because they're in water, and if I pull a vacuum with water in there, all the water will vaporize everything and you'll ruin the instrument, and then whoever owns the instrument will be very upset because they're expensive. So you have to dry out your sample. And then for TEM, you're looking at the electrons that go through your sample. And so if your sample is very thick, the electrons won't make it through. So you're going to have to take slices. So it's important to keep in mind you need to make thin slices. The other thing is electron beams can have high power. So if you're imaging a certain area for a long enough time or too much high power, you can actually burn through your sample. So you have to be cognizant of that. And then the other thing is you have a limited field of view. So the electron beam has kind of a width of the beam, and so that's what you can see in the TEM. Just an aside on imaging, particularly at this scale, with TEM, you can do fancy things to kind of highlight things in your image. So these are atoms in glass, and I don't know how many of you do materials type stuff, but glass, right, is like a semi-amorphous type solid. It has like crystalline regions where they're well organized, and then it has melting and reforming regions. And so in this particular paper, they kind of did what's called false coloring, where they added color to different areas to highlight this is the crystalline region, this is the part that's melting into the amorphous region, right? That highlights things. This is a bacteria, same thing, you kind of false color to highlight. So that's great. You should be careful with that because you only want to use it, you maliciously, right? So you can use it to highlight something, but you don't want to use it to manipulate your data. And I only wanted to point this out because recently there's been a bunch of people who have done naughty things with their images and have gotten their papers pulled back, and it's very bad. So this is an example of a very bad one where they were imaging gold nanorods in some material, and they made the conclusion that the nanorods self-assemble into these structures. But then if you zoom in, you can see they actually lie. Right? This is like copy paste. It's not really there. I don't know if you can tell where this is not like. So, this is another example that got pulled recently. This link actually has a really good review of kind of some of the things that happen with people manipulating images to do things. I point this out for two reasons. One, you're all going to be reading papers and maybe becoming scientists and reviewing other people's work. And I point this out because a lot of times in the press, you hear like, oh my God, how did this paper get through peer review? When it's blown up on the screen like this, it might be easier to see how this is like a falsified image. But when you get the paper and you're trying to review it, it's hard to see. So as reviewers, it's our job to look at data. But as this recent article points out, more and more journals are actually putting in automated image checking algorithms to check for these things. And they will catch people who are trying to falsify data. But they'll also sometimes ping if you're trying to do something like, people aren't trying to falsify data, they're just false coloring the image to highlight stuff. So it's important when you manipulate your images to always fully explain everything you did to your data in the paper so that you don't get yourself in trouble, and also so reviewers know. It's okay to do some manipulation if you're really trying to show something, but you have to explain and justify why. Yep.
For the text, we have very research software.
Sorry?
For a text material for manuscript, they can check that plagiarism.
Right.
Is there any software to check the originality of the images?
Yes, I've seen it. It's a great question. I can't remember. So some of the journals use stuff like that, and there was a link somewhere someone sent me that people could submit so you can check and make sure. I don't remember off the top of my head, but it's probably in Google.
But Google itself has come out
Yeah.
with such facility.
Yeah, like maybe Google Images, right?
Yeah.
You can actually upload an image
And
and
upload
look
and
at
then
it.
it will compare
Yeah.
it.
But there's a software where you can upload also, and it will highlight places where if somebody, what you don't want to do with image manipulation, in general, what you can do is like, if you have an image and it looks dark, right? You could increase the brightness in the image. That typically is okay as long as you do it for all the images, all of it the same. What's not okay is to take like this corner and brighten that corner, but not the rest of the image. And so there's software that will detect that kind of change. But yeah, it's a good question. Okay, so back to actually doing some science. So we're not going to do that, but just so you know, it is, and a lot of times the nano stuff, in TEM, when you talk about it in lecture and stuff, you pick out these beautiful images, right? Bacteria looks so pretty. When you actually do TEM, a lot of times it's like I'm squinting and this thing. Like we use TEM a lot when we're looking at how nanoparticles get into cells. So nanoparticles interact with the cell membrane, and then they can do pinocytosis and kind of like grab it in, or they might pull it out. There's all sorts of different mechanisms, and really TEM is the only way to visualize and see how the cell's actually doing. And I have a collaborator who's very good at TEM, so he usually preps our samples and takes the images. He's like, this is great, you can see the nanoparticles, and I always look at the picture and I'm like, I can see the nanoparticles because they're like little round things. But then the rest of the cell, because you're only seeing like a very small area of the cell right at the membrane, it always looks like soup. Like, I'm not very good at interpreting them. So that's the other thing to keep in mind when you're using TEM. It's so zoomed in, and we don't have a good visualization of what that looks like, that sometimes it makes it hard to interpret. So this is actually a schematic of TEM set up from Wikipedia. And the nice thing with this is it actually shows you how really this is set up like a standard optical microscope, right? You have your source, the electrons come down, and then there's a condenser, and then an aperture and a second condenser, exactly like an optical microscope would with lenses, but with magnetic fields. You put your sample there, and then the electron beam comes out, and you can either visualize it with a fluorescent screen, so like electrons hit the fluorescent screens, photons are produced, and then I can see it. Or there's a detector that will actually put it in the computer these days. So that's TEM. If you've ever seen TEMs, they're very big because they need the space to have the beam come down. The thing you're probably more familiar with is SEM, scanning, or secondary, optical electron microscopes. The key with SEM is instead of like having the beam go through my sample and looking at what electrons go through, I'm going to send the beam, scan it over my sample, and look at the electrons that come back. So I have the beam, it comes down, it hits the sample, and then I have electrons coming back up and then detectors. So it will scan across your sample, which means that at no point in time do I have a full image. I'm just getting point-by-point representation, so I need a computer to reconstruct the whole image. Kind of like if you've ever done confocal microscopy with a laser, same thing, right? I have like, ooh, we're going to do a laser. Confocal microscopy has a laser beam that scans across my sample. Same idea, but now with an electron beam. I have an electron beam, it scans across my sample and look at the electrons coming down. So scanning, so SEM is the thing you typically think about when you think about electron microscopy. That's where you get these lovely pictures of like a bug's eyeball, like all those textbook things where they zoom in onto things. That's very much SEM. So that's a huge advantage of SEM, is I can actually image millimeter, like even centimeter length things, and then just keep zooming in. It has a huge range that it can image. It can't quite get the resolution of TEM. So the limit for SEM is typically about 10 nanometers of resolution, but it has a range that it can image. So you can image very, like, you know, millimeter, centimeter, almost type things, and then you can keep zooming down. So a couple things, in order to get electrons coming back to your sample, especially for biological samples, you need a conductive type surface. So typically what people will do is take their samples and they will sputter coat a very, very thin layer of a metal, typically gold or platinum or something like that, onto the sample. So here is a mosquito. Mosquito goes into the sputterer, and now you have gold-coated mosquito. And you can image that. If you don't have a conductive layer on your sample, you risk most of the electrons are going to hit the sample and then just stay there. So you don't get a lot of electrons back. So what are the electrons that come back? So this is actually text, but I think it's useful to look at the actual diagram. So my electron beam comes down, and then I have things that happen. So this is right there, there's a bonus, I have an electron, it comes down. I have secondary electrons. So secondary electrons are what I use for imaging. They're very much just on the surface. If you look at what secondary electrons are, then they're a result of when your electron from the beam comes down and interacts with your material, it imparts enough energy that electrons on your material actually pop off, and those are the ones I measure. So it's not the actual electrons that are from the beam coming down, coming back that I measure. It's actually electrons from the surface of your material that are coming back that you're using to measure. And that's why it's useful to sputter coat with a metal, because you get a lot of secondary emission from metallic surfaces. The actual electrons themselves that you're on the beam, they actually can penetrate more deeply, and then you get what's called backscatter electrons. So that's the electrons interacting with your material, bouncing off of the nucleus, and coming back. The interesting thing with backscatter electrons is they can give you more compositional information than the secondary electrons. So if you look at the secondary electrons penetrate maybe like 1 to 10 nanometers, so it's very much a surface. It's kind of like a picture, right? You're looking at the light coming back, so this is like the electrons that are very much at the surface. Backscatters electrons, your electron beam penetrates a bit more deeply, and then it hits some nucleus of your material. It comes back. Depending on the size of the nucleus it hit, right? If you think about the collision, right? You have an electron, big nucleus, or electron and a small nucleus. The velocity that the electron is going to come back at depends on the nucleus it hit. And so I can actually measure that and get some information about the composition, at least in the first couple of microns of my sample. So it's a nice way of imaging and then also getting some information about my material, particularly when I have these very highly structured micro nano scale surfaces. If the electrons make it far enough away, I also get X-rays coming off of my material, right? So electrons come in, impart energy, and I get photons, X-ray photons coming back. The wavelength of those X-ray photons also depends on the composition of the material. So that also gives you some compositional information about the material. So all that together makes SEM quite powerful, because you can actually typically both measure the surface in terms of get a picture of what it looks like, but also get point-by-point compositional information about your material. So you kind of get a topographical looking image. We'll talk a bit more about that. By counting the secondary electrons. I, at each point, need to count those. So you typically have some kind of photomultiplier tube that will count those. And then I convert that into a brightness. So if it's really, really bright, that means there's lots of electrons coming back. If it's dark, no electrons coming back. And that gives you my pixel value on my image. So at every point, I basically tell you how many of the secondary electrons. And so that's why you get these lovely pictures that look almost 3D, because depending on the angle, I get more or less electrons coming back to the detector. So this is some just mouth parts. This is like really highlighting this. This is a engineered silicon wafer, and it has gratings, right, like in the material. And so depending on the angle of the grating, I have really bright areas because it's like bouncing electrons back to the detector. So you get lots of electrons. Now, it's important to note that you kind of have a 3D looking view, but you don't actually have three-dimensional information, right? So it kind of looks like it's bar feet. But just from this picture, I can't tell you how deep this is compared to that. If you actually want a three-dimensional map of your sample using SEM, you need to take images at lots of different angles and reconstruct. So it's the same thing as like regular, camera picture. If I really want a 3D picture of somebody's face, I need to take pictures in lots of angles and then reconstruct. So same thing with SEM. So a couple of things with SEM. The resolution is determined by predominantly parameters having to do with the electron beam. So what's the size of the interacting volume and the size of the transmitted beam. And typically, as I said, it's 1 to like 10, 20 nanometers is the resolution limit of SEM. If you remember TEM was 10, 1/10 that, right? So you've got 0.1 nanometer resolution. So TEM, you can see atoms. SEM, you don't quite have the resolution, so typically it's about 1. The magnification is determined by the acceleration voltage on your instrument, and typically it's something like 500,000 times magnification. So this is a picture I got that I think highlights a little bit about what the power of SEM can be for nano and micro technology characterization. So this bottom picture is your standard SEM picture. So it shows you the secondary electrons. And if you look, it looks pretty smooth, right? There's not a lot of topographical highlights. If you look at the backscatter electrons, however, you'll see there's really bright areas and really dark areas. What this particular material is aluminum with zirconium aggregates. So it has two materials. It's an aluminum matrix with little aggregate particles inside the matrix. And on regular SEM, you can see it looks pretty smooth. So it looks like the zirconium actually embedded pretty well into the material and didn't clump up and make funny bumps. But then if you look on the backscatter, you can also see where those zirconium aggregates are. Right? And they're kind of uniformly dispersed into your material. A lot of times, if you're actually making one of these composite structures, that's what you want, right? You want your two materials that you're mixing together to kind of form a uniform kind of thing and not be like one clump of zirconium inside a big sea of glue. So that is really helpful. For some of the studies we do with cells and nanoparticles and things like that, these kinds of techniques are also useful because you can image your cell and then look for if you have, I don't know, gold nanoparticles. You look for where is there gold? Is there gold? If there's gold, it's probably from your nanoparticle. Cells don't typically just have gold in them. So you can show that the particles went in. This is a better picture kind of showing you how the beam comes in and interacts with your sample at different depths. And so depending on the characterization tool you're using, as I said, the secondary electrons kind of give you a surface picture. And then if you're looking at the backscatter or some of the characteristic x-rays and things, that gives you compositional information about your material at different depths. So, a couple things with electron microscopy. It's very nice. You can get TEM, super high resolution pictures, right? You can image atoms. In SEM, you can like zoom in, you've got a piece of tissue and you're trying to see where, say, nanoparticles went in. You can image the whole big chunk and then keep zooming in until you find your puzzles. However, electron microscopes are very expensive. So a new electron microscope system typically is in the millions of dollars to set up. There are some newer versions that are like kind of less powerful tabletop electron microscopes that are more in the like $500,000 range. But in general, electron microscopes are $1 million instruments. They're also expensive to set up initially and expensive to run. And part of that is the vacuum system, and a lot of things like the source need maintenance. So when you buy one of these instruments, you have to have a maintenance contract, and so it adds cost. If you really want to do super high resolution kind of things, you can't just put your electron microscope anywhere. You need it to be nicely vibration isolated, right? Because if I'm walking along like this, I'm making lots of vibrations, and my poor electrons hitting my sample are moving around, and you'll just end up not seeing what you're trying to do, particularly if you're trying to see things like atoms, right? I can't have things vibrating around when I'm trying to image something that small. Also magnetic fields, obviously. If I have a magnet nearby, well, the electrons won't go where they're supposed to. And so typically, electron microscope systems are not always, but if you're good, you put your electron microscope on the first floor, or I forget whether the US does the first floor, the ground floor, right, on the ground. Because you don't have the building motion, right? The higher up you go, the more your building is going to move around, and that's going to be a problem. If you're really nice, you put your instrument on what's called a floating floor. You can't put the hole in is huge, so you can't put it on like an airtable. So what you do is you have a room, and then you cut a giant hole in the room, and you dig in the hole, and then you put a bunch of sand and everything, and put a platform, and that's what your instrument sits on. So now the instrument is not connected to the foundation of the building, and it's kind of vibrationally isolated from the rest. And now if a big truck rolls by, everything is shaking, but your instrument is on a bed of sand, so it kind of isolates it from the vibrations. So those are kind of the expenses and why they're tricky to have. And then the other thing to keep in mind for you as a user is sample preparation is very important. So as I mentioned, electron microscopes, your sample has to go in vacuum. That's a problem for most bio things. We do not live in a vacuum. For a physicist, not a problem. Math is much easier in a vacuum. We wish we could always be in a vacuum. But for bio, we're not, right? We're fluid, and there's salts and all sorts of stuff. So sample preparation is very important. So if you've ever prepped a sample for optical microscopy, right, you fix it. People have done this. Who's actually made slides for optical microscopy? Okay, great. So you fix your sample, you dehydrate it, and then you put a stain, and then you're going to image. So it's kind of a similar process, but typically it's a little bit more harsh. And that's because, again, you want all the liquid out of your sample, and certain buffers will actually precipitate when you use them for electron microscopy purposes. So typically you want to avoid anything with phosphates in them. So for those of you doing cell things, you tend to use PBS, right? Phosphate buffered it's great. If you use that for electron microscopy, particularly TEM, and you do all your sample prep, you'll get weird salt aggregates in your sample. But if you do all that, you'll get lovely pictures. So, yeah.
What mistakes during sample preparation may cause artifacts in the...
Yeah, that's a great question. I have some slides about that. But yeah, so a couple things that cause problems with sample prep. The first one, and especially for TEM, because TEM is fairly harsh sample prep, you want to get all the water out, and then you have to slice your material. It's not a mistake so much as something to keep in mind. The cells will not look the same as they did in the fluid. And so if you think about, I have my cell, it's happy living in its media, and now I fix everything, and then I put it in these solutions, it tends to blow them up so that they don't have the shape that they want. And so it's not so much of a mistake, it's just a thing people do that you need to be cognizant of. If the point of your TEM image is to look for where nanoparticles went into your cell, that's fine. I'm going to see, oh, it got into this organelle, or it's stuck on the surface of the membrane, or something like that, that's fine. If you're using the TEM to be like, this cell is 50 microns in length, and there are these organelles that are X, that's not going to work with TEM, because the sample prep itself distorts your cells or tissue a lot. The biggest one I've seen, just mistakes that actually happen with students, is having to do with the dehydration step in your sample prep. You really have to go slow. If you go too fast, everything collapses on itself, and the cells kind of explode all over the sample. It's like there's cell bits all over your sample. So that's a problem. Same if you use cryo, you can use cryo techniques. You can freeze the sample really hard, really fast, and then slice it. If you don't do that correctly, same thing. If you think about how freezing works, you get ice crystals that'll break everything in your sample, won't look right. And then when you slice it, it gets very brittle and it comes off. So my advice for sample prep for electron microscopes, I think SEM is a little bit more forgiving. So in general, if you follow a protocol for SEM, usually it works okay. You might want to tweak it a little bit for your sample, but it's not too bad. If you're looking at TEM and you want really high resolution things, find someone who does this all the time. And go and learn from them what techniques they use, because there's like tricks that they don't really write in the protocols. Like, I swear, there's this guy at Clemson, and he's very good at it, and he helps us with our sample prep, and I swear there's a, where you like put it in this buffer, and then you put this buffer, then you jump around, make a pretty dance, and then somehow you put it, if you don't jump around and make a pretty dance, it doesn't work. And a little bit, just a little bit. I think for one thing, actually, one of our issues at Clemson, being in South Carolina, in the summer in particularly, it's hot, it is very, very humid. And that actually comes up a lot for nano stuff. It's very humid all the time. And so when we're making samples in air, in the summer, it's like there's a humidity layer on all of our samples. And so it actually is a problem for electron microscopy prep. So we have a separate room that they've like put a dehumidifier in to help with some of that.
That's a control room, right?
Yeah, it's a control room for sample prep. But like for optical microscopy, I can do the sample prep in a regular room, it wouldn't matter. But for electron microscopy, the instruments also need a lot of dehydration. I think when I left, so I said, okay, I calculated, it's like 40 degrees outside centigrade and like 95% humidity. It was awful. So you can imagine, obviously all the rooms inside are air conditioned, but the humidity, unless you actually have a separate control, causes some problems. Yeah, other questions?
This particular picture, bonds.
Which one? This one? Yeah,
It's a centimeters.
it's an SEM image, yes. That's actually from Wikipedia. I usually put the link. So yeah, this is from Wikipedia. It's an SEM. This is these, I think, are all SEM. This is T. So this is an ant, and again, you can see, you all know how big an ant is, right? So you can see its head. But then what they did in this particular study is they zoomed in to look at the folds, because there are sensing mechanisms in the ant, and then they have these little tiny hairs that actually do some of the sensing functions, so they're able to do that. These are pollen, so give me allergies in the spring. This is very much a nanotechnology problem. This is asbestos. People know what asbestos is, right? Asbestos is this material that in the 70s they put all over the place because it's a great fire retardant. Put it all over. And then after that, they found out asbestos causes lung cancer. So that's unfortunate. It causes lung cancer because it's a very nanostructured material. It's these tiny nanofibers. And what happens if you breathe them in is they get into your lungs, and you have cells that clean up debris. And the cells will come in, and they will see, okay, this is a really long thing, but they always see that it's like a couple nanometers big, and they will try to eat it, right? So they'll start eating the fiber. And then they will do what's called frustrated phagocytosis, because they'll start eating, and then this fiber is really long, and they're still trying to eat it, and it will go through, and that actually causes DNA damage. That's what causes cancer. It's the same reason that carbon nanotubes, if you breathe them in, will also cause cancer. So yeah, this is one of the studies that looked at the structure of asbestos to try to understand why it causes cancer. This is actually very nanomechanics related. It's dynein molecule looked at with TEM to try to understand the assembly of this kind of molecular motor and what it looks like. So they actually put these molecules isolated onto, I think it's mica, and then imaged it in different conditions to see what the structure looked like. So a couple things. Obviously, you can do lots of things with electron microscopy. One of the things to keep in mind with electron microscopy, I'm going to talk about AFM and atomic force microscopy a lot because it's my baby. But I think SEM and TEM are kind of gold standard techniques, right? If there's an issue with, I don't know, hip implants, right? You have hip implants and like all these people have issues because they start fracturing and there's a lawsuit. What the courts are going to want is SEM pictures of the fractures to show that the fractures are looking like a certain thing. That's to show the mode of the defect. So you can do lots of things, but eventually you'll probably want to do some electron microscopy. So this kind of gets at your point of like issues with sample prep. I got this from a paper, I think I have the reference right here. It was looking at using electron microscopy to understand chromosome architecture and how chromosomes in your cells form. So, you know, when the cell is not multiplying, the DNA is a certain way, and when the cell gets ready to multiply, it packages up the DNA into chromosomes so that it can split. So they were trying to understand how that mechanism occurs, and they looked at different techniques. And they ended up using SEM, but what they were, they went through different techniques, and obviously, I'm sure it's fine. So with confocal microscopy, we talked about you don't have the resolution. You can see chromosomes because they're very big once they're assembled, but you can't zoom in and see the inside of the chromosome and the DNA and how it actually happens. TEM has great resolution. And you can't really see things in 3D. And then I like this point. It's very time consuming. Love this. AFM is great in that you can see things dry or in fluid. We'll talk about that in a minute. However, the resolution is limited by the tip itself, and you actually typically, the tip will scan across. So we'll talk about some of the limitations with AFM next lecture, but that's the reason they ended up using SEM. This is a shortened version of their very, very long sample prep section, explaining how they prep their samples. So first, they isolated chromosomes from cells. They used cryofracture to get them out. They used DNA and protein staining. So like you would for an optical microscope, they used stains. The stains use heavy metals because you can see those really well in electron microscopy, and also because those metals aren't found in biological samples, you know for sure that that's what you're looking at. They were sputter coated in, so first they were washed in acetone to get rid of the water. They were critical point dried on marked slides. Then they were using SEM on sputter coated samples. And then they did backscatter imaging to try to find where their stains were. Then I think in the paper, that's like one of the longer methods section, because there's a lot of steps in there I kind of skipped on how to actually prep it all. And in particular, the buffers they used, I think, were osmium-based buffers, again, to avoid salts forming in their samples. These are the visual images they got. So here's a chromosome. You can see the chromosome is like, I don't know, 10 microns, maybe 5 long. And then they zoomed in on this section. So here, this is 100 nanometers. And you can see in your zoomed in section right here, you have these little clusters of DNA. found that they made these blue structures, and then this blue stain is them coloring where the stain for the protein that helps pack DNA together was found. Using all this, they actually built a model of how DNA packs itself from the individual DNA to fibrils to these little flowery aggregates all the way up. Before this paper, people had an idea of, well, we knew the structure, we knew what chromosomes looked like. We also knew that there were helper proteins that helped forming these aggregates, but this is the kind of paper that showed exactly how that process occurs. This is important from a basic science point of view because it's very important to understand what's going on, but it's also important because there are certain genetic abnormalities in animals and people that actually affect this packing and cause problems down the line. The problems have to do typically with your cells age faster than normal cells because the DNA doesn't pack as well. The other thing I wanted to talk about is environmental or wet SEM. You also sometimes call it variable pressure SEM. It's a newer technique that tries to not pull a full vacuum on your sample to keep samples kind of hydrated. So if you have a structure that you're interested in and if you completely dry it out, all the nice structure goes away, this technique is useful. And the variable pressure wet SEM technique, the samples are more hydrated, so it's more like when you do optical microscopy. So when you fix your cells to stain and you put it in, it's that kind of sample prep. So it's a lot less harsh. It's still not wet. It's still not like I have my cells in fluid and I'm looking at it, but they're more hydrated and so they're closer to their native structure. The downside of variable pressure wet environmental SEM is you do get some loss of resolution, and that's because I can't pull a full vacuum, and so I can't accelerate my electron beam the way I would normally, right? There's some scattering of things. The name of it depends on the brand of SEM you get. I want to say, I think like Hitachi calls it wet SEM. I forget, the different brands call it different things, but it's all the same kind of technique. So this is an example that kind of gets at the sample prep issue again. From this paper, which I thought was very nice in that this is an optical stained confocal image of these cells. This is your standard unstained optical image of the cells. These are live cells. This is obviously fixed and stained. This is a TEM image of the cell. And then this is variable pressure wet SEM. So you can see that the wet SEM technique, they're more closer to their native shape. But more importantly, here you can see in TEM, even with fairly nice prep with a group that's their expertise is electron microscopy, you can see the cells have like grown up a little bit because they've been put through all this dehydration step. So again, with TEM you get great resolution, but like for bigger structures of the bio things, you might not be able to make measurements on these kinds of things. Yeah, so that's a review of kind of those. The nice thing with these techniques is it's a little bit easier on the sample prep. If you have access to one of those things, you could prep your sample through optical microscopy and almost do the same prep for SEM. But it does have a loss of resolution. So how does this relate to nanomechanics is the last thing I want to talk about. So electron microscopy, very high resolution. It's a necessary tool for nanomechanical studies. The first one is you want to image structure to know what you're actually probing. If you're doing nanoindentation of hard materials, particularly bone, teeth, that kind of thing, it's typical to use electron microscopy to look at crack patterns and understand what's going on. And then if you're actually engineering materials, the nice thing is most of these systems now come with things like electron beam lithography, some systems have focus beam etching and deposition, and you can actually, as we said before, top-down generate very, very complex, very tiny structures. So this is, just for fun, this is a house, full house with a roof and structure. I believe the whole length is 10 microns, so it's tiny. And this one is a 60 micron PMMA bead that someone used, so that one was using, focused ion beam. This is using electron beam lithography, where they etched a globe. The whole is their root of Japan, so they zoomed in on Japan. But it's a globe etched on a 60 micron beam, kind of to let you know the power of these techniques. It's very cool. It's very high resolution. It is time consuming, so that's why we can't, for commercial processes, really build hundreds of thousands of 60 micron globes. That would take years. So it's great for engineering things for scientific purposes, but for commercial purposes, we're not. Yes, that's all I had for this. I think it's lunchtime. Look, I'm perfect. Are there questions before we go to lunch? Okay. Well, I will be here, so if you have questions but you don't want to ask in front of everybody, I'm here, so come and ask me questions.
that group mail ID. Please open it. Okay. So that it will reduce my timing of copying. So external and internal versions, please go to the email, try to download the data and try to read the review of the certificate. That's a homework exercise. That's right.
I was worried that it would be a lot of work. started making some of the frames. It's kind of cool and it's addictive.
All the action of our movie, a little guy made out of atoms is going to be right on top of one of these surfaces. So to make this animation, we move molecules around one at a time to draw a little picture. And we save that picture and move on to the next frame to start to tell a story.
This is a very challenging task because nobody, as far as we know, including ourselves, has ever moved microwave atoms.
Now we see them in it's filled with all this carbon monoxide molecules, and then some of them we would have to shovel away to make it really big in movie frame, so we would have to clean up a little bit.
When we see the image in the microscope, we see it magnified about 100 million times. If an atom was the size of orange, then the orange would be the size of the whole planet Earth.
What we have been doing for the last 40 years is we've taken essentially the same silicon transistor and we scaled it down, putting correspondingly more transistors on the same chip. Very recently what we have done is we've been interested in the magnetic properties of atoms on surfaces. And really what we wanted to answer is a very simple question. How small can you make a magnet and still use it for data storage?
We know that we can make it stably out of million atoms because that's what's done in current technologies. And we found that for the materials that we chose and that we're able to work with, only 12 atoms is sufficient.
You could carry around not just, 2 movies on your iPhone or something. You could carry around any movie that was ever produced. We're using 2 scanning tunnel microscopes to make this movie. First, we need to look at the surface and we need to figure out where the atoms are. So here we have the atom that we want to move, here we have our needle. And we switch between the imaging mode, where I stay relatively far away, to the moving mode, where I get close in. And now these 2 atoms are so close that they chemically react with each other. And so then we can drag this atom along the surface and position it to a new location. Here you are actually in the microscope room. This is the room where the actual tip is, where the sample is, where the action is taking place. We're working at a temperature of minus 260-something degrees centigrade. We do this so that these atoms hold still. When we're moving atoms in the laboratory, you'll actually hear a noise.
And the sound you hear is the sound of the molecule following the tip along the surface.
For us, hearing this scratchy sound is important feedback because we can count how many positions have you actually moved. You go, and you can say, oh, this was 3 locations. Now, of course, we usually build things that can do computation data stores. In this case, we're just telling a very simple story of a boy named Adam falling in love with an atom, dancing together and playing together.
And I think it's very exciting to be able to share something that I really love. Maybe it helps other people be fascinated just by the size of atoms.
If I can do this by making a movie and I can get 1,000 kids to join science rather than go into law school, I'd be super happy.
The ability to do something just because you find it interesting is a really important thing, particularly for research, because that's how you stumble across things that are new.
Now we can't know in detail what those future technologies will be, but we can lay the scientific groundwork for them. And we can spur our own imaginations and get a head start in exploring these new worlds.
So this is called, when we talk about atom,
Yeah.
you have some properties of the atom in mind.
Right. So they used, I think it was carbon monoxide molecules on a lattice of, I looked it up, I forgot what material. So what they're doing is a solid surface, and then the carbon monoxide is on top. So you have a crystalline surface, and so when you have the molecule, the carbon monoxide is stuck at different parts on the lattice, and so you can move them. That's why we say you can move different clicks is you push, and then the molecule gets stuck at the next location on the lattice. And so later today and tomorrow we'll talk a bit about the tools, and then on the third day we'll talk about kind of the forces. What is it that allows us to move? What forces are playing a role in these? And so most of these are what I mentioned earlier today, they're not contact, you're not really touching the atom and picking it up and moving it. You're using attractive and repulsive forces to push things along. So the example you had with the large scale thing with bulbs, they made it using magnets, and that's obviously not really magnetic fields that they're using to move the atoms, but it's that kind of concept. It's not something where you're touching, it's using longer magnetic forces to give a gentle show.
Like a wonderful.
Yes, yeah. Well, for an atom, so van der Waals forces for molecules and surfaces seem like short distances because they're very close to the surface. But when you're talking about an atom, it's still not touching the atom, it's a longer range. So, yeah, that gives you some background. Really gets you excited. I think it's cool just because technique-wise, you saw AFM and STMs are kind of small. You can put them in any lab. You can see to do what they did with atoms on the surface and really get a clear picture. You need to cool the whole system down, right? Because the smaller you get, the more noise and interactions you'll see. And so to really do what they did is fairly impressive because you need to really get rid of all that other noise and issues. For most biological things, we're not talking about quite that small. And fundamentally, biology is kind of messy. So typically, you don't have to do things at those very, very low temperatures, things like that. But, yeah. Questions? You can think about it, and then I have more questions.
It's not very good. What do you say?
No, you have some questions to present, right?
Yeah, after session, I will ask. After the review comments.
Huh? I'm gonna take notes. I will have questions. I will have questions. Good afternoon, one and all.
So this is a post-lunch session. So I want to make it light. Today being the first day, so I'll give a very basic introduction to mechanobiology. So here Dr. Delphine is an electrical engineer, and I guess she would do more justice to the engineering part of the biomechanics or mechanobiology. And I, coming from a biotechnology background, I would like to focus more on the biology part. And since the audience are also most on the biology background, so I think I'll give so even for the pure mechanical and physics and other engineers, I want to give a very basic introduction to the biological part of the mechanobiology field. So I've divided this session into two parts. The first session I'm going to talk about my journey to mechanobiology, how I ended up in the field of mechanobiology. And then the second part will be overview of topics that we would be doing through this 1 week course. So this is my first session. So I did my PhD in National University of Singapore, the computational bioengineering lab. So and my supervisor was from Auckland University, Bioengineering Institute. So Auckland University has a project called the Human Physiome Project. The International Union for Physiological Sciences. It's called the IUPS Human Physiome Project. So their aim is to create an in silico model of the entire human. So they are building up organ models. So we all must be familiar with this hierarchy. We have the organ system and the entire human body. Then we have the organs, then tissue, then cell, then protein, and to the atom. So we have various levels here, and so they're trying to build models at various levels. They have organ models, then cell models, and tissue models, and they're trying to integrate these models to have a virtual human being. Okay, so that's the bigger picture of this project. So we in National University of Singapore, we're focusing on the gastrointestinal system, which is quite a complicated system. So I'm sure all of you had a good lunch. Yeah. So where do you think the lunch is right now in your body? Huh? Stomach. I'm sure you're very confident it has crossed the esophagus. Yeah. Probably few of you might be getting it back into the esophagus if you're suffering from reflux. But where is it now? What is your guess? It's a human body, it's your body, you must be knowing it better than anyone. Stomach? Not into the intestine yet? So it's in stomach, so very likely to sleep. Right? Because the stomach has to do a lot of work to push it to the intestine. So a lot of energy will be spent on digesting your food rather than sending blood to your brain to think. That doesn't give you an excuse to sleep. This is a short video. So what is this? The stomach of a dog. So they have fed the dog with a radioactive substance, and they're trying to create a movie of the food which moves from one region to the other. So you have the gastric body, antrum, pylori, and the tube is your small intestine, the first region of your small intestine. Okay. So can you see the contractions beginning at this gastric body and propelling the food into the antrum region? And from here you have the valve which opens it, sphincter valve which opens the, pushes the food into the duodenum. So how long do you think the food stays in your stomach before it gets moved to the next small intestine?
3 hours.
3 hours. So where do you think the stimulus for this movement, I wouldn't say contraction, I wouldn't yet go to contraction. Where do you think the stimulus for this motility comes from? Your heart pumps, right? Your heart pumps. So what is the stimulus for your heart? How does it pump? How does the muscles, cardiac muscles contract and pump and do all the mechanical activities? You have the pacemaker cells, right? So we have the pacemaker cells sending the electrical stimulus. Similarly, have you heard that GI system also have their own pacemaker cells, which are called the interstitial cells of Cajal? Okay, these are cells which are interspersed in the smooth muscle layers, which send electrical signals. They receive electrical stimuli from the brain through neurotransmitters, and they also have an inherent electrical, very base, minimal electrical activity combined with this activity from this neurotransmitters. So these pacemaker cells create electrical stimuli which are passed on to smooth muscle cells through gap junctions. Have you heard of gap junctions? Gap junctions. You have gap junctions in cardiac myocytes, right? Similarly, you have very active, electrically active gap junctions in smooth muscle cells. So these smooth muscle cells receive this electrical stimuli from pacemaker
pacemaker cells and other neurotransmitters from the brain, and they get the signal for contraction and relaxation. So a pattern of contraction and relaxation leads to this kind of motility. Can you see this? So what causes this motility behavior is the rhythmic contraction and relaxation between the different smooth. It's not just a single layer of smooth muscle cells. We have different layers of smooth muscle cells arranged in longitudinally, circularly. So the coordinated pattern of contraction and relaxation between these smooth muscle layers are actually causing this well-coordinated motility pattern. Okay. So we have two types of motility patterns in GI. One is the peristalsis, the other one is the segmental contractions. Okay. So the peristalsis is seen in your esophagus and your upper part of the stomach, whereas your segmental contractions are seen in your small intestine and large intestine and the rectal muscles. So what causes, as I told you, the electrical stimulus from the pacemaker cells and neurotransmitters and agonists and antagonists from your various glands in the body, they all lead to this coordinated motility pattern. Okay? So it's like very obvious. The functions is to propel food, mixing and grinding, absorption of nutrients, and the removal of waste. Anything goes wrong with this, it affects the health, of course. So these are the various diseases that are caused by altered contractile behavior of smooth muscles. Okay, so at various regions you have esophagus, stomach, small intestine, large intestine, and anal rectum and pelvic floor. So there are many digestive diseases. It can be from any reason. It could be a problem with the electrical stimuli, or it could be anything. But here I have listed some of the disorders that are primarily caused by the altered contractile behavior of the smooth muscle. Okay? So for example, the cyclic vomiting syndrome or delayed gastric emptying. This motility pattern, what if it happens, if it is fast? What if there is a rapid gastric emptying? Or just imagine if there is a delayed gastric, instead of being your food sitting in your stomach for 3 hours, if it sits for 6 hours, it's a problem, right? So you have, and you also have the GERD, which is a very, so many people are affected with GERD. What is GERD? Gastroesophageal reflux disease. You get reflux. So a lot of people are affected by this due to stress and various lifestyle problems. So this is statistics just to show you the magnitude of digestive disorders. The problem is when it comes to life-threatening diseases, everybody is like interested. But digestive diseases, they're not life-threatening. They don't cause you death. But the socio-economic impact of these digestive diseases is large. Just imagine your food being reflexed every 5 minutes. Can you be sitting in this room and listening to this talk? Certainly not. But if you get a heart attack, it's like, but that's like, yeah, but digestive diseases, they have a huge cost in terms of loss of work and huge medical costs. Okay. So this is just to give you like why it is important to study digestive diseases. So the current research in GI system is at various levels. So there are experimental studies that are measuring the contractile response for a given electrical stimuli. So you have a piece of tissue from various regions. It can be from the esophagus or the stomach or the duodenum or the large intestine. You take a piece of tissue, or the studies have also progressed to single cell level. So you can take a single cell, or you can take a pacemaker cell along with your smooth muscle and find out what is the kind of stimulus, what is the electrical stimulus, and what is the kind of mechanical response that the cell is exhibiting. So these are experimental studies. Then you have our cell biologists and biochemists who are studying the intracellular signaling pathways which are involved in this regulation of contraction and relaxation. Then you have this electrophysiologists who are studying the electrophysiological behavior of smooth muscle cells. Electrophysiology, there's so much work has been done in electrophysiology point of view of GI system. So you have punch clamp techniques and other techniques where you can precisely measure the electrical potential or the action potential exhibited by a single smooth muscle cell. So you have this electrical data from the electrical studies. And you have this very basic smooth muscle contraction models. As Dr. Delphine Dean suggested, never a cell is like the one that is shown in the textbook. It's not, it's very heterogeneous. So those smooth muscle cell has common properties between various organs like uterus, vascular, respiratory and other organs. But there is a slight change in various organs. So we cannot use these generic smooth muscle contraction models for all the systems. So that's where my work was to develop a very specific, GI specific smooth muscle contraction model. So I pretty much worked only with computational modeling. So not much of experimental work. So the electromechanical coupling. So what causes this contraction is the coupling between the electrical activity and the mechanical activity. So the mediator here is the calcium. So the electrical activity leads to a change in calcium concentration, intracellular calcium concentration, and this change in intracellular concentration leads to a whole range of signaling cascade within the smooth muscle cell, and that signaling cascade leads to activation of these contractile apparatus. What is a contractile apparatus in a muscle? Actin? Myosin. So you all must have learned in school biology, right? Actin, myosin. So this is a contractile apparatus. So they activate this myosin, and myosin myosin acts along with actin to lead to, which leads to contraction and relaxation. So this is mediated by the electrical activity slow waves and also the agonist from your glands. So you can see the different. So the calcium, it comes from there's an active calcium flux inside or outside the cell, and you also have the sarcoplasmic reticulum, which also regulates intracellular calcium concentration. And this calcium change in calcium concentration activates a protein. And this protein activates myosin, and this activation of myosin leads to contraction and relaxation. So this is called a cross-bridge cycle, which I'll be talking about in detail later on. So just to show you what is the biochemistry part of this contraction. Okay, so we have the electrical part, which is action potential, and we have the mechanical part, which is the contraction, where you measure the force. And in between these, we have this biochemistry part of signaling pathways. So these models were developed in my lab previously before I joined. So these models are, this is a electrical model showing the various ion channels on the smooth muscle cell. And this is also a cell, this is the interstitial cells of Cahar, and this is the smooth muscle cell. So it shows, this model shows the interaction between the interstitial cells of Cahar and smooth muscle cells. So these models predicted the electrical behavior or the electrical stimulus that is being transmitted in the stomach at various point of time scale. So my work was to convert these electrical signals through calcium transients to mechanical behavior. Our objective was to create a model which would predict the mechanical behavior in terms of force exerted by the smooth muscle cells in the stomach. So this is just a physiology textbook picture of your stomach. So it's just to show you how smooth muscle cells are arranged in the stomach. So this is your stomach, and if you rip it, this is your muscle structure, and you have the glands, and this is the muscularis mucosae, and you have different oblique muscle layer, circular muscle layer, longitudinal. So these layers, when the circular muscle layer contracts, the longitudinal muscle layer will relax, and this leads to a change in the size and also the motility pattern of your stomach. So this serosal region is rich in that pacemaker cells. So this is where the stimulus comes from. And you have interstitial cells of Cahar also in muscularis mucosa region. So that's where the electrical impulse for these smooth muscle cells arise. So breaking down, so from the big picture of GI system to cells to tissues to single smooth muscle cell. This is how a single smooth muscle cell is depicted in your textbook. And then this is how your intermediate filaments. So this is a relaxed, it's a cartoon pictured representation of how a relaxed smooth muscle looks and how a contracted smooth muscle looks. And what causes, when you look at the molecular level, so now we have moved from the organ system to organ to cellular level to tissue level to cellular level, and now we have moved on to the molecular part. So what is causing this cellular behavior is your molecular players, which are the myosin and the actin filaments. So it's just to wake you, I'm sorry, I will explain you this at a later point of time. So I would wake you people who are sleeping with this slide. Can anybody guess what I'm trying to say with this slide? I'm sorry if anybody is not familiar with this. What is the machine? Your professor asked what is a machine? Define machine. So can anybody define machine? Any version, the Vijay version or the other version? Can anybody? No, machine, every day we use so many machines, right? So can anybody define machine? What is a machine? Make life easier, okay? Any other definitions of a machine? To perform a mechanical action. So what kind of mechanical action? So something to move. Okay. Any other definitions of machine? Means? Okay. So we have various definitions for machines here. So I just want to life of a cell. dreaded biology. For some reason, I still can't figure out why. And I wanted to be a mechanical engineer because my dad was a mechanical engineer, and I was like, I grew up seeing machines and all these drilling machines and all machines at home and in the industry. So I always wanted to become a mechanical engineer. But you know how things are in India. So I ended up in biotechnology. So the closest to engineering biotechnology was this chemical engineering subject. So I always focus more on chemical engineering subjects like bioprocess and thermodynamics, and did the bare minimum required for the biology part. But still, I always enjoyed cell biology. But then when I came for my graduate studies in National University of Singapore, I happened to sit for a course in biomechanics because it was a compulsory course. And when I was given topics on biomechanics, something suddenly struck me at the perspective. I had never imagined cell biology from the perspective of mechanics. So that was like a great revelation for me. And I was like, I should have known this before. I would have studied cell biology better. So from then on, I focused more on biomechanics and mechanobiology. And though my work was more on mathematical modeling, we had an adjacent lab who did a lot of work on mechanobiology. So especially they were studying biomechanics of red blood cells during malarial pathogenesis. I thought I should give the graduates, I'm sure the graduate students and the professors already have perspective, and the undergraduate students need this kind of inspiration or perspective for you to think, because mechanobiology has changed the way people think in cell biology and biochemistry. There has been a great shift in biochemistry with the way the signaling cascades are seen. So with biomechanics giving in more details about the more dynamic processes, things are changing in cell biology. As she said, no more cells can be viewed as the simple diagrams in textbooks. They are more dynamic than we thought. And previously, one reason why I didn't like biology or cell biology was like, it's very hard to see things, right? It's always seeing things makes you believe and makes you inspires you and want to do more. For some reason, maybe my imagination capabilities were so limited or whatever. So seeing was very difficult in biology, at least in my time. But now the imaging has taken a huge, tremendous progress. So have you seen videos of cell division? So you have real-time frames of cell division happening from the formation of the centromeres and how the cell divides, and even the actin polymerization, the the tubulin form, the motor proteins moving. So you have, the imaging has pushed mechanobiology to great heights that you can actually see what is happening inside the cell. So I think this gives a more reason to love biology now. So after 30 years, I've started loving biology thanks to imaging techniques like electron microscopy and AFM. And yeah, so this course in this mechanobiology is an emerging topic, and we have various levels in mechanobiology. You have the molecular mechanics. It's a vast range of topics in mechanobiology. So you have, at the molecular level, you have single molecule mechanics, where you study the mechanical properties of a single protein or DNA, a single stranded DNA or a double stranded DNA molecule. You try to stretch them, you do stretching studies, you try to stretch them, pull them and play with them, and you try to figure out its mechanical properties. And then you have your cellular mechanics, where you have single cell mechanics, where you try to study the properties of single cell. What is its elasticity, what is the shear model. So you have various mechanical concepts applied at various levels of the biological systems. Then you have cellular processes, the addition, the migration, and the contraction. So these cellular processes play a very vital role in our physiological processes. So the biomechanics studies how these cellular processes are being carried out by these various cytoskeletal structures. And then we have this mechanotranslation. Mechanotranslation is also an emerging topic where, so we are all used to this biochemistry point of view, where you have biochemical signals, receptors, G proteins, and you have ligands sitting in the receptors. Mechanotranslation gives a mechanical perspective to the cell, where the stimulus is actually the mechanical stimulus. It's the force. The force is actually opening up a lot of ion channels. There are a lot of ion channels which are mechanosensitive. So a change in force experienced by the cell opens up a lot of these ion channels and lead to the same signaling cascade that you would imagine with a ligand sitting on a receptor. So mechanotranslation talks about how a cell experiences mechanical signals, how it senses mechanical signals, and how it responds to mechanical signals. So all this I will be talking about in mechanotranslation. And tissue mechanics and organ level mechanics is something that I would not be doing. So probably you would talk a little bit about the whole mechanics, right? So there are various concepts of mechanics that you will be hearing these words. So it's better you go refresh your basic knowledge in topics like what is a force, stress, strain, elasticity, viscoelasticity, shear modulus. I'm sure we've all heard these terms before, right? So it's good to refresh these topics again. So what is stress? What is strain? Viscoelasticity. Yeah, this is for the biology people. I'm sure the mechanical persons will be quite familiar with these topics. And then we have various disciplines of mechanics applied to biological systems. You have the solid mechanics, fluid mechanics, and statistical mechanics, then experimental and computational mechanics. These are the various disciplines of mechanics that are being applied to biological systems, and we're trying to build models of mechanical models of biological systems at various levels. And we have the tools and techniques that Dr. Delphine Dean will be doing in detail. So, as I said, the advances in experimental biology and biophysics have made this biomechanics possible. And we have optical traps. These are the earlier methods: optical traps, micropipette aspiration. Then you have the AFM. Then you have traction force microscopy. And from the experimental part, and we have computational modeling, finite element modeling, and we use continuum mechanics concepts to develop computational models. So these are the tools, various topics in mechanobiology. So tomorrow I'll be doing single molecule mechanics. So I will more focus on the motor proteins. So in motor proteins, we'll see. I'll discuss about how kinesin, myosin, dynein, and probably RNA polymerase carry out their motor activity. And then we'll also look at how, what is the mechanics of cellular polymers. What are the cellular polymers? They have the actin, intermediate filaments, and microtubules. So we'll see the properties of these cellular polymers and also cytoskeletal structures. So these are all at the molecular level. So we are still at the molecular level and we have not yet gone to the cellular level. So cellular level will be more of a continuum mechanics. So here we are focusing on single molecule level. So and cytoskeletal structures, various cytoskeletal structures. Then we have the cell membrane. So membrane mechanics by itself is a huge field. What is the properties of the cell membrane? So these are at the molecular level. Then we have the cell mechanics where this whole cell, instead of looking at molecular level, we would assume the cell to be a continuum, and we would try to apply principles of continuum mechanics to cell membrane and cytoskeletal structures and organelles, and look at what are the properties of cell. And then I would focus on cell processes, how addition, migration, and contraction takes place with the help of these different cytoskeletal structures. And then both in health and disease. In disease, we have cancer, where how the changes in properties of the cell makes it more metastatic and all that. So this is more from the biology point of view. And one example that I wanted to do today to just give you a basic idea of single cell mechanics is single cell micropipette aspiration. I personally have not done these experiments during my research, but during one of the summer schools we happened to play around with micropipette aspiration, where we try to suck in one single cell in a pipette. You change the pressure and you try to suck in a cell. You give little bit pressure and you see how much the cell gets sucked into the pipette, and you try to, with applying Laplace law, you try to figure out what is the shear modulus or elasticity of the cell. So this is a very basic experimental technique that could be used to find out what is the elasticity or what is the deformability of a single cell. So this single cell micropipette aspiration was used in studying malarial pathogenesis in RBCs. So you must be knowing RBCs. What shape are RBCs? What gives it that shape? Why is it different from other cells? Absence of? Any other reason why the RBCs have to be in that shape? So, and this is an optical trap image of a red blood cell, healthy RBC and a parasite infected RBC, where they try to, so you have an optical trap, yeah. So tomorrow she'll be doing optical trap. So basically we try to trap objects between two light beams, and we try to find out, we try to stretch and we try to find out what are the properties of these objects that we have trapped within the light beams. So here they have trapped a single RBCs, infected RBC and a healthy RBC, and they have tried to find out what are how the properties have changed during malarial pathogenicity. So during malarial pathogenicity, the cells become more stiffer. Due to the proteins from the malarial parasites, the cells become more stiffer and they become more sticky also. So they become more sticky and more stiffer than the healthy RBCs, and they lead to a whole range of pathogenesis in malaria. And this is an electron microscopic image of a neutrophil. So what is the function of a neutrophil? First line of, it's an immune cell. It has to move. It has to move, right? It has to move to the site of infection. It has to squeeze through cellular layers which have a diameter less than its own size. So for that, when the micropipette aspiration was done on neutrophils, they seem to behave like a liquid drop. So when the pressure was applied and tried, and it behaved like it was, entire cell was sucked into the pipette. So it behaved more like a liquid drop. And what causes this type of behavior is the way the cellular membrane has lot of ruffles on its surface, which gives it a more surface area for it to expand, because the volume is fixed. The volume is fixed, so when it squeezes, it has to expand itself and squeeze through the cellular layers. So this type of ruffles on this neutrophil surface gives it an advantage to squeeze through cellular layers and move to distant places to the site of infection. So these are some very basic micropipette aspiration techniques that was conducted on cells to find out how elastic or how deformable these cells are. So the last one I'll be doing is a mechanotranscription. As I told you, it's an emerging paradigm in biochemistry and cell function. So mechanotranscription primarily focuses on mechanical signals. What are the different kinds of mechanical signals in terms of force experienced by the cell, and how a cell senses this mechanical signals, and how these mechanical signals play a role in regulation of the cell function in both physiology and pathophysiology. So I like this picture of the IUPS project. Yeah. Any questions? So this is just an overview. So from tomorrow, I'll talk in detail about the motor proteins. From the point of function, so it all leads to structure function relationship, right? Skin cells. Skin cells. Skin cells? Muscular?
No.
So we should go with the other side. Which cells are the stiffest? Okay, then there's one cell that's the stiffest in the human body anyway. Nope. No, so bone itself is stiff, right? Bone has mineral, but bone cells are living on this very stiff thing.
think about the function of a cell. It's muscle. There's one kind of muscle cell that's cardiac muscle cells. Or I think like your average cell there is like 1 kilopascal or some really cardiac muscle cells like 100 kilopascals. Like, so they're just adult. What cardiac muscle cell we have is like you take them out and they stay in the shape because they are so.
Cardiac myocytes are now very, they don't fit in skeletal or
No.
they're altogether different type myocytes.
So back to that question of the soft tissue. So that's one end.
RBCs usually do not have gap junctions. They shouldn't have gap junctions. The other cells should have gap junctions so that they can interact with each other. In case of when there's a malarial infection, will the cells develop gap junctions with each other gladly?
No, they don't develop gap junctions. They just, because of these parasitic proteins on the cell membrane, they become more stiffer and there's a change in shape and they become more sticky. Sticky in the sense there's another infected RBC could interact with this already infected RBC and they try to form like a.
Do the cells interact with each other inside?
No, because the cells are flowing, right? It's not a static. The cells are flowing, so it sticks to the wall. It doesn't move like a healthy RBC. It sticks to the wall of the blood vessel and it attracts more infected RBCs. So it's like a cascade effect. So they become a huge ball and they just clog the blood vessel.
So tight junction and gap junction are only for the attached cells. It is an interaction between cell to cell.
Yeah.
Whereas blood cells are always moving, so
Yeah.
they won't have
Yeah.
any junctions.
Yeah.
So the glycocations, it has more of stearic acid. So given those concentrations, stearic acid are positively charged, so that basic charge repulsion is also lost. So
I'm not sure about it. Yes. Yeah. We'll talk about that one.
Why should cardiac muscle cells be stiff? Because it has to contract and relax. What function does it?
So it's contracting and relaxing and it's making up, if you think about your heart, there's very little, well, that's not true. There's extracellular matrix around the cells, but for the most part, it's mostly cells. So most of the mechanical properties of your tissue, that's all the cells. If you look at something like bone, the cells are in there producing the tissue matrix and making the structure, but most of the mechanical property of the tissue is from the matrix, so from the bone. The contractile apparatus for the cardiac muscle, because it has to pump huge amounts of fluid, is, so as I said, if you look inside the cell, it's packed full of active myosin, very highly arranged to get that, to be able to generate that amount of force. Yeah.
So ECM plays a major role in designing the properties of the tissue. So that's the challenge in scaling up. So here, so I remember the slide I talked about scaling up. So when you see at the protein level, you can take a protein and play around with it. And when you see when it comes to cell, it interacts with a whole range of other proteins. And then when you take a tissue, the cell is not by itself. It has a matrix around it. So the properties of the matrix also influence the properties of the cell. So when you go from a cell model to a tissue model, so you have to sometimes it happens that what we've done at the cellular level is it doesn't matter at the tissue level. So you have to start again from the beginning. Like you take huge blocks of tissues and you try to apply continuum mechanics and do some finite element modeling. But nevertheless, at every level you have some interesting things coming out of this mechanical studies. So cancer is a very classic example of how changes in cellular properties and ECM gives it an advantage for it to migrate, adhere, and also propagate. Yeah. So there's like the cancer. In cancer, the signaling cascade goes haywire, right? So it also leads to a range of extracellular matrix proteins being produced, and these cells become more migratory,
become more elastic, they try to proliferate, they try to spread, and at the final stage when they want to metastasize, they can actually move from the dislodge from the extracellular matrix and travel to great distances and cause your secondary tumor. They can actually travel, squeeze through this and land in the design knee protective gears or some implants that will help in soldiers landing and having less impact. So all this comes from studies of bone mechanics. So you have this gait lab where you try to do walking and try to measure the force experience at various joints, and you have these bone pieces where we have hammering. We have a bone piece we try to hammer, and we try to put that bone into like various range of forces and try to see at what force it cracks and all that. And you try to study the material properties, and then once you have it, then you try to find out the best material that could mimic. So it's like mostly of biomimicry, right? So that's where biomechanics actually comes. So for you to have an implant, you have to know what actually what will be the amount of force that implant will be experiencing within a body has to be understood. So that's why the bone mechanics is also very growing field, because you have these every day you have new materials coming up for these implants that would bear the forces that our bone experiences.
If you don't match them well, you get stress concentrations where the implant material and the native tissue are, and then in response, because of mechanobiology, the cells typically will break down the native tissue, so you'll end up with the implant. So it's very important.
But the conditions when the bone is inside a body and when it is outside, the conditions changes now. How they tackle with that condition?
Yeah, I'll talk about that. But yeah. So that's actually one of the things when you read papers. So when you read papers, particularly on smaller scale mechanical measurements, because larger scale mechanical measurements, they've been around for a long time, so there's like common accepted ways of doing the test that mimic the right thing. But at the smaller scale, it's difficult, and so you should read the paper and the protocol to see how they did it. For instance, with bone, you take bone out and you do your test. If you drive the bone, if you got it from a cadaver, so it had to get frozen to where you are, right? All those things will affect the properties that you measure. So it's important to be able to keep that in mind. Temperature actually is one. A lot of the cell mechanics studies were initially done more at room temperature because it's easy, right? We have the cells in the incubator, you take them out, you do your test, and you don't pay attention to the temperature. But recent work has shown that a lot of cells are actually fairly temperature sensitive, and a lot of the polymers that make up the cytoskeleton of the cell will also change with temperature. And so the properties you measure at more like room temperature might not be the same as what you measure physiologically. So yeah, it's a balance. I think one of the issues with the smaller scale measurements for that is if you think about, let's say the red blood cell, right? It's in the blood with all these other proteins, and from a nanomechanics point of view, all these other proteins are very sticky, and they make a very big mess. And so it's much easier to take the cell out, put it in a nice buffer where there's no other proteins that make those measurements, but you have to think about how that affects the actual cell. So it's a balance.
So I think one of the ways they're trying to address this is they have this microchannels. So where they're trying to replicate
the blood vessel in micro channels. Yeah, and it's like a micro channel on a chip.
Yeah, micro channel on a chip. So where you try to have like a RBC and you have the same kind of environment mimicked for an RBC and the same study. So yeah, in micropipette aspiration you have a single RBC and you're trying to suck in, or in optical lab you're having a single cell and you're trying to play around with it. Probably it will not tell you what exactly is happening within the blood vessels. So then we have this advanced techniques where you have micro channels etched on a chip and you try to create the hemodynamic forces, because the same RBCs are in continuous drag, right? So all these drag and all these the blood hemodynamic forces also play a role in how these RBCs change or the properties are influenced. So you're trying to mimic the same what's happening in your blood vessel on this chip. So those studies are also being done.
I think you're always limiting things when you're doing, especially experiments, but even a computational model, right? You can't model everything, otherwise it would be a model. But it could, in the case of the red blood cell with malaria, the differences in mechanical properties that you measure on a healthy one and an infected cell are, I think, like 2 orders of magnitude. So, you know, yes, they change with the different environment, but we're talking huge differences between the two. So we're pretty confident that that still happens in the body.
So when they are working with the bone model or any other model, they will mimic the simulated body fluid condition. If it is with pacemaker or something, they will simulate the blood conditions. If it is with the bone forming cells, they will mimic alkaline environment or a calcium-rich environment. So they will artificially study the load bearing property. Suppose if the implant is with the dental or the hip and the knee joints, then they will give extensive load because that only bears all the body. Suppose if it is with the heart models, then they will give the load similar to the heart pressure. Similar to the tires, they identify the wear and tear, how long it works. They will work all the conditions similar to the body condition in the artificial strength. Then only they will move on to the innovators.
Based on that, only they will select the material from
Yeah.
what is it?
Heart is one of the most widely modeled organ. Yeah, that's for the immunologist too. I know.
We talk about inner material that is.
Yes, so that's
should be
another one, biomaterials and immunology. So where we have trying to have materials as biocompatible. Yeah.
So, well, it's inert is like the traditional way of doing implants. It's kind of like you have your pan and you're making an egg and you want a pan where the egg doesn't stick, right? So Teflon, the egg doesn't stick. So there was a lot of work trying to make inert materials so that proteins and cells don't stick to it, so they don't have an immune response. I think a lot of more modern approaches have been making a more like biocompatible, bioactive. So like hip implants and all those now have the stem where it goes into the bone has materials on the outside that promote bone growth so that your bone then grows back into the bottom part of the hip implant and holds it in place. But that has actually been, I'd say, like the last 20 years, a big shift.
Ma'am, morning we had a discussion about how the tumor cells are different from the normal cells, and you said that the tumor cells are a lot stiffer than the normal cells, and that's also used to differentiate the cells. So if the cells are very stiff, and then how are they able to squeeze through the tissues and reach the...
So the cells in the tumor are stiff. This metastasized cells, the cells that actually migrate, are very, very soft. So there's a huge transition that occurs when the cell goes from being a kind of a tumor cell that stays where it goes into a migratory cell. And there's actually a lot of work looking at how that transition happens. There's actually people trying drugs now to prevent that transition from happening so that you don't get metastasis, you have the tumor stay where it is. So yeah, that's...
that they will study epithelial mesothelial transition. Then the cells are attached to cells, they will be stiff and they are epithelial in origin. When it is metastasizing, automatically it transitions to the mesothelial origin, where it loosens the hardness and then it is very soft so that, as Madam said, it will move.
Yeah, the way it escapes the ECM matrix is like very good. That they try to develop these structures, philopodia and all those structures.
similar to in that video at the end where this
Yeah.
is into.
Yeah, the last part of the video is the cell spreading and the squeeze. Has to dislodge itself from the ECM matrix.
But that transition and the other direction happens in cancer, but it also happens, in development and with our cells as they differentiate, right? You have stem cells. Stem cells typically are very soft because they don't really have structure because they're, nothing yet. And then as they transition into whatever their final cell type is, there's a huge change in the mechanical properties typically, and also a huge change in the organization inside the cell. So some of the mechanobiology work has been recently trying to understand how mechanics play a role on that transition for differentiation purposes, for a wide range of just understanding development to also repair tissues when you get
Ma'am, if you know the mechanics of everything inside the body, can you control over it by non-invasive method?
Can you control it by?
By non-invasive method.
Not invasive.
Method, yeah.
You mean assess it?
Example means like example that is snake is bite to us. I want to paste that. You can take example nano paste or nano something. What is this thing?
Right.
Paste the thing. Then that will coagulation that poisons at the time only, at the spot only. That you cannot go within the part of the body.
Right.
So if you know the mechanics inside, why not use it outside?
So we can. So I think maybe I'm not understanding. I feel like we can do that. So yeah, sorry.
No, you said if you know the mechanical stimulus inside,
The body.
can
Can
you
you use
control?
that concept to control over that mechanics by outside?
That is what we're trying to.
Yeah. So there's been some work on that in terms of like how to use that for therapy. I think actually bone repair is one area where people have actually done that, where they stimulate with various stimulus to try to improve bone. It has changed actual therapy for a lot of orthopedic, how to treat orthopedic injuries and disease. If you ask probably even your parents, growing up, people were always told like, break something, you've got osteoporosis, the solution is to not move, right? Because you don't want to break it more. Modern medicine, that's not what the solution is, right? In modern medicine, you're supposed to move on it and increase and add mechanical stimuli because that has been shown to improve the growth. So I think it takes time. There's a lot of ultrasound techniques now being used to internally apply mechanical load at different spots for treatment and other things as well. But those are not all in the market yet. But yeah, people are trying.
So with the GI, so hypercontractibility is a problem with GI. So the GERD that I talked about, gastroesophageal reflex disease. So one way they try to control the hypercontractibility is by giving ion channel blockers. So you have this proton pump inhibitors which try to inhibit these proton ion channels and thereby reduce the contraction in your smooth muscle cell.
The problem with a lot of those types of things is it's hard to get targeted delivery, right? So if you give a drug or something like that to stop some of the contractions one place, the problem is a lot of times it goes all over, so you might have side effects.
Non-stick.
Yeah.
Did we answer your question?
Yeah. When we discuss about that stomach 3 hour food is going there is good. Because I'm not from biology part, that's why I'm not explaining that. So this time is different on what? Deep on the quantity or deep on the micro things what is going on, just like states you discuss about mechanics of the stomach.
So the time together the 3 hours is for the stomach to, the stomach is like a bag, so it is
No, the time is for what? Why the time is fixed 3 hours?
It's not fixed 3 hours. It's roughly 3 hours because the cycle at which the contraction is 3 cycles per minute in the stomach. Whereas in intestine it's 11 cycles per minute, and in small intestine it's 13 cycles per minute. The
basic contractions, and in large intestine it's around 11 cycles per minute. So this is the, so you know, why does the heart pump, why do you have so much of heartbeats? Yeah, it's 160. What fixes this number of heartbeats?
Because my question, the first question why I am saying that, because we know that if there is more cell aging, then our aging will be very less. So if you control the if you know the mechanics of cell, why need to control the mechanics of cell outside?
Yeah, that's a problem because specific targeting is always a problem because the signal comes from various places here. So the brain sends its neurotransmitter, the acetylcholine from the brain comes in, then you have this pancreatic duct pumping in all the juices, and then you have your glands sending your agonists and antagonists, then you have your pacemaker cells which are working at a particular speed. So there are so many things. So that's the complexity of the biological system. So you don't know exactly which one to target.
If you make a fixed one, can you do that?
If
you make a fixed program, can you fixed program? Is the example that what I can make example?
Yeah, so because this, for example, the altered smooth muscle contractility, we know the smooth muscle contraction is altered, but we don't know what is the reason. Probably sometimes the electrical signal might be all fine. So you have this EGG, like ECG, you have the EGG. That's the challenge in digestive diseases because it's very hard to diagnose. You have ECG, which gives beautiful signals where you can say the heart is working fine or not, but you can't get good ECG signals because your ECG signals hinder with your ECG signals, so you don't get them. So it's very difficult to diagnose what is the problem. So if you don't know at which level is the problem, is it the electrical impulse that's going wrong, or is it the mechanical behavior that is going wrong, or is it something in between them, the signaling cascade that is going wrong, or is it something, the neurotransmitter, or is it the nervous system that's going wrong? So it's very difficult to, and many a time it's not a single,
yeah, I was going to say, there in biology, as an engineer, right, I came into biology things thinking like you, like excellent, we have a model, I know what it is, we're going to change it. That's not how biology works, right? It's very dynamic.
My thing is that what do we have, we know that. What we don't have, we don't know. That my question is that.
No, actually, it's not like physics or chemistry or like engineering. Biology or body physics. Suppose I know how exactly my GA is working. If I have a plastic that can inhibit particular other side you will get a kidney pain, or other side you will get a liver pain, or other organ, anything may affect. So you have to control each and everything. So I can't design a particular drug that will work only on a particular organ. That doesn't have any side effect. So it's all complicated. You can't control one thing in your body.
But I think that's the aim of
Another one is once it occurs, it's very difficult to cure. Because I have an experience with one of my friends got into a problem where his intestine is start moving, contracting. It's a very critical condition in fact. He has to be admitted, all his intestinal content has to be removed, and he was under medication for 2 years. Till now they are not able to find out what is the reason.
I will give you another example.
It's a very multi-dimensional process.
Yeah, but the ultimate aim of any therapy would be what you are trying to say.
Yeah, that's the goal.
That's the goal. That's the ideal goal. But it's very hard. I think you have to.
See, for example, 5 years I was getting a hot infection, ear pain, everything from childhood onwards. So I will take antibiotics. Doctors will give me antibiotics. So now I have a kidney pain. You understand? This is the bad effect of I'm not saying science. It's a half knowledge. I took an antibiotic because of hot infection and everything. Other side I got a kidney pain. So everything is connected, but it's not a symbol like of physics like you send a ball and go and
that's why I said, if you control by non-invasive method, you are not control. No, that I'm asking because mechanics is
Understanding things is the best way to control. That is, all these approaches are to understand.
Yeah.
Science is first you have to understand, then only you can model it.
Yes. But I mean, I do think that it has led to therapies, is my point, is that some of the basic science stuff that's been done on biomechanics and small scale things has now started to translate to targeted therapeutic approaches. It's just the ones that work are in very specific cases where you don't end up with as many of these side effects. Like fatigue. There's been some really cool developments on new materials for dental implants
bones in general like get harder stronger, but a lot of tissues actually get like very sick. Yeah, so that
about today is atomic force microscopy as a imaging tool. With my, I made a terrible bad AFM joke. It's scratching the surface of nanoscale imaging, and you'll see why in a second. But the movie we saw of the atom and his atome was made using scanning tumbling microscopy and then imaged using AFM. So that's the technique they used. So the atomic force microscopy was invented in 1986 by Vinnie Quick-Gerber over at IBM. And the basic idea is pretty simple. It uses a very sharp tip probe to image the surface. So you get your tip and you scan along the surface. And as the tip goes over the surface, if it has topography, it will move up and down. And that's what we measure, which means it works just like a record player. For all the young people, records are this thing that work like an AFM to make music. So if you've ever seen a record, right, they have grooves, and then you have a little needle that goes on top of the record, and as the needle goes on, as the record moves, the needle will move up and down with the grooves on the record, and that's what produces the music. So same idea with an AFM, it's just a much smaller needle, looking at much smaller bumps and grooves, but the basic principle is pretty much the same. You can image everything from close to atomic resolution, so AFM can image atomic lattices, like crystalline materials. There are tricks to make AFM actually image down to the resolution now close to TEM, but it's not quite TEM level, but getting there. To things on the size of cells, so you can kind of see the size range it can image. So the resolution is quite good. The scanning size is at most about 100 by 100 micron. And people use it to image all sorts of stuff. So these are chicken printed. This is really cool. Since we're talking about nanomechanics, this is from a microorganism called Forticella. It has a stalk with like a little spring mechanism, and so the head part of the microbe grabs things and pulls it back with this spring, which is to scale the strongest spring we know. So this is that structure. This again is a cartilage aggregan, which is a very cool molecule that I did all my graduate work on. It has a protein backbone, and then a lot of glycosylated glycan, highly charged sugar side chains. So it can image lots of things, big molecules, small molecules, all the way up to, cells. You can also use it in different modes, which we'll talk about with imaging, to image not just the topography of a surface, but also properties of that surface with the topography. So in this image, I like this image because it's a read-write head from a computer, the hard drive. And if you look at the topography, it looks pretty good. But if you look at the magnetic field, you can see the magnetic field isn't uniform through the gap. So this is a read-write head with a defect in it. AFM imaging is imaging topography. So because you have that needle going up and down over the surface, you actually can measure topography. So if you remember SEM, the pictures look like, you kind of get a 3D head perspective, but really to get the topography in SEM, you have to take pictures at lots of angles and then reconstruct. With AFM, because I'm scanning, across and my tip is moving up and down, that's what I'm actually measuring, is how bumpy the surface is. You can use it to measure nanoscale forces, which we'll talk about, obviously, but also it can be used to image all sorts of other properties of your sample, depending on the tip you use. So that's the big thing with AFM. The tip you use for scanning and imaging and probing determines the things you can do with it. So you can measure magnetic, electric fields, compliance, chemical affinity, all sorts of stuff. But you just have to pick the right tip. These are the two AFMs we have in my department, just so you can see what they look like. This is the one I typically use in the lab. This is the AFM right here, and that's a regular optical microscope, just so you get a sense of the scale. So whereas an electron microscope is like a room-sized instrument, AFM, pretty small. Back in grad school, when my first paper got published, they did some press about it. So the press came, and they wanted to take a picture next to the atomic force microscope, and they were very excited. And they showed up, and we're in the lab, and we're like, there it is! And the press people were like, that is not very exciting. So they're like, how about you stand next to this microscope? And we're like, that's just an optical microscope. And they're like, no, but it looks so much better. So, the AFM I used in grad school looked like, this one looks like a toaster. The other one kind of looks like a bagel holder. It's not this big. So, a little thing about, since we talked about electron microscopes and imaging, how does AFM compare? So the advantages of AFM is, compared to electron microscopy, it's a relatively cheap technique. You can get an AFM now for about $20,000. So kind of in the same price range as a nice optical microscope. The really nice AFMs can go to maybe like $200,000. So it's the same price range as optical microscope and confocal microscopes, which is a lot cheaper than electron microscopy. It's very high resolution, so you get topography as you're imaging. It can be done in fluid, in air. You don't need to fix things, and you don't need to have a vacuum. So for biological samples, it's very nice because I can actually image in fluid. Now, the big disadvantages of AFM compared to electron microscopes, the first one is you have the limited scan size. So this kind of thing, which you see all the time with electron microscopes, like this is a pinhead, and then they zoomed in on the pinhead, and they got like, oh look, there's bacteria on the pinhead. It's very hard to do with AFM. Like, the AFM, you're limited to 100 by 100 micron scan size and smaller, and so usually you have an accompanying optical technique to try to put your probe near this area you want to do and then scan. But you can't just take the AFM and you do a huge scan and keep zooming in like you do with SEM. Compared to electron microscopy and optical imaging, it's relatively slow because the way it works is basically I have this tip that's scanning across, and I can only scan so fast. And I'll show you a demo. The higher resolution imaging I want to do, typically you want to scan really slow. So to get really nice images can sometimes take a minute or two or longer to do a really nice scan. There are newer techniques that we have tricks to make it fast scanning, but in general, because it's mechanically scanning the surface, it's not going to be instantaneous. And you're doing the scanning with these microfabricated tips. And so they're fragile. And if your sample is really bumpy and you didn't plan for it and you have a very soft tip, you're scanning across and then you get in a big hole and then you move and you're going to break the tip off. So there's tricks to getting around that. And then how to pick your tips is always kind of a trick. But every technique has its advantages and disadvantages. I don't know what happened. Anyway, so I had.
measuring something as it's moving up and down. I want to measure something on the nanometer scale. I can't actually move my tip with a gear, right? If you think about it, gears have a size limit, so a standard motor won't work. So what you end up using is piezoelectric materials. So piezoelectric materials are crystalline materials that if you deform them, they produce a voltage change, or if you apply a voltage, it will deform the material. So lots of materials are piezoelectric. Quartz is a famous one, so if you have a fancy quartz watch, it's because there's a little piece of quartz in there, and if I send a little electrical ping, it will vibrate at a resonance frequency, and that's what I'm using in the watch. Certain ceramics are piezoelectric, which is what's used in most AFM applications. Polymers, even bone, lots of things are piezoelectric. And the nice thing with piezoelectric materials is this happens very precisely. So if I have a material and I put my voltage across it, I know exactly to within an angstrom how much it's going to stretch. And so this basically gives me an actuator that has the resolution I need in order to make the measurements I want. So not just AFM, but a lot of nano manipulating techniques, high resolution precision pressure sensors, all those things use piezoelectric materials. That's the most expensive part in an AFM. They're not, as I said, they're not that expensive. But I will tell you, if you're building an AFM from scratch, that's the most expensive part. And the ones where they sell you the AFM for $20,000, I think if I were to buy all the parts and make it myself, probably that would cost around that. So that's the cost of anything. It's also why you shouldn't take the AFM and drop it, because for materials, mechanical people, ceramics are brittle and they will break. So don't drop the AFM. So this is actually the setup for an AFM. So here's the cantilever with the tiny sharp tip. Here's a blow up of the tip so you can see. This is a standard imaging tip. This one has a resolution of about a nanometer. If you look at the very tippy tip of the end of it, it's about that big. So as I scan the cantilever across my sample, the deflection of the cantilever is measured by a laser. So I get a laser, I bounce it off the back into a mirror, into a position sensor. So if the cantilever deflects up, then this spot is going to move up, and I can record it. And then what happens is you get a feedback loop. So it records that the cantilever moves up, and then it moves the piezo actuator in response. So how does the piezo actuator actually work? Most of them use what's called a piezoelectric tube, which is cool, which is why I put it there. You pick those. You basically have a tube, so if I put a voltage from this end to that end, it's going to stretch in the Z direction. If I put a voltage from here to here, it's kind of going to sweep this way in the Y direction. And then if I put a voltage kind of from the front to the back in the screen, it's going to move in this other direction. So that's how most AFMs are made, because the nice thing is you just need one piezoelectric component. The disadvantage of this version is if you do particularly larger scans, so closer to 100 microns, if you look at the X and Y direction, it's not actually stretching this way, it's kind of tilting back and forth. And so instead of having a flat scan, it'll kind of make your sample look like it has a bow to it, right? So some AFMs have kind of started going around this. This is a different one. But that's, again, something you need to know. If you do AFM and you're doing very large scan sizes, you get some artifacts with how the AFM is doing the scan. But most of the time, I'd say people tend to image more in the 20 microns and lower, and so this isn't as much of an issue. Okay, so in basic imaging mode, it's called contact mode because the tip is in contact with your surface. It's very, very original naming. But the principle of contact mode imaging is I bring my tip down, it's going to deflect, and then I'm going to image and try to maintain the deflection
deflection of the tip constant. So what does that give you? That means that as I'm imaging, I'm pushing on my sample with the same force. If I didn't do that, right, and I'm pushing and I'm deflecting this amount, and then I come here and now the tip is deflecting more, I'm actually pushing harder on this than it was on the sample here. So what the AFM does is, okay, I'm coming, I scan, and then I get, it deflects a little bit, so now the piezo actuator is going to stretch up, so now my cantilever is still at the same angle. Keep scanning. So that is the feedback loop that's shown over here. And that's also why if you want to do higher resolution scans, you tend to usually image slower because there's more time for that feedback to happen, so you're doing a better job of following the surface. If I try to scan really fast, the tip's going to deflect up and then the piezo doesn't have time to move before I'm on my next one. So I have a little demo, which I think I'll, hold on. So a couple things to keep in mind. So here's it's a cute one-dimensional, two-dimensional AFM model. So right now the tip, you can see there's the cantilever, there's the tip, here's my laser beam that's coming down, and this is the position of the laser on the photodetector. And then at the bottom it has a gain factor and a scan speed. And then now I can bring my sample closer to my tip. So here, this is what I would get if I was not actually doing constant force imaging, right? So now you can see all the motion is happening with the cantilever, and here I'm pushing really hard, and here I'm pushing much less. So if I have a sample, I might scratch things and things like that. So what we do with AFM instead is, here we go, do add some feedback. So now you can see, if you look at my AFM cantilever, right, it's barely moving, and in response to any motion, the piezoelectric actuator is moving up and down. So when I actually get my image, the height in the topography image is coming from the motion of the piezo, and then any motion that happens on the cantilever is kind of an error signal. Now, this is a really nice demo because I think for understanding what are the tricky bits of imaging with AFM, right now it's imaging slowly. If I try to, I'm lazy and I want it to go faster, let's say I'm imaging really fast, you can see I'm no longer tracking the surface really good, right? The AFM tip is moving, so I'm not actually doing a good job. You're like, okay, well that's okay. And then in that case, I'm not imaging, I'm not tracking, I'm just gonna bring my gains up. This is what happens when your gains are too high. So this happens with many imaging techniques and things like that have scanning things, right? You have a feedback loop. If you put the gains too high on the feedback loop, you'll have unstable feedback, and you'll get vibrations like this. So just something to keep in mind when you're imaging. And then, so if your feedback gain is too high, what you'll notice, first of all, if it's really too high and you're sitting in the imaging room, you'll hear it because it'll vibrate and make a terrible buzzing sound. But even if you don't, you'll see it on the image because you can see it's a very high frequency. So when it returns the image, you'll see like very high frequency components that aren't on your sample. Yeah, and then the other parameter I didn't show, but you can always change also the reference, which is where on the photodetector I I make it really low, then I'm barely touching the sample as I'm imaging. So one of the issues that I brought up at the end of last lecture with AFM is because you have a tip that is scanning along, if you're doing contact imaging and you're imaging at really high force, you can actually scratch the surface, which is actually something we do experimentally sometimes. So let's say I have a polymer layer and I want to know how thick the polymer layer is. I can make a little 1 micron box, image really, really hard and scratch it off, and then see what the height difference is from the surrounding area. So I see a nice little scratch off box. Other questions? So that's like the basic idea of how it works. So this is the actual data, what it looks like. So this is a collagen gel that I imaged in air. This is the height data, so that's the piezo motion that shows you how, like, here is really low, here's a very high point, there's a 100 nanometer height difference across the sample. And this is the deflection signal, which is my error signal. So it's how much the tip moved as it was scanning. Now, what you can see is the deflection signal. So first of all, you can see it was scanning, I was collecting the data. I'm scanning back this way because here is light color and the dark color, so it's going up and down. But you can see sometimes a little bit more of the detail in X and Y on the deflection image. But if you're trying to actually measure topography, you should look at the height. If you look at the height, it's a topography. So this is what the topography of my sample is, right? It's a three-dimensional map. So in this particular image, you can see collagen. You can see how thick the collagen fibers are. You can see banding of the collagen, right? It has a repeat pattern because it's a triple helical molecule. And you can see in this particular sample, there's no orientation of collagen fibers. This particular study, we were trying to make orientate collagen, so this was a control sample. Now the nice thing with AFM is I said we can do this in air or fluid, so what we had done in this study is actually image it in air, added fluid, see how it swells, and see if the geometry changes in water. So there's a couple artifacts if you're ever doing AFM imaging. The first one is piezo creep. So as my actuator is warming up, piezoelectric materials, as I said, if you put a voltage, it will change, it will move in response very precisely, but it needs a little warm-up time. So this is an example where at the beginning of my scan, the piezo actuator isn't quite warmed up. By the end, it warms up, but so instead of moving, I think this is 100 microns. I don't remember if you write it down. But instead of moving the full 100 microns at the beginning, it only moved, 95 microns or something. And so as it warms up, it actually can move the whole image. So a nice thing with AFM, if you're doing some imaging, make sure the instrument is warmed up before you actually collect the data. The other thing that can happen is you have your sample and it's fixed, and then you're imaging. Make sure, and this is true for a lot of imaging technique, make sure your sample is stuck to whatever it is, because if I'm imaging and I'm scanning and it's not stuck and it moves with the tip, I'm going to get something similar also. So you'll get the sample moving with the tip, which is not what we want. So that's basics of AFM. Are there questions? Just how it works, right? So it's fundamentally not that complicated. It's a little tip, and I drag it across my surface and I measure the topography. So I was going to ask, if I want to do really high resolution, what is something I can change? You got the slide, so it probably says on the slide. Yes, so you can change the speed. That tends to change a little bit the resolution because I can't track the surface as well, but it also changes the sensitivity. But if I really, truly, fundamentally want to change the resolution, what's the thing that determines the resolution of my image? The tip, yeah, the diameter. So the more sharp and pointy the tip is, the smaller the thing I'm going to image, right? So it can fit into smaller groups. another issue. So when my laser moves, right, that's what gives me the signal to actually do the topography. One of the biggest things I can do to improve my images is make sure the laser is at the end of the cantilever, right? Because right now, where it is like right here, if my tip moves up, it only moves a little tiny bit, and so it's hard to measure that change. So if you put the laser at the very end of the cantilever arm, right, I get better sensitivity on the motion of the cantilever itself. So, and then there's lots of artifacts that happen. So what are some things you can do? So what do you think is going to cause noise and issue in your sample when you're imaging? So I have a little tip, it's scanning, and I'm getting nano stuff. What was a noise and artifact issue in electron microscopy? Any small scale imaging, what's the problem?
When there are vibrations next to it.
Yes, when it vibrates, right? If I'm like, if you're trying to image over here and I'm like, what do you think I'm going to measure? I'm going to measure the cantilever doing, right? So you need to isolate the instrument. Now, unlike SEM, which is huge, AFM, as you saw, is really small. So typically you put the AFM in a vibration isolation chamber on an air table, something like that to buffer the vibrations. If you want to do a good job, you again typically put it on the first floor, ground floor of the building, as opposed to up. In our building, actually, we used to get lovely images, but they're doing construction on the building next to our building. So if you really want high resolution images on our AFM right now, you go after 5 p.m. because the construction stops. So yeah. So that's the basic things on the AFM. Now there's a couple other imaging techniques that are very important for bio things. So one of the problems with the standard contact mode imaging is I'm actually touching my sample and moving along, right? So I could scratch and damage my sample. It's a problem with biological things that are soft and squishy, like how am I measuring? The solution most people do is called intermittent or tapping mode. So instead of scanning and touching my sample the whole way through, I'm going to vibrate the cantilever near its resonant frequency, right? So I have a cantilever arm, I'm going to set it vibrating. And then as I bring my sample close, so I'm going to tap. And then as I come, I'm going to try to maintain the amplitude of the vibration on the cantilever constant. So what that means is every time I tap, I'm going to tap with the same amount of force, right? If I had a bump here and I'm vibrating and it comes, it's going to suddenly have smaller amplitude. So I'm going to move the piezo and then it goes back to vibrating at the same amplitude. So that's tapping mode or intermittent mode. It's the same idea. There's a feedback, but the difference is you vibrate the cantilever, and so you only touch the sample intermittently, and you're never dragging across the sample. Most of the very, very high resolution images in air are done with this type of technique. That's how, this is my friend Laurel image, this molecule, that's how they got this image. It gives you beautiful images of things, typically in air, but unlike electron microscopy, it's just room temperature air, right? It doesn't need to be, again, dried out and everything. So you do get slightly more physiological, relevant images. So here in this image, they used, this particular study used the image to look at the structure of cartilage aggregate. So you've got the contour length, you've got how long this molecule is, the protein, how long the little side chains are, and then also whether they're stretched out or shortened together. So in this particular study, this is bovine fetal aggregate, so baby cow aggregate. This is bovine mature aggregate, so this is adult cow aggregate. And you can see the molecule itself, the contour length from the top to the bottom is about the same, but the side chains look a lot shorter. Now, the interesting thing with this particular study is we know the chemical structure, so we know what the side chains are, and we know they're the same number of sugars. These are glycosaminoglycan side chains, so there are lots of sugars in a row, and we know there's about 40 of them in both the mature and in the baby one. So why is the size different? Well, the sugar chains on the adult one have a little bit less sulfate groups, so they have less charged groups, so they're able to curl back on themselves more because they don't have that repulsive force that the fetal aggregate does, right? So if you have charged sulfate groups interacting with each other, they're all negatively charged, they're going to try to repel, and they're going to stick out straight more than the adult one. Unfortunately for all of us, we're all in this case, that means your cartilage is not as good at being a shock absorber now than it was when you were a kid, but that's something we were interested in looking at. So that's kind of imaging, but why does it matter for mechanics? And the lovely thing with AFM is you can do these things in more physiological conditions. So you can actually look at things over time and how they stick and form. So this is an example of a fresh contact lens, a brand new contact lens. You can see the surface of the contact lens is nice and clean. And this is a few minutes later after you use it, it's all covered in proteins. So you get a lot of adhesions, proteins on the surface. But besides just passively looking at what happens, you can actually use the AFM to make mechanical measurements. And I'll talk a bit more about that tomorrow. But the idea is pretty simple. I have this probe. It has an arm, and it's deflecting, right? If I know the spring constant, and I know how stiff this mechanical arm is, I could actually back out the force I'm pushing on my sample. And that's really all there is to it. So I bring, instead of scanning across my sample, I'm going to take my cantilever, and let's say like indentation, I'm going to come down, smoosh it into things, measure the deflection. If I know the spring constant, I know the force, and that will give me a force versus displacement curve. So I can do that by indenting into things. I can also measure longer range attraction and repulsive forces on molecules because it's very sensitive. So as my cantilever comes towards the surface, you can see initially here for this particular curve, there's some repulsive forces. Then I smoosh into the surface, but it's a very soft tip, so it doesn't actually indent. And then when I come back on the back side, you see there's attractive forces, things that are stuck, that are popping off. So that's the basic idea of force field. So if you believe me that you can measure forces, you can actually use it to actually do what's called chemical affinity mapping. So if I know my tip and I put specific ligands on my tip, I can now come in contact with the surface and see where it sticks. So basically poke at different points in the surface. If I get adhesions or not, that will tell me something. So in this particular example, it's a plant cell, and they were trying to localize where these certain ligands were. And so this is just the topography, so same thing as before, it's just the topography of the cell surface. And then these are where the probe is sticking with the proper ligand, so it's sticking at different spots. Where here it's like not a reduced form of the ligand, so it doesn't stick on this one, even though the topography is the same.
Is there any defined area of how many spottings we have?
Yeah, so yes. In this particular example, the way they got around that is they had lots of ligands on a tip. So it happens fairly quickly when you have a pretty good adhesion. You don't have to wait, right? You just come down and stick some hole, and pretty much every time. You might get more than one hole, but in this case they didn't care. They just wanted to see whether it's stuck. When you do simple force spectroscopy, then you have to sample the space. So we used to do 100 at a spot just to get a good sampling of adhesion sites.
So propagation
binding event, they weren't actually characterizing the binding. If you actually want to characterize the binding, you need to do a lot of them because you need to sample the statistical. You know, sometimes it makes a shorter range interaction, sometimes it sticks harder, so you need to sample the space. So this particular one, I think, is an interesting study where they looked at endothelial cell surface, and they were looking for VEGF receptors, and looking at how they migrate over time. So very similar to that movie we saw of inside the cell, right? There are surface receptors, they're on grafts, and they're moving across the surface. So kind of measuring the dynamics of that relative to actin in the cell. And so it was this is a couple frames from a movie that they actually made of the cell over time. So just on the logistics of imaging, if you're going to do AFM imaging, or if you're reading about somebody who did AFM imaging, the biggest thing you need to worry about is what tip am I going to use? And so you need to pick the tip that matches your application. Cantilevers and tips are commercially available, so typically now you don't have to make your own. They can range in price from like $10 per cantilever to hundreds of dollars, probably like $100 per cantilever. So you want to make a good decision for what you want. So there's a couple parameters. The first one is my cantilever itself, right? I can have really, really soft cantilevers, so this big long one is like very soft, to more stiff cantilevers. So if I'm imaging something hard, I can use a stiffer cantilever. If I'm imaging something soft, maybe I want to use a softer one. And then you can change the geometry of the probe, right? So this is your standard probe, has about a nanometer diameter probe. This is a sharpened probe, it's much smaller. And then the other thing is what the probes are made out of. So typically, the cantilevers themselves are almost always made of silicon or silicon nitride because we make them using standard lithographic techniques like you make for computer chips. But the actual like tip itself can be made with just about anything. So for example, this is how they come right on the chip. Here's a bunch of different geometries of the cantilevers themselves that change the spring constant. And then for the tip, you can put a giant ball, and by giant I mean 1 micron ball at the end, maybe if you're doing some indentation studies, because the nice thing is this is a nice sphere. If you're modeling stuff, it's very easy to model a nice sphere interacting with something, because physics, it makes it easy. It's a sphere. Weird sharp pointing geometries, they're hard to model. You can put cells and bacteria on the tip and have that interact with your surface. You can put individual molecular ligands. If you want super, super high resolution, you can stick a carbon nanotube at the end of your tip and actually image with that. Obviously, carbon nanotube tips, more expensive than standard tips, so it depends what you want. So a couple of things. We just said the resolution of the tip matters. The size of the tip determines the resolution. So here's a brand new tip. It's nice and pointy. Especially if I do contact imaging, it's like a pencil. After a while, it will get more blunted, more blunt. And so the resolution will go down. This is examples of bad tips. This one is a tip that got contaminated with stuff from the media. So like, there's lots of proteins, they stick to your tip, and now I have a sticky, gooey mess. It's hard to image. This one is actually fresh out of the box, but it has a defect on it, which causes this. Which I'm looking, this artifact always like hurts my head to look at. So does anyone know what probably is the problem here? Why, if you look right, there's like 2 images of everything. It's like weird double vision. What could have caused that? 2 tips. Yeah, so this is what happens here, right? There's like a defect when they came out, and so now I'm actually kind of imaging with two tips, so I get weird doublets. This is an initial scan, and then this is what happens when stuff gets stuck on the tip. Everything kind of gets blurry because you have things sticking. But as I said, you can like change the tips, make them really cool. So the other parameters to keep in mind, especially if you're reading other people's papers, is the surrounding environment makes a big difference because, like in electron microscopy, I'm measuring small things. So when I'm measuring small things, every little factor matters. So obviously you can't have vibrations. If you're really doing high resolution imaging, you might have a lovely isolation system, but typically you put a big sign and you tell people to stop talking and move away because if you talk, it'll cause vibrations. If you first turn on the machine and wait, they heat up, so the cantilever will heat up using the laser on it. So again, you turn it on, you let it warm up, and then you kind of dig into your images. This is a problem we have a lot in South Carolina. It's very humid. So if you're doing your images or you're measuring things in air, everything is really humid in South Carolina. So all my surfaces have kind of like hydration layers on top. If I'm actually coming down and trying to measure forces, the first thing I'll measure in air is the cantilever will get like attracted to the water. Like there's water layer on the cantilever, water layer on my surface, and it'll get stuck. So luckily for us, biology tends to happen in fluid, so it doesn't matter when everything's wet. It only matters when you're trying to do things in air and you don't want things to be wet. So just for imaging, this is kind of a seminal paper that was in 1989, which was DNA being imaged with AFM. So like we did in the electron microscopy, looking at how chromosomes put together, this is DNA condensing into a loop over time as it's imaged with AFM. This is actually some data from my lab. This is just to show a different kind of thing you can do with imaging. So this is the topography. Here's our kind of error signal as I'm scanning. And then this is a map of the surface charge on the surface. So this is a tooth. And we're looking at charge distributions on the surface of teeth. And then, as I said, you can do magnetic stuff. So maybe less useful for bio, but thought I'd put it in there. So here's topography, it's nice and flat. Here's the magnetic field of VHS tape. So in general, AFM compared to SEM, AFM is kind of useful for soft polymer things that are in fluid, that are hard to image with electron microscopy. So this is a picture of a polymer layer from Abercan. So we patterned it in some area, and then we added more and more salt to the solution. And what happened over here is the layer got smaller and smaller and smaller because as I add salt, it shields all the charge interactions and the layer collapses on itself. So you can look at these kinds of behavior in situ with just some more examples of things to image. And then the last thing is kind of what you saw in the video. You can do manipulation with the AFM. You can move things around, dip lithography, all sorts of things, which is cool for building small systems for study. It's never going to be commercial, like you're never going to make thousands of these because it takes, again, time to do, but for a scientific experiment, it's useful. And then this was a cool thing that recently came out, was using the AFM to measure piezo response of a material. So here's the topography of a white blood cell, and here's mapping out the piezo response of these. And if you remember when we talked about piezo responsive materials, it's more like crystalline things. So certain proteins have piezo response, and it maps out kind of the interceptors of the band. So the last thing I wanted to do before is just to say that AFM is nice. It measures topography. You can use it to measure forces, and there's a lot of limitations. The big one being it doesn't directly measure distances, and we'll talk about that tomorrow. But you have a review article to read, so we'll talk about some of these issues. And in order to actually measure these things, you need to actually have good models. So we'll also talk about that. So there's a review article which should be getting via email. And the nice thing, the review article is actually kind of the role of nanomechanics in healthcare. It covers a lot of the techniques and issues we're going to talk about in class. So it talks about AFM, it talks about laser tweezers, it talks about some of the emerging techniques and how they're used for healthcare things. And I wanted everyone to read that to get an overview of the different techniques. I would like everyone to come with at least one question. If you want to email me the questions, you have my email address. So if you want to email me the questions, please email me the questions before tomorrow morning with the title, let's say, with the title of the course, so I can find them. And I will collate them, and we'll talk about them in the morning. Tomorrow, we'll talk about AFM for nanomechanics and nanoindentation, high-resolution force spectroscopy, and optical tweezers. We'll have an exercise to do also to play with the data, and I'll help you look at some articles to talk about how to work things. So that's kind of my plan. So read the article, send me one question. At least you can send me more than one question from the article, and kind of do that. Are there questions now?
Tomorrow, please.
Yeah. Yes. Oh yeah, that's a great question. So the question was way back where, when I had the picture of agarcan, is it a single protein fits on the surface, or how is it? So that particular protein is it's a single macromolecule. They are dried on mica, but they're not chemically attached to mica. So the reason we use mica, anybody, I don't know if there are materials people, does anyone know what mica looks like? Everyone's seen mica. Does anyone? Do people know what mica is? What's mica? It's the shiny stuff in granite, right? It makes the sparkles. Has anyone seen a larger piece of mica? Right? When you have mica, it peels off in sheets. The reason it peels off in sheets is because the crystalline structure is basically sheets. So if you take a piece of mica and you peel off a sheet, you have an atomically flat surface. And so that's why it gets used a lot for imaging purposes, because it's completely flat at the atomic level. And so you get these nice pictures. If you were to put the molecule on something that already had a topography, it would be very difficult to image. And so by the way, if you read papers and they say, oh, freshly cleaved mica, you might think, oh, this is very complicated, and you need to, what you do to make freshly cleaved mica, to get yourself a piece of mica, you get a piece of tape, put the tape on top of the mica, you peel off, you have a nice clean surface. It's really easy. Any other questions? Oh, the actual mechanics? Yeah. So there's already software on most AFMs that actually will calibrate the cantilever for you. So to measure the spring constant and all that is typically done with the software on the machine. Okay. What? I will say it depends on what you're trying to do. For most things, it doesn't matter. Any other questions? So earlier today, right, we were talking about mechanobiology, cells, and molecules. So the advantage of this particular technique, right, is that you can stick your cells on an optical microscope and put the AFM on top, so you can see the cell and then push on the cell, pull on the cell, with basically, like Richard Feynman said, like little nano hands, right? You have something that you can manipulate. So AFM is not the only technique that does this. You can get just micro and nano manipulators that are basically the same idea. You get piezoelectric actuators that move things around. So it's a very kind of, they're not called AFMs, but they work with the same principles. I will not bite. Questions?
When the cantilever is moving, if it encounters a cloud, it will flag according to the amplitude because of that but now how will you detect a trough or
It's a great question. So there's, depending on the mode, right? So if I'm imaging with contact mode, it should hopefully not vibrate. So it should be just like, here I bump up, the piezo goes up. There it comes back down, so the piezo comes down in response. It basically tries to keep the cantilever at that same. In tapping or intermittent mode, I'm tapping at the frequency, and then as it comes up here, suddenly the amplitude goes down, so now the move is piezo response. And then as it comes to a trough, the amplitude will increase, so now the piezo has to drop down in response. So it's always the same kind of idea. Does that make sense? So in contact mode, if the more the tip deflects, the harder I'm pressing and the higher up it's going. In tapping mode, it's kind of the opposite. It's like the smaller the amplitude is, the higher the sound is. That actually, one of the limitations of AFM is if, again, you have a surface and it really has really deep pits in the surface, the cantilever and the piezo might not be able to go all the way to the bottom before coming back up. So that's where you can try scanning really slowly, but if it's like a really deep and narrow hole, you're not going to, obviously you can't go all the way to the bottom. So yeah, that's
But the software is going to reconstruct the...
Yeah, so it's a point-by-point reconstruction. So one of the things actually that happens with AFM imaging is you get your, as each line comes in, it reconstructs the image. And then once you have a full image, typically what people do is they fit a plane to the image and flatten. So like it takes into account that your sample might not be perfectly level. So if you're doing that, you can plate fit all day because that just basically gets rid of the tilt on the sample. Most AFM software will give you lots of options of fitting like quadratic functions and whatever. There's very little reason ever to be fitting and taking out a quadratic function from your image. The only place I saw that being used and it made sense was someone was imaging the surface of basically like a micro scale tube. And so they wanted to get a picture of the topography that's on top of my tube. So then, yeah, you might want to take out the bigger topography and look at the little groups. But otherwise, yeah, you should.
So in the scenario of AFM, cantilever, teeth and sample is the main part of it. But my question is that, if you fix the teeth by spring mode, where no need of moving the cantilever, where there is no movement of the sample,
right.
So what is the prospect of that? Teeth will be northwest and sample will be also northwest. So if you make the teeth with a spring counter, spring type.
Yeah. So you mean like if, so usually you
cantilever will be like this only,
right.
sample will be like this only, but only teeth will be spring mode.
You mean mean like if it's vibrating?
Yeah. The same concept is same, but you should be converted it to movable type instead of cantilever or instead of sample.
Instead of six, it says can be elastics, like fixed to a scale.
Yeah, we can
Oh, yeah. So actually, there's a mode that's basically kind of what you're describing a little bit. Like so, it uses it vibrates the tip and kind of uses the fact that it's like a spring to measure, like without actually touching the surface, map out forces, like from the non-contact forces as you're imaging.
Then you can set both. You can set the deepens, you can set the sample.
Yeah. So you can actually, but it's the same principle.
The principle is same. Only that thing I must.
Yeah. And so most AFMs will like to do that.
Would it compromise on the sensitivity of the
Right, so the resolution, yeah, because you're not necessarily imaging, but then typically when you're doing that mode, that's not what you're aiming for. You're trying to map, you know.
Because for the scales we are working with biological systems, I think that should work fine for rather larger scales.
So, well, and very, very small things. So the video we saw from IBM, when they moved, they used what's called STM mode to move the atoms on the grid. But when they imaged, they actually didn't do contact mode. They kind of vibrate the tip and keep it away from the surface and map out the surface. So they're not actually touching the atoms as you're imaging, because that would move contact. You can't. But they're kind of mapping out kind of potential away from the surface to map out where the atom is.
So for the nanoscales that we are working,
yes. Yeah, for like soft, flexible things, it's a problem. So a lot of problems with imaging biological stuff is they're very soft and flexible and they wiggle a lot. So whether you're doing it with AFM or anything else, it's hard to image them because they're moving. And so that's where cooling, maybe you want to make the system really cold so everything kind of freezes in place. In the case of biological things, that's why we tend to dry them out because they're not in fluid, but everything kind of moves a little bit, so you don't get this kind of crispy image in fluid. In fluid, it has the same general shape, but you can't really see all the little side channels. But you can see how far out they extend. Kind of look away from the sample. Dramatic. See, I dance. Dramatic readjustment of the molecule. Yeah. With this sound, instead of if I vibrate my tip at a set frequency and then I measure the response, the phase lag, that will give me more than just the elastic response, right? Again, kind of a model of the system over space. So that helps. Other. So if I were, I'm going to give you an example, and then people can tell me what they would do. So this actually is like legitimately something that happens to me all the time. I have a colleague who comes and they have a new polymer that they're going to use, that they're interested in understanding how, I don't know what cell, pick your favorite, epithelial cells stick to this material, right? That's their goal. And they want to see a couple things. One, they want to know what is the mechanical properties of their polymer material, because they want to know if it's too hard or too soft to put in the body. Two, they're interested in understanding which proteins are sticking to their material to allow for the cells to then stick on top. And then three, they're interested in understanding the time course. How long does it take for the cells to go and stick on their material? So that is a very typical thing that kind of nanomechanics bridges lots of scales that are people will do. So three things, right? I want to know the mechanics of the actual polymer in material. I want to know how proteins are sticking to that material, and I want to know how the cells themselves are sticking to the eventual material. So think about it, what techniques would I use to do what? I'm going to sit here until people give me some answers. You can talk amongst yourself. I'll give you 2 minutes, and then I'm going to call on a random person. Yes. That's a great idea. Yes. Excellent. So I don't know if everyone heard. So for the second, the suggestion was if I want to know how the proteins are sticking, you could put protein on the tip and look at it and how it sticks to my material. So that's a great idea. Logistically, those experiments, the first step to figuring out how to do those experiments is to figure out how to chemically attach my protein emitters onto my tip. And once you do that, it's pretty easy to knock things out. So good job. It's not the world's easiest experiment. So as a first pass, what I would suggest is stick your material, put your protein solutions, and then do some imaging so at the micro scale you can actually see how much of each different protein will stick. And then the one that sticks the most, then you can measure the actual forces, just because that is a longer experiment. So other things, how would you measure, this is an easy one, how would you measure how many cells stick to my material over time? That's not very mechanical, it's just everybody in this room should know how to do this. How do you look at cells normally? Like an optical microscope. You put some cells on it, you watch it over time. How many cells are sticking on the material? So, as I mentioned, I do a lot of AFM. So people will come and want to do AFM on everything for things they don't need to do AFM on, right? So you need to pick and choose your battles. It's really easy to stick a material, put some cells on it, look at it, optical microscope, and then use fancy techniques to drill down on certain things. You don't want to use AFM, SEM on everything all the time because it'll be expensive. It will take forever. And you probably won't get the data you want, right? So always look at larger scale things first and then come down. So the last one was how do I measure mechanical property of polymer layers? There was a mechanical you invented, you know that. use so in general, for mechanical testing, right, you can push into a material, you can pull on a material, you can try breaking the material, right? Lots of things. It's the same at the nanoscale, right? I can use different actuators and things to push, pull, break materials. The analysis is a little different, but it's the same idea. So similar to when you're testing larger scale materials, you can do these things. Honestly, for AFM, that's an easier measurement to do than actually imaging. In general, imaging is a little bit of an art. It's like, you know how some people are really good at photography, so we both could take the same picture of like a flower, but I'm very bad at photography, and so the same flower, someone else will take the picture, it will look great, like a magazine cover. I will take a picture and it's like out of focus, right? So, same thing, imaging, there's a bit of an art to it. All these parameters that you have to tune for AFM, whether or SEM, same thing, I'm going to have to tune the electron beam and everything. It takes time to get a perfect image, but you learn those things. The mechanical tests with AFM are much more like mechanical tests with like standard materials. You just come down, push on stuff, pull on stuff. It's a little bit more plug and play, easier things. The hard part with nanomechanics is less the actual experiment, more the experimental interpretation. So the data isn't like standard large-scale macroscopic tests because you have all this structure, things are moving, there's a lot of less signal to noise, so those are the things we're talking about. No? So you're getting a paper, yes, email, the paper and the data for tomorrow. So everybody should open the data file just to make sure. Okay, make sure the data opens. Yeah. Read the review. Yeah. Yes, please. And send me questions or come tomorrow with questions. Because if people don't ask me questions, I will get up one at a time and ask questions.
So in that case, we'll wind up for today, and we will also start by 9:30 sharp. 9:15 sharp. No, 9:30. So 9:15 we have to start for
I'll start with that. So, I think someone
group, because I can't pull up my email, pulled up and asked about what of the imaging techniques we covered yesterday were the best for biological samples in terms of resolution and magnification. So the short answer to that is it depends what you mean by the best and by biological sample. So the highest resolution imaging you're going to get pretty much is TEM. So if you really, really need to drill down into atoms, you're stuck using TEM. That said, just because a technique has really high resolution, really good resolution, and you can get really nice detail, doesn't mean that that's necessarily the best imaging technique for your sample. Particularly if you're talking about biological samples, because as we mentioned, right, TEM had all this kind of, you had to dry it out and everything, and it tends to distort samples. And so the other techniques might be better for what you want. The next best resolution is probably AFM, maybe SEM. They're kind of almost the same, but you can get better resolution with AFM than SEM. But fundamentally, they image different things. And same for magnification. I think the power of SEM is that you can go from really big to pretty small really easily. So if you're not sure what you're looking for, it's kind of useful technique. It also is kind of non-contact, but it does have sample preps that are a little bit more harsh than AFM. So if you're trying to look at something in fluid at the nanoscale, AFM might be a better technique for you. But again, if you remember how the technique works, you could optimize it, but it's a little bit more finicky. SEM has really standard preps, so a lot of times it's easier to go do SEM. So that's the longer version. Do people still have questions on that, or does that help kind of clarify? It depends what you want to do and what you want to see, which imaging technique you want. And for everything that we're saying with nanoscale everything, your first pass on a biological sample should just be optical microscopy, right? We all just look at our sample first, make sure it looks okay, and then you spend the time to prep it for these nanotechniques. If you have a sample and when you look at it under the optical microscope, it's not perfect, right? It's maybe the cells look weird, or if you have a polymer material that you want to use as a new implant material, the structure isn't right, or it's not forming the way you want, then there's no point in doing the nanoscale type assessments, unless it's because you can't figure out what went wrong. So we have done that before with collaborators where they're trying a protocol to make like a hydrogel for some kind of implantable material. They're following a protocol, it works great in their collaborator's lab, and it's just not working in their lab. And then we would do SEM or something like that to try to figure out what the heck is going on and why it's not working there. So yeah, is there any more question on the imaging side? Are there any questions from the review article? So the review article I thought was nice in that it covers the breadth of nanomechanical techniques. We're not going to cover all of those in this class, but I wanted to know if there was any particular topic that people especially were interested in. So I think on Thursday, I have scheduled to talk about like cardiovascular nanomechanics, single cell mechanics, and cartilage nanomechanics. But I can shuffle those around if there's a topic that really interests the group. I think someone emailed me. See, I wrote the questions. I didn't write down who was there. And was interested in cancer cell elastic properties. And so for today, actually, we're going to cover AFM nanoindentation and optical tweezer methods. And then I have two actual articles that were assessing breast cancer cells and the changes in elasticity with breast cancer cells using AFM, and then the other paper uses optical tweezers. So what I wanted for tonight was that everyone could read the papers, and then tomorrow morning we could discuss, because they find different things, right? And so again, it's one of those important things to figure out which technique you want to do, knowing the limitations of the technique and what they're measuring. Especially if you're reading papers, the different techniques might give you different numbers, even for an elastic modulus. And it's important to know when you're comparing things that you're comparing apples to apples, oranges to oranges. And then I think someone asked about therapeutics on the nanoscale, so I was going to include some of that on Thursday. But are there topics or things when you read the review article you're like, I don't understand this? So, something. You all read it, right? Really, so if I put questions on, we're supposed to have a quiz with multiple choice on Friday. So I could put questions on anything on that article and you feel fine. There we go.
How is AFM related to the breaking of bonds in the...
Yeah, so we're going to cover a little bit of that for high resolution force spectroscopy. So AFM, has a probe. We talked about it in imaging, and today we'll talk about it in force kind of modes. You can actually use it to pull on molecules and pull enough to break bonds. Those are actually kind of tricky experiments, so I was going to go over how to set up one of the experiments. The tutorial, actually, you'll have some data from an actual experiment looking at intermolecular forces, so more like ionic interaction, not a covalent bond, but it'll give you a sense of what that kind of data looks like. Honestly, setting up the experiment is not that bad once you know how to do it. Interpreting the data is always difficult, because you'll get these like sticky things and then they'll pop off, and then how to interpret that data is hopefully I'll cover a little bit, but you have to you have to know what you're looking at to kind of use the right model and get some data. You can have lovely data, but if you're interpreting it and it's not physically what's happening, you'll get, nonsense results. So if you take the data we're going to do on the tutorial, it's from layers of kind of polyelectrolyte things interacting with each other and pulling. And you have some adhesion type forces. If you didn't know that was what it was, and you interpreted that graph as a bunch of covalent interactions breaking, you can fit the model to that, because there's lots of fitting parameters, but it'll get you, first of all, really weird results, but it doesn't make sense for what physically you know is in the system. So I think that's the trickiest bit with those kinds of experiments, in my opinion. Yeah. Questions? Other tickets? Yes.
One other question is, how viable is a biological sample after AFM?
That's a great question. And someone asked me that at the end of lecture yesterday. So AFM, kind of like, in general, kind of like optical microscopy, you take your sample out, you put it in, if you're really careful, you can make sure it has a heated stage so the temperature stays warm. You can even put it in like a carbon dioxide level so you can keep it really nice. So in those experiments, you can actually keep samples pretty alive. The physical interaction with the tip in your sample does, affect samples. So for instance, if we're going to talk about cell indentation. If you're indenting into a cell with a probe, obviously you're poking at a cell. The cell is going to react to that. Now, one thing that people tend to think is if you have sharp, pointy tips and you push into the cell, you might poke a hole in it. And I have to admit that when I started, that's also what I thought, because they're really sharp and you're pushing into them. It actually requires quite a lot of force when you're pushing down. It's a lot of force and really fast into the cell for it to actually poke a hole and have it burst and kill the cell. The cells can actually handle quite a lot of
compression type forces. They're designed to do that. In imaging though, it's actually fairly easy and sheer to scratch across and kind of like cut off filopodia and things like that. But I've actually personally never managed to poke a hole into a cell with indentation. Now, if you indent the cell alive, and like you, or maybe with a sphere, you push it down and it's like, I don't know, over 50% strain, like it's completely squished down, and you hold it there for more than like a second, the cell probably will die because, you know, you're deforming the nucleus and all those kinds of things. But in terms of generally your sample, if you're careful with them, you can test them and then put them back in the incubator and they'll be fine. So that's a good question. Yes?
How is atomic AFM different from STM?
Yeah, so AFM and STM are related techniques. So if you remember the movie from yesterday, it was STM. It's scanning and tunneling microscopy. And so STM was actually invented first. And the way it works is you have your tip and your sample, and you put an electrical potential across, and you actually can move atoms that way. You can also deposit material or take away material depending on the direction of the field at the atomic level. And that's why IBM developed it first. They realized then if they turned off the field, they could actually image with what we now know as AFM. So typically an STM setup you can turn on, well, AFM setups usually you can also turn on STM mode, and basically you're driving a field, so you're driving ions from the tip down to the surface. In the video with the IBM, when they're moving the atom around for each frame, that's STM. And then, so they move it, and then once it's where they want it, they will image with AFM. And so that's why the one researcher was saying they have to listen to the sound. It's because while they're using the STM mode to move and kind of like, they're not touching the atom, but they're putting a field to nudge the atom along. So while they're doing that, they can't also image at the same time. And so they listen for, as the atom moves from one position on the lattice, the atomic lattice, to the next. So they know they've moved it, 3 slots over. Once they're happy with that, then they switch it to AFM mode and image across the sample. Does that kind of make sense? So, like fundamentally, the way the instrument is set up is very similar. It's just that you can add a current that goes from the tip down to the sample and back.
So is there any threshold on thickness of the material that should be used for
STM or AFM? AFM. No, so it's a surface technique. How thick and big the actual sample can be really depends on your AFM. So some AFMs have really big sample stage, and so the AFM itself, we said, could only move like 100 microns or so because of the piezoelectrics, but they're usually mounted on a motor, so you can it has a motorized stage, so you can use the motor to get your thing close to where you want, and then you can come down and move. The AFMs that are typically used for material science, semiconductor analysis, typically have really large stages, so they can put whole silicon wafers in there, and then scan different sections of it. Most of the biological type AFMs are mounted on top of an optical microscope, and so the only thing that limits the size is kind of how there's little legs that they sit on top, so how far up you can make the sample. So in terms of bulk sample size, there's not too many limitations. It kind of depends a little bit on your instrument. The one thing I will say is you kind of want the sample to be sort of flat, right? So if you have a piece of bone or whatever, and it's
shaped funny, and you have to figure out a way to put it in the machine so the end that you're interested in is pointing to where the tip is. So, more than that. Good.
When you're discussing SCFC and SMFC related to cellular adhesion force and molecular adhesion force, we're changing the T.
Right, we're keep going. Yeah. Yes.
So for that reason we are changing a T. For cellular thing we are using a live cell, and for this thing we are using a you can say that Dijon peptides or chips.
Yes. Yeah.
So but even that molecular force in cellular force. So by using the cell, can you find the molecular force?
Yes. So we actually think I have data on that. So you can either kind of try to decouple the two, right? So if you're trying to look at molecular type forces, you could take molecules of interest, put them on the surface, take molecules of interest, put it on the tip, measure forces. Or if it's like a cell type molecule, you can put your cell and then directly measure on the cell. The harder part of that type of experiment is you need to decouple the mechanical properties of the cell itself from the molecular interaction. So the models used to analyze those types of data a little bit more complex. But one of the issues with kind of directly measuring molecular interactions between a surface and a tip is how to put the molecules on your tip and surface so that the molecules themselves don't denature or change their conformation. So what you're actually measuring is what you want to measure, if that makes sense. So it's a little tricky. It's not. Usually people end up doing both. Like they'll do one first and then the other to kind of confirm results.
Then next, the force versus distance curve for both the scope is the same?
Yeah, so not exactly. So we'll talk about force distance curves. If you're doing a force distance curve on a cell, you'll be indenting into the cell at the end of the curve, right? Because you'll come down and then you'll squish into the cell and come back up. Whereas if you're doing it on a molecular thing with surface, usually the underlying surface is hard. So when you come in, there's kind of a point where you're pushed up against the surface and then you'll come back out. And so that's actually what we're going to talk about today, is kind of the differences between those two types of measurements. And that's what I mean with the analysis is a little bit different on both. Yeah? Plants versus like animal cells. So one of the difficulties, in my opinion, because I don't do plant cells, plant cells have a cell wall. And so there have been lovely studies looking at mechanics of cell wall versus the membrane. So with AFM, you can definitely measure the cell wall, but then how to get into the internal cell information is more difficult. I saw a really interesting paper where they combined AFM and high-resolution optical techniques so that they were using the AFM basically to deform the whole cell, and then optical techniques to look at the cell slices to actually get the deformation of each parts, and then back calculate mechanical properties. But yeah, that's it's not my area of expertise. I'm very impressed with that paper. Yeah. The other technique I've seen a lot for cell mechanics in plant cells is actually, again, it's more optical, but it's using osmotic swelling and things like that to back calculate. And then image correlation techniques to look at small scale interactions in the cell. So yeah. Are there more questions? Are we feeling good? So I can ask anything. Okay. I will talk a little bit about AFM as for nanoindentation and high resolution force spectroscopy today. And I figure after that, hopefully that will help kind of. The nice thing with the review article is it covered a lot of techniques, but it doesn't cover them in very much detail, right? So hopefully this will help. So AFM, yesterday we talked about it as imaging,
but also it can be used for force measurements. And the only thing that's different really is typically for force measurements, you just take the tip, come down towards your surface, come back up, and then you look at the deflection of the cantilever, so like here it's bent. If I know the spring constant of the cantilever, then I can have a force. And that's really all there is to it. So you'll get data that kind of looks like this. So this is kind of a typical high-resolution force spectroscopy curve. So you come in, and this is what I was saying, usually kind of with a hard surface. So you'll hit the surface, and then you'll come back out, and you'll get adhesions. Or sometimes you can have long-range repulsive forces, which is happening here actually. In nano indentation, it's pretty much like a traditional mechanical test. You come in, you push into whatever it is, this is a cell, and then you come back out. You can also do fancy things like you can come in, you can wait and let the stress relax, and then come back out. Very much like if you've done traditional mechanical testing of materials. There are some tricky bits to analyzing these types of data, and so the tutorial lab exercises for today, I think I have one for tomorrow, are kind of focused on what does the data actually look like and how do you analyze it. And I think that's important to keep in mind, again, when you're reading papers, because small changes in how they do the conversion of the raw data into force distance curves and things like that will actually make a difference in terms of the numbers they actually report. So it's always important to read. And again, make sure that the two papers you're comparing, or if you're comparing a paper in your own work, that you're using the same methods. So nano indentation I thought I'd start with, because if you've, at least mechanical engineers, if you've done indentation, it's the same, it's just very small. So basically you have your probe and you push into the material, and that gives you some material properties. You can indent into harder materials, so this is a force displacement curve from indenting into, I think this is bone. No, that's not bone. That's hydroxyapatite. So if you're pushing a tip into like a ceramic or a material that's a mineral that's really hard, you end up with poking holes into it. And then this is from pushing into a cell. So this is a picture of that experiment. So you come in, you push into the cell, cells are viscoelastic. You don't end up with a permanent deformation of the cell because it just bounces back into shape. If you've ever done mechanical testing of materials at the larger scale, nano indentation into hard materials is very similar. The only difference is that I am not going nearly so far into the material, so it's nano indentation. And the advantage of this is I can actually do these experiments over a material surface and get properties on that length scale. So understand if there's like stiff areas and soft areas on that material. You also can then image the indentation site and understand, here you can see there's a pile-up of the material after I've pushed into it. So in order to make these types of measurements, so for biological things, that's what you do for bone, teeth, seashells, bug exoskeletons I've seen, things like that. You use a true nano-indenter system, typically, as opposed to just a standalone AFM. The nice thing with indenter systems is they have extra sensors, so they actually measure displacement directly, and we'll talk about that in a second. And then there's usually an AFM connected to the system so that you can then image your indentation site and calculate contact area afterwards. This is the tip, so in order to push into hard materials, you need a really hard tip. So typically you use something like diamond tips, and they're shaped into pointy bits.
And the shape of the indenture, of course, determines what kind of model you use to output your material properties. This is a picture of a Berkovich indenture, which looks like that when you indent. So it's a little three-sided pyramid. It's a pretty common indenture because they're relatively easy to make. You might also run into things called Vickers indentures, which are very similar, but it's a square pyramid, so it's 4 sides. So I thought I'd bring some examples from stuff I've done. So we had this project on teeth, which started because my collaborator was getting married and she was thinking about whitening our teeth. And we were at the medical school talking to other people and talking to the dentist. And the dentists were like, oh yeah, we can whiten your teeth. And my collaborator was like, do you whiten your own teeth? And the dentists were like, oh, heck no. Never whiten my teeth. And I was like, why do dentists not want to whiten their teeth? That's not good. So they were worried about the properties, damaging your teeth with the whitening. And so we were like, great, we are going to test this. So we're going to look at teeth mechanics. So a little bit about your tooth. Tooth has, enamel, which is really hard, and on the outside, it's smooth. It's almost all, it's like 98% hydroxyapatite. It's highly crystalline. And then the inside is dentin. Dentin is a lot more like bone. It's a combination of mineralized components and collagen. So it's a little bit more elastic. So this is just to show you what a nano-indentation curve on enamel looks like. So you push in and you push back. You get up to, this is 5 newtons, I think? Yeah, 5 millinewtons of load, and I'm still only 50 nanometers into my sample. Whereas if you do the same thing with dentin, you can see that at the same load, I've indented almost 300 nanometers into my sample. And also you can see that the material has this much more, there's a loss in here. So that's teeth. For the people who aren't mechanics people, I thought I'd do a little review of like numbers of things we're going to talk about. If you read nano-indentation type papers, most things report the Young's modulus. The Young's modulus measures the stiffness of a solid material in the linear elastic regime. And what that means is over here, that's your traditional engineering stress strain curve. At the beginning, when I start to compress, I have a nice linear region. If I were to just compress my sample from here to here, and I let go, it should come right back. That's an elastic material. So I have no permanent deformation. In real life, most of our materials are more complicated than that. So if you were to keep pushing into your material, you'll have an area where you have plastic deformation. So that means you keep pushing into it, but now you're permanently damaging the material. And that's why when you do a nano indentation, you end up with a hole in your material, right? I've like permanently made a defect. So from those, you get other properties. So one thing with Young's modulus is not to get confused. Just other parameters that people measure, including hardness and toughness. Those have very defined meanings, and they're not the same as elastic modulus. So toughness is the amount of energy that a material can absorb before fracture. So here's where it fractures. If I push hard enough, right, I'll fracture the material. So the area under the curve, right, is the energy. So that's toughness. And then so on. So we're doing Young's modulus. So just a little bit about nano indentation. I borrowed this slide from my former advisor because it has all the details. It's very busy, but I thought you could have it so you have it for your reference. So when I push my indenter into a material, right, it's going to go in
the material is going to deform, and there's an area where I have contact with my indenter. So here, if I do nano indentation, I will push into my material and I'll come back on unloading. And there's usually hysteresis in the curve. So if I have a purely elastic material, which in biology I never do, but let's pretend I do, I'm going to push in and I come back exactly to the same spot, right? It's purely elastic. If I have a purely plastic material, it's not elastic at all. I push in, and then when I come back, it just goes back to zero because I've made a giant hole, and it doesn't bounce back from that. So most of our materials are elastoplastic. So I push in, I let go, and it comes back, but it just doesn't come back exactly, right? So I have some loss that happens because I've changed the shape. You can get really fancy and get, a combination of visco, elastic, and plastic. Which I think if you look at the bone, this is kind of that. So the fact that it comes back and it doesn't come back to zero here, that's a plastic deformation. The fact that it has this kind of roundy shape, that's a viscous loss. I had that slide there. Okay, so the way people analyze nano-indentation data is with Oliver Farr. There are lots of ways that are much fancier to analyze nano-indentation data, but this is the first pass. This is what everybody tends to do first. And again, if you're going to compare papers and things, you start with that. So in Oliver Farr, you're going to calculate what's called a reduced modulus, which it takes into account the modulus of your sample, modulus of your indentor, and then the Poisson's ratio of both. For most biological samples, Poisson's ratio is near 0.5, which means they are incompressible. So between 0.4 and 0.5 is many material, but not all. So you should look up what those values are. And it's very fancy and there's lots of parameters, but all you really need to know for Oliver Farr is that you have your curve, and the thing you're really interested in are two parameters. One is the contact area when you've indented, so A, and the other is this S parameter, which is the slope at the top of your unloading curve. So, the slope of the top right is like right here, so if I draw this line, this slope right there. And then the contact area I'm interested in is the contact area right there. The contact area depends on your indenter, right? The size, like what's the shape? If it's a round thing, a pointy thing, right, you're gonna have different contact areas. So for a Berkovich tip, the contact area is roughly 24.5 times this little distance here squared. So basically, the only thing you have to do when you have nano-indentation data is take your curve, draw a line at the top, at the very top of the unloading curve that follows that slope, draw it down to the baseline, that will give you HC, and then the slope of that line is S. So pretty simple. Are there questions? Does that make sense? So a couple notes. First of all, the indentor geometry matters. So this formula is for a Berkovich tip. If you use a sphere, a Vickers indenter, right, you get different formulas. And the material you're using matters. So this is for a very much elastoplastic kind of system, and we're really only interested in the elastic part of the data. This is only reporting values for plastic stuff. So this is the experiment. We had teeth. We cut the teeth in half. Half the teeth were left untreated, and the other half of the teeth we treated with either Crest white strips, opalescence, which is a whitening treatment you can get at the dentist, or just as a positive control phosphoric etch, which heats up the mineral component. And then for sample preparation, we had to somehow get the tooth under the
AFM. So we put it in a non-infiltrating histology medium, so that's a plastic that kind of holds it in place so we can slice a nice flat surface. And then we did nanoindentation along the dentin enamel junction. So along the part where dentin and enamel meet. So here's the tooth, and we did like right there. Just so you can see, this is, I'm in one part of the tooth, here I'm in the other part of the tooth, here's the dentin enamel junction. So, which part of the tooth, what part of the tooth is up here? Is it the enamel or the dentin? Oh, it's the enamel. So enamel is much, much harder than the dentin, right? So this is 100 gigapascals, and down here is 20 gigapascals. So yeah, this is the enamel, this is the dentin. Now the interesting thing to note here, right, is the junction between the two layers in your teeth is really short. The space difference between the indents was about, I think, 5 microns. So that happens really quickly. So this is actually what we got for data. This is the mechanical properties of dentin in gray, enamel in blue, and the percentage difference from the control with the different treatments. So first of all, you can see if you put phosphoric acid, your teeth, huge drop in the modulus. So that's what we expect, right? Phosphoric acid should etch away the mineral component. For those of you that drink a lot of soda, that's also why your teeth end up being soft. So Coke, soda products have a lot of phosphoric acid. So liquid essence didn't change them too much. Crest white strips, if you look, they actually got harder, right? So what's in this material? There's peroxides, which is what makes things white, and something else that will make your teeth harder. So what happened was, when manufacturers started making these materials to whiten teeth, they found that peroxides, kind of like the phosphoric acid, make your teeth softer because they have to go in and etch away at stuff, get the stains out. So in response to that, Crest decided, no problem, we're going to put peroxide for whitening and fluoride into the strip. And so when you put the strip on your teeth, it's putting peroxide and fluoride together. So you might think, this is great. I should Crest white strip my teeth, they get nice and hard. But one of the problems you'll see is that the dentin got harder by like 15%. The enamel got harder by 25%. And what happens is, in teeth, why do we have problems with teeth is because that junction between your enamel and your dentin is really short. And there is a lot of load that has to transfer from the enamel to the dentin. And so there's a huge mismatch in mechanical properties, right? We have really stiff, hard enamel and kind of much softer dentin. And so if you're doing this, you're making that difference bigger. And so what our hypothesis was, and what we kind of saw when we looked at samples, is you're much more likely to crack the tooth and get little crack fractures in the junction when this happens. Because you've gotten, yes, they've gotten harder, but the outside got way harder than the inside, and your tooth can't handle that. So maybe the dentists were right, we shouldn't have whitened our teeth. And then the other thing is that, yes, they do put fluoride in your teeth whiteners. So that was an example. Nanodentures are nice. They can do these tests pretty consistently. It's one of the easier nanomechanical tests to do. The harder parts is figuring out how to take your sample and kind of, as I said, hold it in place and kind of cut a flat surface so you have something to probe. But people have been doing this for quite some time, so there are nice, well-established methods. The other thing, again, is when you're doing the analysis, make sure you know what your tip is, kind of what your material is, so you do the correct analysis. So if you're comparing across samples or between people's data, maybe you have an indenter with a Berkovich tip, but you're looking at a paper that uses a Vickers indenter. Make sure you use the right equations, because otherwise your numbers aren't going to make sense. True nano-indenter systems do measure displacement very accurately, so it's relatively easy when you get the data's kind of all converted for you. It's pretty easy. And most of the systems now have all over far models built into them, so you can, if you give it the parameters, the computer will spit out a number for you. So the only reason I really point this out is one of the problems that students run into a lot is if they go do nano-indentation, the computer will spit out a number, but the computer doesn't know what tip you put in and things like that. So always double check that you have the right settings, because otherwise you'll get a whole bunch of data and you'll say that your material is way stiffer or way softer than it actually is. So always double check. So that works really well for harder things, but soft materials like a cell, hydrogels, most of your tissues, right? That doesn't work. This is much higher loads. The load cells go up to millinewtons. So what do we do to measure those? So that's where you use back to standard AFM methods. But first, I had this as a homework question, but I thought we could do it in class. So this is actual data. Nano-indentation in bone from this paper. And I think it's in the slides. Is it on the slides? Do you have it in there? Maybe? No. Because I had it in the notes. It's fine. We'll do it from class. So, these are all the curves. So if you look at the curves, with just looking at it, which curve which of the, first of all, is this bone an elastic material? Right? I've heard some people know, right? It's not purely elastic. Why? Because I push in, I come back, it doesn't go back to where I want it. It's not just coming right back in. Right? So bone is not elastic. Okay, so of these curves, so this is like they had a bone and they pushed in different spots. Which of the curves is the softest? Is it the blue curve, the green curve, purple, or red? Red, right? So red is the softest, blue is the stiffest. And so C was calculate the reduced modulus for the stiffest and softest curve, assuming a Berkovich indenter. So I can send the file so you can actually practice and do it. But basically what you're going to do is take a ruler, right? Draw a line from here going all the way down to here, right? So we get to, what is that, 35, 40 nanometers. And it went up, let's say we go 40 nanometers, and it went up to 5 micronewtons. So the slope is 5 divided by 40, right? So that's S. And then I told you it's a Berkovich indenter. So it's on the bottom of the equation. So S is, what did we just say? 40 divided by 5 is S. And then it gets to here, so HC is 40 nanometers. And then you plug it in, and that will give you your modulus number. So that's really all there is to nano-indentation data as a first pass. There is a lot more happening in these curves than just the elastic properties. And so most of the discussion with nanomechanics is, yes, we get a stiffness, but what is the mechanism that happens? What's the parts that aren't elastic? And so you can measure the area in the curve to look at energy, all sorts of things like that that have a higher level kind of analysis. as a comparison, this is bone. This is indentation into pure hydroxyapatite, which is the mineral component of bone. So, what are some things you notice when you compare indentation into bone versus indentation into hydroxyapatite? Yes, right? Pure hydroxyapatite is pretty consistent, right? It's a nice crystalline material, so you get very consistent properties. Bone is not, right? Bone, depending on where you are in the bone, you'll get much different mechanical properties because the bone has different areas getting different loads. And so when it grows, right, it has different parts that it needs to address. What's another thing you notice? Yeah, so the elasticity versus they're different, right? If you look at the shape of the curves, they're different looking. So it's definitely not the same. What's something what's the scale here versus this? Yeah. So hydroxyapatite, right, is much, much harder than bone. That's because bone, like the dentin, is a good portion of bone is actually collagen. So the way bone gets made, the way bone gets made is your cells put down some collagen, and then hydroxyapatite actually grows on top of the collagen. So the collagen acts kind of like a very elastic, very soft material, and the hydroxyapatite is much harder and much more brittle. So the advantage for bone is that while it has a much lower elastic modulus, so this is a much harder material, hydroxyapatite is much more brittle. So once it cracks, it cracks. Bone, it has collagen, so it can kind of diffuse some of the load, and you won't get as many cracks from the same load. In addition, because of the heterogeneity, instead of having one crack that just propagates all the way down the crystallographic structure, when you have collagen, it will make lots of small hairline cracks. So if you think about your bone and how if you hit something and you break it, you'd much rather have lots of little fine cracks that can easily get repaired versus one big crack. So that's kind of bone for you. So does that make sense? So that was bone, and now we're doing cells, squishy things. When you do cell or hydrogels, a very soft material, you can't use traditional nano-indenters. They can't take that load. I think someone had asked about what you do for mechanical testing. If it's too hard, you destroy your sample, right? So if you were to use a nano-indenter on like a hydrogel or a cell, the sensitivity is not good enough, so the indenter would come down. It'd be measuring really nicely your displacement, but it would never feel the top of your sample. It would just keep going down, squish it completely, and you wouldn't get data. So with AFM, what you do is you get a nice, softer cantilever, and you push into it, and you come back. And so one of the things you'll notice with AFM, like gels and things like that, is they're not plastic, right? You come in, you come back, it goes back to where it went. There's no plastic deformation. Now, it's not purely elastic either because I'm coming in and I don't come back on the same curve, right? So there is some viscous dissipation, but no plastic deformation. I wanted to do this first before high resolution force spectroscopy because I think nano-indentation of cells, soft tissues, gels has become a standard technique. When I started, it wasn't. So if you were doing nano-indentation of cells or something, you could write a whole paper just on nano-indenting cells. You have whole sections on how you did your methods. Nowadays, people do nano-indentation as a way to assess the mechanical properties of their soft material as one of the many things they do in a paper. So the paper there's two papers for tonight. One is on optical tweezers measurements of cancer cell, and the other one is on nano-indentation of cancer cells, among many things. So it actually tests many things, and one of the things they look at is the mechanical properties. The difficulty with AFM, and what we'll do today to see how the data is converted, is that AFM does not directly measure the tip displacement. If you remember about how AFM works, it has a piezo actuator, right? So the tip is standing out here, and like my legs are the piezo actuator, right? So as long as I'm not interacting, if I go down 1 micron, the tip went down 1 micron. But if I go down 1 micron and the tip goes up, right, my displacement isn't 1 micron. So you have to take the deflection of the tip and the displacement of the piezo to get actual distance. The other thing that the AFM doesn't directly measure, and one of the biggest things to keep in mind when looking at AFM indentation data, is if you're indenting into a sample, it never tells you when you've hit the sample, right? The raw data has, once you've converted it some, you'll have a distance axis and a force axis, but where to put 0? Where do I put, like, okay, I've touched the sample? The machine doesn't know that. And so there are different ways to determine a contact point. How to determine the contact point will change the mechanical properties you report. So one of the ways to do it is saying, okay, like here, obviously I haven't touched anything, that's 0 force, right? Here, when I get over here, the force starts going up. Okay, I'm going to say that the contact point, when I've hit my cell, happens when the force goes above the baseline noise, right? Like if I hit a force that's higher than kind of my average noise value, then I've probably hit something. So that's a good idea. The problem with that is cells, and many hydrogels and things, they're not like a solid interface, right? Cells have like glycocalyx above. So you'll have this, like if you look at the data, it kind of has this like slow increase and then it goes up. So most of the instruments now will actually fit slopes and find where that kind of inflection point occurs, and that's where they'll stick their contact point. So the nice thing with AFM, right, is you can push into your sample and measure, and you can also use that to map. So here's a vascular smooth muscle cell. That's the topography from the AFM image. And here's a map of the mechanical properties as I'm pushing in different parts of that sample. The other thing is, we talk about cells, but it's very much used for lots of other things like hydrogels and small tissue samples. The big one being for mice, right? So mice are great for experiments because you can genetically modify them. You can get, all sorts of mice that have all sorts of things. But mice are really small, and so that's actually one of the biggest problems initially when they started using mice for these kinds of things. Is like we can't do the types of tests that we can in a larger animal model. So with techniques like AFM and nano-indentation now, you can take a mouse bone and do nano-indentation and get the mechanical properties of their mouse bone. And you can do AFM indentation on, say, the cartilage or different things. So this is some of our data on cartilage from mice. This is a mouse that, this is a control mouse. This is a mouse that got 2 grades of X-ray. So the mechanical properties of the cartilage went way down. Which this whole study was actually a colleague was doing studies on bone, and so he was doing nano-indentation, and I told him we could test the cartilage. I didn't think the cartilage would change. So when we first got the data, I didn't believe my grad student. I went back, I was like, nope, do it again. So every time, though, it came back. So yeah. So don't sit in the x-ray. This is a lot of x-rays. This is when you have cancer and you get multiple doses of x-rays, this is what happens with one dose of those types of cancer treatments. But this was for NASA, so these are also what astronauts do. So a couple caveats. While these are similar to larger scale mechanical testing, especially the soft materials with AFM, there's a little bit more issues than you would have with standard techniques. So there's a lot of signal to noise problems. So a lot of times people will come to me because I do AFM and they're like, I have this new hydrogel material, it's going to be great, we're going to use it in, I don't know, what's the one recently was like something gastrointestinal, putting it in like soft repair something. And we'd love to measure the mechanical properties in, physiological conditions. And I'm like, okay, how soft is your material? And they're like, well, we haven't done the mechanical test, so I don't know how soft it is. So my next question is it like, one of those gelatin dessert type soft? Or is it like, the stuff that comes out of your nose mucus type soft? And invariably it's like, yeah, it's more like snot. So the answer is yes. I can measure mechanical properties of like mucus-like things with AFM. Is it easy? No. So really, really soft, really, really sticky materials, you can measure them with AFM, but it's like very difficult. And so the things you have to optimize are, again, what's your cantilever? How soft is it? And if you know something's sticky, you want to make sure the tip isn't going to stick into the sample when you come back out. But for most biological tissues themselves, it's really not that bad because we ourselves aren't sticky. We're made up of things that sit in fluid, so most of the time it's not that bad. It's most of the synthetic materials that tend to be harder to do. You have to figure out how to mount your sample. So again, it's AFM, right? I have my sample here. I'm going to come push down on it. It's in fluid. You don't want it to float around so that when you're pushing, it's going to slide around. So with cells, it's not that bad if they're adherent cells. If they're, fibroblasts or smooth muscle cells, right? They attach, so they're not going to move around as you're pushing on them. But doing AFM indentation on something like a red blood cell is much more tricky because the red blood cell, it doesn't naturally stick to a surface. If you have tissues, so I've done mechanical testing on mouse heart valves, which are teeny weeny samples that you can see in the microscope. But if you just put them in a solution, they kind of eventually float down to the surface. And so we had to find kind of a bioadhesive glue to have them stick. So one of the things to keep in mind. And then on the analysis, the materials, as you saw, they're viscoelastic. They have weird properties. They're very heterogeneous. So how to interpret the data, there's not really a good model for most of those. What everybody does is interprets the data as a linear, elastic, homogeneous material. And a lot of the machines now will, kind of like the nanoindenters, will spit out a modulus for you so you know. And that's great, but you're losing a lot of information when you do that. You can't use Oliver Farr. It's not that kind of thing. So to calculate a Young's modulus, you model it as a linear, elastic, homogeneous, isotropic material. And this is the formula for a spherical tip. I had an equation for the pyramid cone tip. It's not showing up. So if you have a sphere on your tip, this is the formula to use. If you have a pyramid, sharp, or pointy tip, it's a different formula that you take the cone angle into account. If it's not showing up in the slides, let me know. I will make sure it's up tomorrow. I don't know. Is it in there? Okay, good. Excellent. You all can see it. I can't see it. A couple things to keep in mind. They're not linear, they're not elastic, they're not uniform. There's many ways of actually doing more in-depth analysis of cells. And we will do that the day after tomorrow. There's a day I'm talking about cell mechanics. I think it's tomorrow, so yeah. We'll talk about some of the more complex models that people use to model cells. Now the important thing is most of the time, I'll be honest, a linear elastic model is fine for what you're trying to do, right? So if you're interested in things on the length scale of kind of hundreds of microns and up in biological stuff, a linear elastic model of a cell usually will do an okay job. If you're looking at deformation of the cell or forces and things at very high frequencies, or if you're compressing and you're holding for a long time, then elastic models don't work. But for kind of a first order approximation, if you're looking at the example I have for the paper tonight is looking at cancer cells that are drug resistant versus those that aren't. As a first pass, linear elastic is fine. It gives us a number that we can compare. So today we'll do how to convert AFM data. So here's raw data from the AFM. This is pushing onto a hard surface, so it's not really indenting. So you come in, you don't feel anything. At some point you get on a surface, you push, you come back. And if you look, the raw data is the piezo motion by the deflection of the cantilever. So to get the force is pretty easy. We take the y-axis and you multiply by the spring constant. So how do I know the spring constant? First of all, I know roughly the spring constant because the manufacturer, when I buy it, tells me. So that's convenient. But there's actually a lot of variation. So you shouldn't use the out-of-the-box value because when they micro machine these kinds of things, the thickness is not that well controlled. So you can have a tip whose nominal spring constant is 0.2 newtons per meter. But if you look at the manufacturer specs, it actually varies between 0.08 and 0.5 newtons per meter. And so if you happen to get the really, really stiff one and you use the nominal value from the manufacturer, you'll get it wrong first. So the way you calibrate the cantilever, where's my physics person? So you let your cantilever sit there, you measure with the laser, and it's away from everything, and you watch it vibrate. And so I can either do this by watching it vibrate in air, or I can drive it, and it has a resonance frequency. And the resonant frequency is related to the spring constant. So the stiffer the cantilever, the higher the resonant frequency, the lower the cantilever stiffness, the slower it's going to vibrate. And so that's how we calibrate each tip and know the spring constant exactly. So that's easy for the y-axis. For the x-axis, as I mentioned, right? This is ballet. So if my legs are the piezo, and my arm is the cantilever, if I move down 1 micron with my piezo and my cantilever moved up 100 nanometers, then the distance that actually got traveled is 900 nanometers, right? Like, as opposed to here I've moved a micron, here I'm moving like less. So you're going to take the x-axis, the piezo distance, and you're going to subtract out the displacement of the cantilever. And that's what we are going to do in class in later, which sounds super easy, and it's not. So this is, once it's converted, that's kind of what the data looks like. Oops. If you look at it, so here I come in, and here I hit a really hard thing. Here I pushed into something softer, and then A I pushed into something really soft. this particular curve is after the conversion I just talked about. What they haven't done on this curve is actually put where the contact point is with the indentation. And that's the hard part that we talked about. So just a little bit, again, you need to convert stuff. And again, remember you don't know the contact point, so you're going to need to figure out the contact point. So just as an example again, this is actual raw data. So if here I pick versus here, right? The piezo here has moved 1 micron, right? And the tip has deflected 200 nanometers. So the distance the tip has traveled is actually 800 nanometers. Does that make sense? Yeah, so that's kind of where I wanted to end for this part. This afternoon, we'll actually get real data, do the conversion, kind of look at it. I think the data I have for today is high resolution force data, and I have some for tomorrow that's nano indentation data, because we can do models and look at it. I think from yesterday, most people haven't ever done MATLAB before. How many people feel really comfortable with MATLAB? Okay, good. We have a couple. It's good. Okay. Okay, for everybody else, no worries. I have the first thing we're going to do it in Excel. And then today, so everybody gets familiar with MATLAB, because it's a very useful tool, we'll learn how to import data into MATLAB and basically do the same thing on one curve in MATLAB. So I think that's a good exercise to do. MATLAB's a nice tool, particularly if you actually end up doing these kinds of things. Excel is great for like one curve at a time, but usually you have hundreds of curves, so you don't want to have to manually do each curve at a time. So that's where MATLAB is helpful. What tips to use for cells and soft tissue? So we talked about when you're indenting bone and teeth, you need a hard tip, so you use a diamond usually or something like that, and they have this very specific geometry. For soft gels and tissues and cells, obviously you don't want to use a diamond. First of all, it's expensive. So the nano indentation tips are typically reusable. You're using the same tip over and over again. For the AFM type measurements, you might use one tip for one session, but because the tips will end up getting proteins on them and things like that, they're a little bit more disposable. So for the experiments where you saw like the map where you had a cell and they were trying to map out how stiff the cell was over the surface, typically those are similar to the imaging tips we talked about. So they're silicon or silicon nitride. They're these weird pyramid shapes. That's where you're using the cone model analysis. And the goal of those types of studies is really to understand how the mechanical properties over the cell is different. So when you're looking at how the cell interacts with like just its individual matrix, if the nucleus is different than the cell, right, you're going to be mapping over it. The problem with doing that for just getting a modulus number for your cell is the model is pretty bad. So those weird pyramid tips are not cones. So that's one approximation that doesn't really hold. And secondly, because they're sharp, you get stress concentration at the tip, and that really breaks the assumptions of linear elasticity, small indentation, homogeneous, all that the model should be. But it's fine because that's not the point of those studies. The point of those studies is not to tell me that this spot right here is exactly 20 kilopascals. It's to tell me that this spot here is in the range of 20 kilopascals, whereas this spot here is only 2, right? There's a 10-time difference. And so for those, it's fine. Now, if you wanted to actually measure what is the mechanical property of my cell on average, what people typically do is use spherical indenter tips. So you can get tips where it's an AFM cantilever and they attach a colloidal, a little bead at the end. Typically they're made of glass or polystyrene, and their diameters vary from like hundreds of nanometers to 10, 20 microns. It depends what you're looking for. For most cell and small tissue samples, a good rule of thumb, what people tend to use is 5 micron borosilicate particle tips because they're readily available and they're glass, and so the cell doesn't really stick to it too much. If you want to be really if you have a sample like I was saying that's very, very sticky, you can also coat those tips with polyethylene and things like that to try to keep them from being too sticky. But usually glass or polystyrene if you want to, but usually glass will work pretty well. So that's typically what we use. And so when you're doing that, then you can use the spherical approximation, and the tip, if you're using like a 5 micron particle and you're indenting up to a micron or so into the cell, and you're doing your analysis in the first couple 100 nanometers of the indentation, you're still well within the limits of the assumptions of the model. So you're closer to small indentation, linear, homogeneous, all that stuff. And so those numbers tend to be a little bit what people think is closer to an average value for your cell. Does that help? So that's cells and indentation. Tomorrow, I'm going to talk a little bit about models of nanomechanics of cells, and we'll do a lab exercise where we'll actually use actual cell data, do the conversion, and then fit the model so you can see how well or not well these kinds of models fit to your data. So yeah. Questions? We're good? Okay. So the rest of this morning, I wanted to talk a little bit about molecular forces and how to actually measure molecular forces. Tomorrow morning, I'm going to talk a little bit about the theory of where these forces come from. And then the data this afternoon is actually from a molecular force experiment. But before I do that, I had another, let's see if people remember things from yesterday. So this is an AFM image, and this is an SEM image. I said SEM image of nanoparticles. And they're the same nanoparticles. And so my question is, if you look at these and you kind of eyeball what size these particles are, so this is 30 nanometers, that's 30 nanometers. On average, what's the size, roughly, if you look at this picture, guess how, roughly what do you think? Yeah, 20 to 15, maybe 20, let's say 20 nanometers. If you look at them on this picture, what's the size roughly do you think they look like? Bigger, right? They look bigger in this picture than in that picture. So the question is, knowing what you know about these techniques, why do you think that might be? There's multiple answers. So I'll start. Why do you think that particles, that's the same particles?
Gives exactly the surface information. This gives the force information, the force which is available surrounding the particle.
Yeah, so that's kind of getting, the biggest thing is, these are dry particle, completely dried out, and so what you're getting is very much just the surface of the hard part of the particle. Now, these particular particles have a polymer coat thing on them. That's not going to show up on electron microscopy because polymers are very low density things. So unless you really coated it and you look at it with high resolution, at this resolution, you're not really going to see it. It might look, if you zoom in and look, it might look slightly fuzzy on the edge. But they're also dry, so they're completely collapsed, right? And this is in fluid. So if you have a polymer on the outside of your hard particle, it kind of makes the particle look bigger. And so the difference between these two could be that the polymer has swollen in solution, and so the particles are bigger in solution than they are dry. And there's a couple other techniques you can use that aren't imaging based to kind of confirm that. So that's something that it could be. Now, if I told you that, no, actually, so that is actually, I think, this paper, that is what they saw. But it could be that actually this is exactly the same sample, they're both dry. What's one of the reasons why this might look bigger in AFM versus in an SEM? What am I using to image in an AFM? Yeah, it's tip, right? So if I have a fat tip, right, it's gonna make everything look bigger, because if I don't have a sharp enough tip, it's gonna make everything look bigger than they actually are. So that is one thing to keep in mind. But as I said, in this particular experiment, it was a difference between hydrated and not hydrated particles. So that's a standard thing people do with their samples to try to get an idea of like nanoparticles and size and things like that. So, are there questions? Does that make sense? So one of those things that you can look at in papers and get some information. Also, I think yesterday we talked a little bit about how a lot of people make nanoparticles for therapeutic application, and they publish these, they're like beautiful particles, they're all perfect, and they all have the same size, and then, you know, you put them in the body and they end up not working because you get this protein corona, protein gunk that's sticking to them. And so AFM is a nice way to actually assess that, because you can put your particles down, image them dry, you can add a buffer, image them in like just a simple salt solution that's physiological, just to see if like whatever you put on it swells. And you can add, you know, serum or something like that to see if any proteins stick to it, and if it makes how associated those proteins are. So along those lines, so proteins and things on surfaces, we talked about biocompatibility, right? You have a surface, proteins will stick to that surface. No matter what you do, eventually things will stick. A good example is a Teflon pan, right? When you cook, when you first get a Teflon pan, a brand new pan, right? I don't know if you've ever done that, but you put like water on it and it heats up, it just slides right off. You don't need to put oil on it, just everything just slides right off, right? And then over time, it stops being so slick. So there's a lot of reasons why that happens. One, you get scratches and things on it, so you've broken the Teflon coating, and so stuff will stick there. Two, the heat breaks down the Teflon coating, so again, Teflon. And then three, you always will get protein adhesion, and so if you really don't wash, and nobody can wash perfectly, you'll end up having some protein adhesions and things on it that over time will cause things to stick. So that's why Teflon, we think of it as like a super slick surface that nothing sticks to. And so there's a lot of people who would think, okay, this is great, we'll stick it in the body for an implant material, nothing will stick to it, we won't have a problem, right? But the problem is over time, proteins will stick to it, and then cells will stick to it, and there's a big immune response, because when they stick to Teflon, they don't just come down as a protein and stay like this. They denature and unfold onto the surface. And your immune cells are trained to look for unfolded proteins, right? If it's a nice little protein that looks the same in solution and it comes down and it stays in the same shape, your immune cells don't see it any different, so it won't react. But if it's all unfolded and everything, then you have a potential. So you can actually measure how well proteins stick to surface, how well different molecules stick or repel from each other directly using AFM. That's typically called something like higher resolution force spectroscopy because you have to do lots of measurements. We're at a scale where, particularly if you're looking at protein adhesion and unbinding events, it's a stochastic thing, so you have to sample multiple times to get good data. But the basic idea is you have your flexible cantilever, you bring it down, and you pull up, and you look at the forces that happen on a proton operator. I borrowed this from my old advisor. It was a good slide. Just so you have an idea of the kinds of forces that you could measure. Right, there's all these different types of interactions. You have dispersion, hydrophobic, thermal energy at room temperatures. Things like that is what So if you look at this is the forces that I would measure, that I would need to break those bonds. So if you look at a covalent interaction is much stronger than an ionic bond, which you all know from basic chemistry, but that is actually what it is. This is actually a nice table because it kind of tells you the distance of interaction, so kind of the size of these bonds. So they're pretty short range. And then this is a nice chart for like typical materials and interactions that occur with them. So one of the interactions I won't talk too much about, but if you're testing a material and you're putting it in the AFM and you're doing measurements, that always comes out as huge is hydrophobic interactions. So if you have a hydrophobic surface, like say Teflon, and I'm measuring the forces in fluid, like a water-based fluid, like a physiological condition, and my tip is whatever surface my tip is, right? As my tip comes, and then it gets close, it's going to have a huge pull because the surface doesn't want water on it, right? And so the water's in the way, and the tip is coming down, and the tip is a surface that isn't water. So it'll stick, and then you'll have to pull a lot of force to pull it back up. So just some examples of actual data that people took. This is a paper looking at streptavidin biotin interactions. So I don't know people. Okay, good. I see nods. So right. So this is a non-covalent interaction, but it's actually one of the stronger non-covalent interactions we know. So the nice thing, part of why I'm showing this data is one of the hard parts of these experiments is figuring out how to attach your molecule of interest to the tip or the sample or both. So there's a couple chemical schemes to do that, and one of them that's very common is actually attaching things using streptavidin-avidin binding. So you attach your molecule of interest to avidin, and you attach streptavidin to, your molecule of interest to biotin, you put streptavidin on a surface, then it'll stick to the surface, and then you can do it. But you have to keep in mind that if you pull hard enough, it's the streptavidin-biotin bond that will break and not the thing you're interested in. So this is a data where, so here they came in, they hit the surface, and then when they pull out, you can see different peaks that occur as things break. And this particular paper was looking at the difference between streptavidin biotin versus avidin biotin. So streptavidin biotin is stronger. It has more sites that it'll break. But as it broke, it actually pulls the molecule apart. This, I think, is one of those like seminal papers with beautiful data that everybody likes to reference. So one thing to note is that when people are looking at pulling apart molecules and breaking bonds in molecules and looking at adhesions, right? So you come down and you somehow, we'll talk about how that happens, but you come down, you pick up the molecule, and then you're pulling, and you get these adhesions. And the data that comes out of the AFM looks like this.
So you come in, and then you pull, and this is negative, and then that's positive. But a lot of times people will display the data when they kind of flip it, and they make the adhesion forces look positive, because all they're talking about is looking at the adhesion force, so it makes it easier to read the graph. But standard AFM measurements, adhesion forces is flipped. Does that make sense? So just something to keep in mind when you're reading papers. So this is the adhesive forces on retract. So titin is one of the biggest proteins. Here's what it looks like. So in their experiment, they had attached one end of the titin to a surface using silane chemistry. So this is one of those things, again, if you're picking out a paper to read, it's very common. I don't do surface chemistry, but I do like 2 different things every time, and it works for most things. So this is one of them. So the first one is you get either glass, or if you want mica, right? And you put silane, you look at it, it's silica, right? And then you use chemistry to covalently attach one end of the molecule to using silane groups to your surface. So that's one method. The previous paper used gold. And the other reason to do that is it's really easy to attach things to gold using file chemistry. So that's the other way to do it, and honestly, that's all I've ever needed to do. And so for gold chemistry, you can make a nice self-assembled monolayer of like something that has an amine group, and then you can bind things to amine groups. So at this point, you've attached one end of the titin, and it's sitting on your surface, and you come down, and you pick up with the tip the titin. So the question is, how is the titin getting stuck to my tip, right? And the answer is I'm not doing covalent attachment. It's not like my tip is actually covalently grabbing. It's, again, small scale forces. If you get close enough, everything sticks. So I push on with my tip. Now the top of the titin is adhered to my tip with intermolecular forces, and then I pull. And as it unfolds, that kind of force is smaller than the interaction with the tip. And I'm able to unfold the different domains of titin. And then this is why you end up having to do a bunch, is because at some point the force that it is using to attach on the tip is smaller than the force that it's being pulled, that you're trying to pull from the next event, and it'll unhook. And so from the data, you can look at a couple things. You can see that there are a bunch of peaks that are almost the same height every time. So if you look at titin, this is the titin, what it looks like. So it has these folded regimes like this, and then here's my AFM tip, so it's kind of sticking to the AFM tip. Initially, right, it starts pulling, and I get like, here, right, there's like little force, and then it pulls, and suddenly I unfurl one domain, and now I have kind of a flexible part, so I get almost no force until I start unfurling the next domain. So that's why you get this kind of classic sawtooth pattern. This is actually some old data looking at a single molecule. In this case, it was looking at the interaction of albumin. So albumin is the most abundant protein in blood. This is fun for students, right? So human albumin, human serum albumin, most abundant protein in blood. What is chicken albumin? Huh? What is chicken albumin? Everybody's seen chicken albumin. Egg white. Egg whites. Egg whites are chicken albumin. So human albumin in solution in your lab pretty much looks like a jar of egg whites. So anyway, so human albumin was placed on a probe, and then we took that and
and looked at how it's stuck to different surfaces. So why do we want to do this? Because these different surfaces, if you put them in the body, they will be in contact with blood, and albumin is the most abundant protein in blood, so we were interested to see how albumin would stick. So the red curve, that's gold. So there's a huge, a huge adhesion with gold. And that has to do with the fact that bare gold is slightly hydrophobic because of stuff in the air. So again, that's kind of what you get for hydrophobic forces. This is a hydrocarbon, so it's a nice uniform hydrophobic surface. So what you can see is in here it sticks, and then you get these peaks again from the protein itself unfolding. So what that's telling you is it's sticking to the surface, and it's actually denaturing some as I'm pulling on it. So this is one example, right? Every time I do it, it comes out slightly different. Because the hydrophobic layer and the protein, the internal hydrophobic groups inside the protein are going to unfurl to try to stick to the surface, and then you pull on it. As comparison, this is polyethylene oxide. And this is a nice curve if you're used to molecular forces, because this is a classic pull of a long chain polymer. So this isn't force coming from unfurling of albumin, it's force coming from pulling of the polyethylene. And so polyethylene is, I don't know if people are familiar, it's a common material and coating for implants to make them biocompatible. And part of the reason it works is it's a nice hydrophilic material that when proteins stick to it, they don't denature, they kind of stay in their shape. And so that's why it tends to be biocompatible. So that was the point of this study, was kind of looking to see the forces that would happen. The other thing to note with this is if you look at you can look at the magnitude of the forces, you can look at the range of the interactions, and then if you look at the area under the curve, it gives you an idea of the adhesion energy. So again, the energy is a lot more here than it is here. There we go. So that's AFM. I briefly wanted to touch upon a different technique for measuring the same kind of stuff called surface forces apparatus. So surface forces apparatus is actually an older technique. It was, I think, invented, it's on my slide, I want to say it was the 70s. So it's been around longer than AFM. It really is to look at the nanoscale interactions between surfaces. So you can't really do kind of single molecule experiments because you don't have a sharp tip, but you can do very high resolution measurements on surfaces that are really small. So classic examples include looking at things like how phospholipid bilayers interact with each other to fuse, to look at vesicle fusion. So the way surface forces apparatus works is it has crossed cylinders here of mica. So again, if you remember from yesterday, mica is atomically flat, which is a nice surface. The other thing is mica is clear. So it's the two optically clear flat surfaces that I'm bringing together. And similar to AFM, as I'm bringing together, I can measure the forces between them. The nice thing with SFA is because the mica is clear, I can pass light through it, and as they come together, if I know enough about optics, I can actually measure the distance between the two surfaces by looking at refractive fringe patterns on the thing. So unlike AFM, SFA does give you the displacement exactly. So that's one of the advantages. Personal experience, SFA experiments are messier and more annoying to set up than AFM experiments, but that's just me. And SFA instruments tend to be a little bit more expensive. So this is a classic example of an SFA experiment. This is trying to understand fusion of vesicles. So they had their flat surfaces and they put phospholipid bilayers on both sides. And then as the layers come, you can see when they start to fuse together and you get force interactions. You can also see the longer range interaction forces that occur that kind of help to keep vesicles apart or have them come together. Once they're within proximity of each other, they're going to suck to each other and tap. So again, just to look at the geometry constraints, this is SFA versus AFM. So AFM is a sharp tip, SFA is kind of surfaces. But in terms of the magnitude of forces and the distance range they measure, it's very similar. So typically, surface-surface interactions are a little easier to study with this kind of an instrument. Single molecular forces and that kind of thing is easier to do with AFM. I will say that there's a lot more AFMs out there commercially than SFA instruments, just because these are a little more expensive to set up than these. If you want to do surface-surface interactions and you don't have an SFA, the easiest thing to do is go back to taking one of those large particle tips, the spherical tips, and then do the same thing they do in an SFA experiment, but use that in your AFM. So you might be wondering, like, this is cool, I can pull on molecules, I can look at molecules sticking with each other, but why do I care? So as I've been kind of alluding to, for biomaterials and understanding biocompatibility, the biggest thing to understand is how proteins stick. Cells don't stick to synthetic materials, fundamentally. They don't have receptors, right? Like, how does a cell stick to a surface? It uses integrins, and as we talked about yesterday, right, there's mechanical transduction. A surface, if I have, like a hip implant, right, it's titanium. Cell doesn't have receptors for titanium. What the cell does have is receptors for proteins, that the proteins themselves will stick to the titanium. As an example, this is just to understand how proteins stick to things. So this is albumin, one of the plasma proteins. So I have my implanted material, and now it's in contact with blood, right? Because I had surgery, I had to put it in. It's got blood everywhere. What happens? So your blood is like 45% cells, but the liquid part is really complex. And so this is a high area of research, both on the basic science side and just for application purposes. Serum is a really complex solution of all sorts of different proteins, growth factors, and then ions. And if you're a materials engineer person, it's a terrible, terrible solution to put your nice engineered material in. So you spend all this time making a beautiful material, and now we're going to put it in this warmish temperature, really salty conditions, right? We are 0.15 molar. That's pretty salty. And so salt tends to attack things. And then most importantly, it's full of sticky, large proteins. One thing to note is the majority of these, if you look at them, have a net negative charge. So why is that? Like your protein, why does your protein have a charge associated with it? Yes, right. So they have charged groups that are dissociating, so negative charged groups. So usually carboxyl, sulfate groups, all those things, right, form in solution, they dissociate, and now I have a negative charge on my protein. So most of these surfaces are negative. So perhaps one of the strategies would be, well, if most of the surfaces are negative, or most of the proteins are negative, if I make my surface slightly negative charged, then hopefully they won't stick. Now the problem is, as you know, this is like a complex molecule, and so while the net charge on the protein might be slightly negative because it has more carboxyl groups than other things, you know it also has positively charged parts, right? It has amine groups, things like that are positively charged. So if you try the strategy of making your surface positive, now or making your surface negative, now the positive charged groups are going to stick. It's the same thing. The idea is like they're hydrophilic. So if I put in a hydrophobic surface, they shouldn't stick. That's true that in this conformation it's hydrophilic, but the inside right here is a hydrophobic object. Okay. So that's why from an engineering, coming up with ideas of how to make a material to work in the body is very difficult. So what happens? I put my nice, clean, beautiful material. I have protein. It comes, so I have it, they flow. And I get attractive forces that kind of slowly bring proteins towards the surface. Once the protein is in a certain range of the surface, I will end up having fairly strong attractive forces that will bring it on. Depending on the surface chemistry, the protein will then denature or desorb or just stick to my surface. And this is what the hard part of making a biocompatible material is how do I make a surface to try to prevent it from completely turning into spaghetti? And because when that happens, platelets come in. So there's now this sticky stuff on my material. So platelets will come in, and I will get a blood clot, and that will get me inflammation in the cardiovascular system. You'll get neonatal hyperplasia, bad things happen. So what can you do to prevent this? Do we have any ideas? So I don't know everyone's background, so I don't know if you've thought about implants and different materials people are using, but what are some strategies people do to make implants more biocompatible? Let's start with, everybody must know someone that has either a hip or a knee implant. That's like a huge number of people have hip or knee implants. What are hip and knee implants made out of? Titanium, stainless steel, right? They're made out of metal. Why do we make them out of metal? Yeah, it's a lot of load, right? Like, we need something that's strong enough that, not that I'm saying I'm fat, but I need something that can withstand my weight, right? So that's why we use metals. And I think I mentioned it briefly this yesterday. One of the things you want to do when you want to look at materials and things is the mechanical properties of the material itself. So kind of like at the beginning, we were talking about teeth and whitening and the dentin versus enamel. You want to try to match your material to the mechanical environment. Because if you don't, right, and this happens, if I have titanium, or actually stainless steel, and it's really hard, and compared to bone is softer. So if I don't get good attachment, I'll get huge stress concentrations right where the bone meets with the implant. And that causes a host of problems. So I have a nice metal surface. So obviously, things stick to the metal surface. So what can I do to my metal to treat it or do something to prevent, cells from coming in and sticking, prevent bacteria from coming in and sticking to it, prevent immune cells from having an immune response? Does anyone know what currently gets done? Coatings, different coatings, right? Yeah, everyone's got it. So if you ever look at an implant, if you look at a hip implant, the stem where it goes into your bone, if you look at it, it won't look shiny. It'll look matte. So those stems have a coating on them. The coating is actually hydroxyapatite. Not all of them, but typically it's a hydroxyapatite. And that allows for, over time, the bone to grow into the material because the hydroxyapatite at a protein level kind of looks like bone. And so proteins will stick to that material the same way they kind of do to bone. Now, obviously not exactly, but that's the goal. Now, on the flip side, on the side that goes into your hip, you don't want bone to grow. And so typically those surfaces, unless you have a metal-on-metal implant, that's where polyethylene comes in, some kind of plastic, to have less friction and also okay protein absorption, because a bare metal surface will have protein stick to it. So that's one of the things. So what's another implant people get? Something else people get. Anybody? Huh? Silk materials. You mean like, yeah, so that's actually a good point. That's like sutures and things are. Yeah. So silk, it gets used currently for sutures. There's work on using them for different other applications. So the nice thing with silk is it's super strong. It is relatively biocompatible because that is a natural material. Raw silk from silkworms actually is not biocompatible because the silkworm makes silk and then puts a coat on the outside of proteins to make it hydrophobic. So the way they treat silk to put it in materials is actually like take out that and then you only have a protein that looks more like a natural protein in the body. There's also silk coatings people are working on for that same reason. But what's like a big class of materials that gets used? Composites, yes. Okay, movie stars, what kind of implants do they get? Well, yeah, they get teeth that get gold, but silicone, they get silicone, right? There's breast implants, all sorts of soft materials, right? So silicone is a plastic, it's hydrophobic. If you look at breast implants, they're like little bags, right? The silicone is on the inside. First generation implants, people used to put silicone straight in the body. There were horrible results that happened, right? There was a lot of immune response. And to this day, if somebody has a silicone implant and the implant bursts or there's a crack in the outside and the silicone comes in, you get horrible immune responses. So the way they currently do it, right, is they make an outside bag that has different properties to try to make them more biocompatible. But slightly stiffer silicone gets used for nose reconstruction of cartilage, that kind of thing, because that stays as a more solid piece, so you don't have as much problems with little pieces of silicone getting everywhere. So composites, I heard there's a lot for teeth, right, that do gold, all sorts of different metals. Right? But typically what you do is you take your material that has kind of the right bulk properties, and then I treat the surface to try to make it more biocompatible. So besides chemically modifying the surface, what's another thing that, if you go back to the hip implant, what's something you can do to promote or stop certain types of adhesions and things? So it has a lovely surface coating. What else matters? So the side that rotates, right, is very smooth. Has anyone looked at what's the size that goes into the bone? It's really rough, right? It's like not a smooth surface. Because in that case, they're trying to get more proteins to start growing bone. So surface topography matters also. So it's a combination of molecular interactions and the molecular interactions with that topography. So a couple things if I want stuff not to stick, right? I can try all sorts of stuff. We said you could try putting charge on the surface. You could make it hydrophobic, hydrophilic. One of the easiest ways to do that is using steric hindrance. So I'm going to put polymer layers on top that basically push things away, right? And so this is kind of a classic example. Again, this is one of those techniques that when you first think about it, it's great. I'm going to put a polymer layer, I'm going to put a layer of polyethylene, and things shouldn't stick. But if you look at the energy landscape, you'll actually see that things do stick. Typically what happens with polymer layers is you can either have protein sticking kind of towards the top of the layer, or eventually, if you put enough force, it gets down and it'll stick to the surface. So most of your surface coatings and stuff, that typically is a problem you try to avoid. But the more flexible ones will tend to keep proteins kind of at the top of that polymer layer. And the nice thing with that is if you choose your polymer correctly, basically your protein gets trapped, and that's why it stays in its shape. Because it's a hydrophilic kind of polymer, the protein stays in its kind of hydrated state. It's just stuck on the surface now and not moving around. So that's kind of a strategy people do. And this is important for material surfaces, for interactions with the body, but also all those nanoparticle strategies where people are trying to make drugs out of nanoparticles. Same principles apply. So you want your nanoparticle to go in the body. You don't want all the particles to clump up together. You want them to kind of stay and go where they need to go. And so a typical strategy is taking your nanoparticle and coating it with some kind of hydrophilic polymer brush. And that will keep them from sticking to each other and having weird proteins stick to them. So a couple other strategies we've covered. So one is having a topography, if it's smooth versus rough. If it's a smooth surface and it's having blood flow, I constantly have something trying to push things off, so that might be a strategy you want. If it's with bone, maybe you want it to be rough, again, to kind of interact. If you're trying to make material like a suture or something, right, you want something with pores that stuff can go in. And then you can make the surface charged. That is a strategy a lot of people have tried for implant surfaces, but it turns out not to work. And that's kind of what we alluded to, is that your protein might have a net charge, but it will always have some groups that are charged in the other direction, so things will stick. Having your surface be charged, having ionizable groups on it, does work pretty well for small colloidal particles. So for a nanoparticle type strategy, that is something people do. But for larger surfaces, it hasn't looked like it worked. Having things be hydrophilic or hydrophobic, depending on what you're trying to do. And then the latest strategy people are trying to do is having the surface mimic physiological conditions. So putting groups on your surface specifically that look like the thing you're putting in. So maybe coating your implant with albumin to start with. So there's albumin already there. It doesn't matter. So, that was fast. So this afternoon we're going to play with some data. So I was going to talk a little bit about the data we're playing with. This is data I have because it's from my thesis. Which is from a while ago. That's okay. Okay, so my work in grad school was understanding the molecular forces in cartilage tissue. So cartilage is, the tissue on the top of your joints. It's the shock absorber. There's no blood flow. There's no nerves. It's, from an engineering point of view, it's a great material. There's very few cells. There's like one cell over here and then like one cell, they don't touch each other. You can almost, or at least we used to think, you can kind of ignore the cells. Most of the mechanical properties of the tissue, almost all of them are due to the matrix itself, not the cells. So that's as opposed to something like cardiac tissue. Cardiac muscle is almost all the mechanical properties are due to the cells. So yes, they have some collagen and elastin and things that the cells stick on, but the majority of the properties are due to the cells. If you take out all those cells, the property of what's left is much, much smaller than the cells themselves. Whereas cartilage, if you took out the cells, is very little property difference. So cartilage is this gel, and it has collagen in it, and then it also has proteoglycans. So that's what we were studying, is these big, I showed pictures of this molecule because it's so pretty, proteoglycans that are found in cartilage. So in cartilage you have what's called aggrecan. Aggrecan has a protein core and then a whole bunch of glycosaminoglycan side chains. Glycosaminoglycans are like, it's a long chain sugar. So it's a bunch of sugars hooked up together. And they have carboxyl and sulfate groups. So when I put them in solution, they dissociate, and I end up with a net negative charge. And if you look at this, each of these chains has something like 40 sugars. So each chain has 40-ish negative charges on it. So this is very highly net negative charge. So tomorrow, I'm going to explain a little bit about the theory of how do you measure, how do you interpret the force. But for now, what we have to think about is, in your tissue, I have lots of these all over, and when I push on the tissue, they come together, they're highly negatively charged. If you think back to basic physics, two negative charges coming together want to push apart. And so that was the theory, one of the theories is that 50% of the modulus of the properties of the tissue were due to this molecule. So due to the fact that this was highly negatively charged, so when I push, it pushes back. The other part was like water and collagen, right, other things. So in compression. So we were trying to measure at the molecular scale how much of contributions could this molecule really produce, and measure it directly, and then build some models to see if we were right or wrong. So we did a bunch of individual molecular data. The data you have is from an experiment that looks exactly like this. So we had engrafted the molecules on the tip and on the surface at a fairly high density. There's one molecule for 25 by 25 nanometers squared. And so if you think about the chains are 40 nanometers long-ish, 20 by 25, they're really close together. And this actually is close to the density that's found in your tissue. I will say personally, from experience, that was the trickiest part of the experiment, is how to get these molecules that don't want to be next to each other to stick at a density that's close to what they are. So that was, in the body, what happens is these N groups are actually connected to another protein. So that's how the body keeps them together. Okay, so then I brought the tip and the surface together, and we measured the forces. And when I did that, this is what I measured. So you come close to the surface, you push in, and you push back. And you get nothing sticking. And even at very high salt concentrations, this is a much, much higher salt concentration in the body, you still get pretty large repulsive interactions. At this range, when I have so much salt, the salt shields the charge interactions. And so most of this is just from steric hindrance, right? It's from the fact that I have big molecules on low surfaces and I'm pushing on them. At lower ionic strength, what we saw, I have the data, but what we saw was that actually up to almost 800 nanometers, you would see huge repulsive forces. So even more than that. So if you went up to like a micron, you could, as they were coming together, you could feel the repulsion between them. So they really don't want to be next to each other. So this is the experiment, what it looks like when I just do this. I come down, come back up. The data I have for you to play with was an experiment where we went down, held on the surface. I think the data you have is 10 seconds, I think 5 seconds. It says on the data. So come down, wait, and pull, just to see if we get adhesion. And to our surprise, we did. So you'll see the data and you'll see what it looks like. And then we'll talk a little bit about why that might be, right? So I can push them together all I want. They don't want to be next to each other. But if I apply enough force and I hold them together, they do stick. And so that's one of the things with intermolecular forces, as I explained. If I put enough force and I put things together, eventually everything sticks. So it's a problem for things. So in the experiment, we had a tip with a certain radius, and I have molecule specs. So today, that's what we're going to analyze. That's kind of all I had until we did the experiment. So are there questions? Or questions about like single molecular kind of force experiments? Otherwise, we'll come back and do the experiment in the lab. Questions about this molecule? Because this is what we're actually going to be studying. No? Good. Okay. Oh, yes.
The type of interaction between a result of two molecules.
Yes.
Or maybe a larger number of two.
Yes.
Are both the larger molecules.
Yeah.
So the force is also real.
Yes.
So what is the minimum force you are read?
So with AFM, the smallest forces we can measure are about 5 to 10 piconewtons. That's kind of the resolution limit. If you get very soft cantilevers, that's what you do. But if you get very soft cantilevers, thermal fluctuations, there's at least 5 piconewtons of thermal fluctuations, so it's really hard to measure anything smaller than that. Yes, yeah, so for really small forces, that matters. This afternoon, after the thing, we'll talk about optical tweezers. Optical tweezers can measure like 1 piconewton and lower. So, or 1 piconewton to 1 nanonewton. So they can measure those very, very small forces that might not have the resolution with AFM. In terms of the upper end, that's where AFM, you can put a really stiff cantilever, right? But yeah, the limit on the bottom end is, I'd say like 10 piconewtons.
What is the material used for this?
There's still silicon or silicon well, typically the softer one is silicon nitride. And typically the very soft cantilevers are the ones, if you remember the picture, they were V-shaped because you can make them very thin and really long. They're hard to work with because they're very soft. So as you're mounting the sample in, if you touch it, it'll break off. So it takes a little bit of practice, but once you have it in, it's actually not that bad. I think that's also something people think of AFM is that you break tips all the time. I think you break tips in the first time you learn. Usually you break 1 or 2, but once you learn how to use it, you don't touch the tip. So. Right, so for analysis is very important. Like in terms of the measurement, I can measure all sorts of different thickness of things, but to understand the results, I need to know what my material. So this, for instance, that's actually a good point for everybody. I didn't measure the density using AFM. So I end-grafted all the surfaces, and then once I had my nice surface and I did the measurement, I took the surface and I used chemistry to break the bonds of the molecule from the surface, lifted it out, measured how much I had. Yeah, that's how I got this number of how many molecules I have. It's easy with this particular molecule because there's a colorimetric assay to measure the sulfate groups. With other molecules, it's a little trickier. So there's other techniques to do that. One of the techniques you can do is actually, instead of coating your whole surface with the molecule, you pattern areas where the molecule is, because then you can compare the blank surface to where your molecule is, and you have a control right next to it. You always have a control. Yeah, that's a good point.
Surface chemistry,
yeah. Right, so surface chemistry lab does their own surface chemistry to get attachments. However, if you've never done this and you want to do this, I highly recommend starting with trying to attach things to gold, because it's very easy. You get a self-assembled monolayer of amine groups. There's a thiol end of an amine group and a hydrocarbon, and it creates a nice amine layer. And then use sulfo-NHS EDC chemistry, which is to cross-link a carboxyl group to an amine group. And so what happens is every protein always has at least one amine group, one carboxyl group, and so you, so as long as you're just trying to attach the ends, it's not that bad. And so the actual attachment chemistry is almost always, if you're directly attaching, it's almost always using carboxyl to amine binding. It's just a matter of how to put either a carboxyl group or an amine group on the surface you're testing. With glass and mica surfaces, you use silane chemistry to get those. But yeah, that's more standard now. Everybody does that. Now, one thing I didn't mention, and that's actually a really important point for everyone, is that for these molecules, they're big. They like to stand up because they don't want to stick to themselves. For a lot of proteins, if I were to just directly attach the protein onto my surface, it will unfurl, and that's not what I want. So what people typically do is they attach a polyethylene glycol linker, like a flexible arm, and then they attach the protein to the arm. So then I kind of have, it's like a fishing pole. I have a polyethylene line and then a protein at the end, and I'm fishing. Because that way it ensures that the protein stays nice and round, and it doesn't like stick on the tip.
Ma'am, the adhesive force is due to these two reasons. That is, one is negative or positive charge, another is that hydrophilic or hydrophobic. So my question is that can you control the negative charge or positive charge of the cell by fractional field?
Yes. So yes, and actually I'll talk about that tomorrow morning. So this experiment, the way we did it is we measured it in different salt concentrations, because if you put enough salt in there, you shield out all the charges. The other approach is you can change the pH, so you can titrate, because these are dissociations of carboxyl groups and sulfate groups. I know what pH that happens at, so as long as I'm in the range where they're not negative charge anymore, I can turn it on and off. So that's the other approach people do. In terms of if you have a general surface and you don't know, you can also give the tip a charge relative to the surface using an external potential. And that is also an approach that people do. Tomorrow I'll talk a little bit about gecko feet and how they stick to things. And that is one of the ways people use to check does it work with like a static electricity versus not. That's one technique. But yeah, so typically again, it's always having a control. So you need to compare it to something. So usually you do the measurement in different conditions and things like that. So you can sort of turn on and off different molecular forces and isolate different ones. Yeah. Yeah, so implant materials, a lot of them are ceramic coated, so the hip and orthopedic implants, they have ceramic kind of nano and micro, but now it's like nano ceramic coatings to get them to stick. Yeah, on the top, like where it goes, yeah, so they tried many things for that. One of the issues with friction at surfaces is they start out really good, but over time there's always wear. And so that's why implants don't last forever, even when you get them replaced. And the idea with the more softer polyethylenes and plastic is they wear, and then you take it out and you just replace that. You don't have to replace the whole, just the top part. Same in the knee, it's like looks like a meniscus kind of almost. So you just replace that. You don't have to replace the whole. Yeah. You can make the tip of the cantilever a composite material that is a little bit more tricky. The way I've seen it done is typically people will get a tipless cantilever, put a little bit of glue, and go pick up a piece of composite. I mean, if you're trying to measure the composite compared to some other surface, yeah, that would work fine. If you want like high resolution, you have to like sharpen things, so that's tricky, but it's doable. Oh, how to nano pattern or micro pattern. Micro patterning is super easy. You use soft lithography techniques. Same thing as like for making computer chips and stuff, but with soft lithography I have one master mold and then I can use PDMS stamps to stamp my protein in different things. Nano patterning is a little trickier. Some of the techniques people use involve electron microscopy, like beam lithography to get nano patterns. Otherwise they use self-assembled systems that make nano patterns by themselves. So if you mix two different materials, when they form, they'll make little inclusions of different materials. But yeah, for most of what I was describing, it's a micro pattern. You want like an area with the molecule, an area without the molecule. So if you micro pattern where the molecule goes. So for nano or micro? For nano patterning, what I've seen is for surfaces for biocompatibility, people will try to either put a texture or a chemical modification using nano patterning, and that's much more just like mixing the right materials. So when they self-assemble, they make like these fractal kind of surfaces at that nano scale. For nano patterning with typography and nano ceramic material like hydroxyapatite, they take the stems and then they basically have a whole bunch of hydroxyapatite particles and they spray it on and stick it on a surface. So that's how most of the movies are made. They're like sprayed onto the Yep. Are there other questions? Okay, so this afternoon we will play with data and we will try to answer whether the molecules stick together, what is roughly the adhesion energy, and estimate the number of molecules interacting and what the force per molecular pair should be roughly. So, I think that's it. Otherwise, I'm here, so if you have questions. Eat lunch. Oh yeah, make groups. Make groups. Start talking amongst yourselves.
Not the same.
Wait, have you already made groups? Have people already made groups?
Not you to be a part of this.
Oh, yeah.
So that you will mingle and you can just
Don't be shy.
okay,
Each other.
Please go around the. Can you make a group now? So that you start working on it.
Wait, are people in groups already or not? How many people, who does not have a group? No, everyone has a group?
The people of external no group.
What?
The external people have no group. I think internal people have a group.
The external people are moved up. Yeah, okay.
Time ask, na? Who have a group, you not group.
The point, I think, was to get the external people to mingle. So
we'll make like there's a four
yeah.
Yeah, that will be
Yeah,
fine.
very fine. Yeah.
Can we just form groups based on our interests?
No. Because I want all of you to communicate.
And every group should be containing different field. I think it will be better.
Yeah. But there, if you start, all the external people are kind of.
Because physics, chemistry.
Yeah. So only external we can do it
are we doing randomly? Are we just counting off? 12 groups, right? Okay, so everybody count.
About single molecule mechanics. So we have few topics in single molecule mechanics. As I discussed yesterday, we have cellular polymers, the mechanics of protein, single protein, DNA, single stranded DNA and double stranded DNA. So we have a few range of topics in single molecule mechanics, but today I'm going to talk about motor proteins. So before I go on to the presentation, there's a small video just to appreciate the nano machines. So these are one of the most fascinating nano machines ever.
Occurring in biochemistry and cell biology over the last 2 or 3 decades. What biologists, molecular biologists, cell biologists, microbiologists are discovering is that at the level of individual cells, there are little tiny examples of nanotechnology, little tiny machines at work. The flagella motor is the one that Behe made most famous. It's a rotary engine that powers a whip-like tail, protein tail, that functions like a propeller, and it moves the bacterium through liquid, enabling the bacterium to essentially track down its food supply. And this little machine includes a rotor, a stator, a drive shaft, a U-joint, bushings, bearings, and a whip-like tail that functions like a propeller. And the machine in some bacterial systems turns at 100,000 RPMs in one direction and can reverse direction on a quarter of a turn and turn 100,000 RPM in the other direction.
The bacterial flagella is a true nanomachine, about 40 nanometers in size. It's amazing. I mean, E. coli, salmonella, which are kind of our model systems for the bacterial flagellum, can propel the cell about 20 lengths per second through a very viscous medium, like water to these organisms. And you extrapolate that to human scale. 20 body lengths per second, 6-foot person, times 20, 120 feet per second. Mark Spitz or Phelps would be setting records with this type of culture.
It's hardwired into a signal transduction circuit that allows the bacterium to sense changes in the sugar gradient in the surrounding liquid.
This signal transduction system is actually a short-term memory system where the cell is, if it's going in the direction of an attractant, a nutrient that it can use to metabolize, it follows that chemical gradient. If it's a repellent, it will sense that and move in the opposite direction. So it's more than just this engine.
It's an extraordinary piece of nanotechnology. It's high-tech in low light. And so just by spotlighting these extraordinary pieces of nanotechnology inside cells, and the flagella motor wasn't the only one by any means. Behe, in a sense, opened up a window for people. He opened up the black box of the inner workings of the cell and said, look, this is much more complex than anything that the early evolutionary biologists had envisioned. Darwin knew nothing of this type of nanotechnology in cells, and at the very least, we've got to come up with an explanation for this.
So there are actually beautiful videos about this flagellar protein online. You can check it out. So in E. coli, this flagellar protein, I think with this video you can appreciate the structure. So you have a motor, you have a stator, you have a propeller. It's like a proper machine, and it can rotate at 100,000 RPMs, and within a fraction of a second it can change its direction in chemotaxis and quantum sensing mechanisms. Okay. So when we come to human motor proteins, so we have myosin, kinesin, dynein, and ribosome and RNA polymerase are the most well-studied motor proteins. We also have proteins that move, but these are the proteins which actually move from one place to the other. So they have varied functions in the cell, like cargo transport. So they enable transportation of cargo, the vesicles and different organelles and other molecules within the cell from one part of the cell to the other. And in contraction, so most of the cells contract, so in contraction myosin plays a major role in contraction of the cell. And ribosome and RNA polymerase, you must be knowing, they travel along the DNA and they do transcription and protein formation. Okay. So these are the different motor proteins, but due to shortage of time, I'm going to just talk about, I'm going to select two motor proteins. The myosin, which is a very well-studied motor protein as on date, and kinesin, and maybe give a short intro on dynein. So I suggest you guys to go back and at least take a look at the videos of how these motor proteins, these are called the molecular motors of the cell, how they work. They have beautiful videos online which they have animated, and so you can look at them to appreciate how these motor proteins are working inside a cell. Okay? So myosin, myosin attaches to, so when I talk about motor proteins, I have to talk about the cytoskeletal structures. You have three types of filaments within the cell. Can anybody say what are the three filaments? Three types of filaments? Actin, filaments, microtubules, and intermediate filaments. So the myosin interacts with actin. The kinesin and dynein, they walk along microtubule filaments. Okay, these filaments are continuously forming and they're polymerizing and depolymerizing along the entire length of the cell. So, and ribosome and RNA polymerase, they work along the DNA and RNA strands. Okay. So this is, I have few pictures of kinesin here. So one is the structure of the kinesin protein. So the X-ray crystallography studies have made possible to greater resolution of these motor proteins. So we can exactly find out which part of the protein works, contributes to what part of this transport phenomenon. So this picture here, it's a cartoon of kinesin molecule attached to its cargo. So the cargo can be several sizes of its own size. It can carry cargoes of huge sizes irrespective of its size. So here it has a cargo attached to it, and it carries the cargo along the microtubule filament. Okay. So this is a kinesin structure. So there's a neck linker region. This is the region which attaches to the microtubule filament. They have they have specific orientation. So kinesin travels from the minus end to the plus end. Basically kinesin moves from the center towards the periphery of the cell, whereas dynein moves from outside to the inner part of the cell. So this way there's a directionality to this cargo transport within the cell because of kinesin and dynein. Okay. So and you have a neck region, a hinge. Then you have a stalk, then you have this tail and light chain. This is a region where which attaches to the cargo, and these are the two heads that are shown here. So these are the two heads that actually do the walking movement. So this picture shows gives you a pictorial representation of how this walking is done. So there are basically two heads here. So one head is attached to the microtubule, and there's an ATP molecule. So all this happens through ATP hydrolysis. The energy for this walking comes from hydrolysis of ATP. So when an ATP molecule is bound, there's one head is attached, the other head is actually not attached, it is in an unattached state, and ATP hydrolysis takes place, and when another ATP molecule binds to this head, actually this head is detached and this head is thrown forward. So basically the kinesin moves hand over, it's called a hand over hand mechanism. So it moves like this. So
one head is attached, the other head is detached. When an ATP molecule gets attached, this gets detached and this is thrown. So all this happens in a coordinated way. This hand is thrown in front and this gets detached and this gets attached. So that's how the kinesin molecule walks along the microtubule, and as it walks, it carries the cargo to the wherever it has to take. Okay. So mostly one kinesin molecule is attached to one vesicle or one targeted cargo, but sometimes the kinesin molecule might get stalled because of the filamentous network within the cell. So in those, when such a kinesin molecule gets stalled, there are other kinesin molecules which gets attached to the cargo and generate more force for it to carry on with the movement of this cargo. So unlike dynesin, dynesin has a very different movement pattern. Some dynein molecules actually exhibit this hand-over-hand mechanism, whereas some dynein molecules they are shown to move like a worm. So they move back and forth. So it moves like a worm along the microtubule filament, but it's in the opposite direction. So it's from the So it's from the periphery to the center of the cell. Okay? So these kinesin is also very well studied, and dynein is being studied, and we have many information coming up on dynein molecule also. So when I talk about myosin, so myosin are also very well studied motor proteins. Myosins are present predominantly in muscle cells, and we also have, there are many, myosin is a superfamily of proteins, so we have various isoforms of myosin, myosin 1, myosin 2, myosin 4, myosin 5. So myosin 2 is found in muscle, and other myosin isoforms are found in other cells. Okay. So myosin 1 and myosin 2 is actually the one which is actually the reason behind the contraction of muscle cells. So this is a pictorial representation of the cross-bridge cycle in myosin. So myosin also has, if you look at the structure of myosin, it also has two heads attached to a next region, and which is attached to a light chain. So the head region attaches to actin filament. So the actin filament has myosin binding sites. Okay. So in the default state, myosin is actually unattached to the actin. So, and an ADP and phosphate molecule is bound. When the ADP and phosphate molecule gets hydrolyzed and the phosphate molecule is released, the energy produced causes a power stroke. There is actually a change in conformation of the myosin head. So the head actually undergoes a conformational change. It becomes like it bends towards the actin binding site, and it attaches to the nearest actin binding site as shown here. And when it attaches, the phosphate molecule is released, and this at this step, so you can just imagine the actin to be like this and the myosin here. So initially it is like this, and when ADP and PI is bound, it undergoes a conformational change, and it actually moves like this, binds to the actin, and when the PI is released, the energy produced causes a power stroke, so it actually pulls. So it's like contraction. So it's not like one myosin actin attached to actin. So there are many myosin molecules which are attached to actin. So when this happens, the entire the actin molecules are tethered to the membrane of the cell. So you can just imagine when these myosin filaments are pulling from each other, so you can expect the contraction to happen. So it's like a crossover mechanism. It's called a sliding mechanism. Okay? So it's called a sliding mechanism. So the actin filament actually slides over the myosin filament and causes contraction. And after this power stroke, again attachment of an ATP molecule detaches the myosin head from the actin filament. So this goes on and on. So there are many myosin molecules which are undergoing this cross-bridge cycle. So due to this cycle, you have the contraction and relaxation happens within the cell. And the other myosin isoforms, like the myosin 1 has a different structure. It has an extra light chain region,
and it also helps in the contraction of the cell. And myosin 5 actually works like kinesin, like it also helps in cargo transport within the cell. So, okay, we know the motor proteins, they carry cargo transport within the cell, and all this is cell biology. So what is the mechanical characteristics that could be studied on this motor proteins? So I said X-ray crystallography studies give us the structure of these proteins, and assays like in vitro motility assays show the movement of like we have fluorescence imaging. So and motility assays which actually show us how these motor proteins are moving on these filament networks in what direction and all that. And what are the further mechanical characteristics that we could gather from these motor proteins is like the conformational changes. What is the conformational changes that these proteins undergo during this during their motor pattern? And what is the pattern of movement? Is it like a hand-over-hand mechanism, or is it a sliding mechanism, or it is a worm-like movement? So what is the pattern of movement of these motor proteins? Then what is the step size? Step size is what is the distance traveled by these motor proteins in a single step. Okay, so it's in the nanometer range. And what is the force? What is the force during this one single step? So it will be in the range of piconewtons. So these are the things that we would like to study using some mechanical techniques like optical tweezers. So these in vitro motility assays are mostly qualitative experiments where you have a cover slip, you have actin filaments or microtubule filaments attached to this cover slip, and you have your ATPs, and you then put your fluorescent tagged proteins, and you using imaging techniques you actually see how these filaments, the proteins are moving along the filament in what direction and all that. But optical tweezers and AFM also to a certain extent will give us some quantitative figures on what is the step size of these proteins and what is the force experienced by these proteins during a power stroke and all that. Okay. So some of the figures is like just to give you the scale. A step size of a kinesin is found to be around 8 nanometers. So a single hand-in-hand mechanism. So it travels around 8 nanometers in a single step, and it experiences few piconewtons force during this movement. And for myosin also, it's around. I'm not sure about the number, but around it's like 11 to 12 nanometers that is a sliding. That's the distance that an actin filament slides with a single myosin molecule. So these figures have been possible thanks to single molecule mechanics and advances in techniques like optical tweezers. So optical tweezer as such will be dealt in detail by Dr. Delphin in the next session. So I'll just give you a rough overview of how these studies are being done. So this picture shows this from current biology. So it's like this optical trap. You have the bead trapped in your optical trap, and you have the microtubule which is fixed on your cover slip, and you have a kinesin molecule fixed onto this bead. Then when you trap, so using this optical trap, you try to make the kinesin interact with microtubules and find out how much force is required for the kinesin molecule to detach from microtubule, or what is the distance that what is the step size, I mean with the one hand-in-hand mechanism of kinesin, what is the distance traveled by kinesin. So this is a single optical trap study of kinesin molecule here, where the kinesin molecule is trapped using a bead. And this in this experiment, it's a double optical trap where you have the actin filament actually fixed to the beads, and you have the myosin fixed onto a bead, and it's fixed to a cover slip. And here you find out what is the kind of interaction between myosin and actin filament. Okay. And here in this RNA polymerase characterization study, you have the bead which is, and the DNA strand is attached to this bead, and you have the RNA polymerase here, and you study what is the displacement of this bead and what is the force exerted by the RNA polymerase motor protein. Okay, so these are the curves or the experimental data that you get from optical tweezer studies, and from this you can find out what is the step size. What is the step size, and yeah, I'm not sure, like, yeah, and you also have a force here. Yeah, this curve also shows you what is the force. Yeah, so this is how optical tweezer experiments help in single molecule mechanics, especially in motor proteins. So apart from that, I think you also have AFM, right? You have, in AFM you have a bead, the cantilever, you have a bead, and you have a single molecule of myosin or kinesin attached to the bead, and you also have these filaments on your cover slip, and you try to find out the displacement, and also you try to find out the force of adhesion and all that using AFM. Okay? Yeah. So some of the questions that are being investigated in motor proteins is like, does a step involve a conformational change or power stroke in the motor protein? So initially, when it started, early days of motor protein, it was all hypothesis, especially with myosin. Myosin could be undergoing this, undergoing that. So we have X-ray crystallographic structures of different conformation. So you don't know actually what is happening. So you only have static pictures of this myosin, and you come out with hypothesis or theoretical concepts of what could be happening. But now with increased imaging options and other micromechanical techniques, now we could actually see in dynamics what is actually happening with these motor proteins. And or it's just a step, just a monomer to monomer transition along the filament, or one more point is like it could be a thermal motion also, because you know in cell is a very dynamic environment. So how could you say it's an active mechanical movement? It could be a just thermal Brownian motion, right? So that is also possible. So studies have shown that it's not just a thermal motion, or it's not just a thermal ratchet mechanism. There's actually a mechanical movement happening here. So, and it's the chemomechanical coupling type. The chemomechanical coupling is the energy for this mechanical movement comes from your chemical. So that basically the chemical energy is converted into a mechanical movement here through ATP hydrolysis. So the other question is like, is this chemomechanical coupling tight? Tight in the sense is like, what is the amount of ATP required for these power strokes or for this movement? Is it like one-to-one coupling? It's like one ATP molecule for every step that kinesin takes, or it is like one ATP molecule manages to do a few steps. So these are the kind of questions that people are trying to answer using this micromechanical techniques. So, and I think in terms of health and disease, so we have some mutated proteins which actually show a change in this movement. So when it comes to disease, you could find how the mutation affects the step size or the force or any or even the functionality, how it is affected. So these are also the kind of studies that are going on in motor proteins. Okay. Yeah, so I finished with this. So it's just a basic introduction to motor proteins. So I could do one session in just a flagellar protein of E. coli, how it helps in chemotaxis and quantum sensing. But here, since we have too many things to talk, we have just I've just concentrated on myosin and kinesin. So it'll be very, I would suggest you to go and look at dynin also, because it is also a very interesting motor protein and a lot of new things are coming out about dynin, how it changes. Actually, dynin has varied movements, like it doesn't exhibit one pattern like kinesin or myosin, it actually exhibits to different types of pattern according to the cargo it's carrying. So all these things you could just go back and probably I could share a few review articles and videos with you. Yeah. So here I have not talked about the properties of the filaments as such, because that's entirely another topic. The properties of the actin filament, the properties of the microtubule filament, because it's a polymer. You can imagine actin and microtubule to be like a polymer, like a rubber band. It's like a polymer, and they also have properties like elasticity. How is it very stiff? How stiff it is? What is the polymerization kinetics? How fast it is polymerizing? How fast it is depolymerizing? And all this is like, so filaments also you have other mechanical characteristics attached to these filaments. Okay, and intermediate filaments is more complex because intermediate filaments are not made by just one protein like actin and microtubulin. It's made up of at least more than 12 types of proteins. Yeah. So any questions? Yeah.
What is the time taken by the myosin for the one single movement?
It's few nanoseconds. I don't remember exactly the number, but it's in terms of nanoseconds. Yeah.
Does that explains that about getting cramps during a sudden heavy exercise?
Cramps during sudden heavy. It's a skeletal muscle because I am a smooth muscle person. So the skeletal muscle.
I think it's
because myosin, though it is like common between smooth muscle and skeletal, the structure of the contractile apparatus is very different from smooth muscle and a skeletal muscle.
But it kind of is. Yeah. It's in part because every time you do one of these cycles, you're using up ATP. If you use up all the ATP, and it's going to get stuck, right? So when you have cramps, it's basically these kinds of mechanisms. You've depleted the source, and so it's stuck, attached. Basically. Yeah. Because there's no ATP to then release it.
Yeah.
And then what about muscle tear?
Muscle
tear.
Muscle tear, you mean
they tell like muscle tear is
yeah. So tearing a muscle is not so much at the molecular level. It's because you've generated enough force, typically, that you're going to actually tear apart muscle fibers.
Tissue level?
It's a little bit tissue level. It's that's at the actin that like those structures break. So it's not this. It's the actin. So, but it's a microscopic. Like it all happens. You can have one of those tear and it's fine, but if like a whole set tear at one.
Is it also with the ACM, right?
Yeah, the ACM. All the proteins inside the cell, all the.
I think the first level being the ACM and
well, the skeletal muscle is all continuous.
Yeah, continuous things.
In what way the calcium ions are important for this process of contraction and relaxation?
Yeah. Yeah, it's a good question. So the myosin head actually changing the ATPase, the enzyme, and there's another enzyme called myosin light chain kinase which actually phosphorylates the head. So here the conformational change happening, the head from turning like this, it needs a phosphorylation step. That phosphorylation actually happens through the enzyme called myosin light chain kinase, and this myosin light chain kinase is activated by calcium through calmodulin. So 4 calcium ions are required to activate this myosin light chain kinase. So calcium will bind to calmodulin as another very significant important intracellular protein. So this calcium calmodulin complex actually activates this enzyme, and this enzyme will phosphorylate the myosin heads, and this phosphorylation along with the ADP-ATP cycle will cause a conformational change in your myosin head, and this leads to contraction. Yes.
Other than calcium, any neurons can do that process well?
No, the calcium is the calmodulin binds only to calcium. But the calcium's current by itself is not only dependent on calcium. You have this everything sodium, potassium channels. So everything together works on the intracellular calcium concentration. Yeah. You must have read about the G protein coupled receptors, right? And you have calcium getting released from sarcoplasmic reticulum, and especially in skeletal cell, I think the sarcoplasmic reticulum is a huge storage for calcium. Yeah. So maybe we can just proceed to the next session. Thank you.
getting set up. As I mentioned, for reading tonight, we have 2 papers. One is AFM-based and one is optical tweezer-based of breast cancer cells, looking at breast cancer and breast cancer cell mechanics. The optical tweezer, no, that is my Is it computer science?
So I was going to talk a little bit about the basic principles of optical tweezers and laser traps. Oh, great. It's my So, a little bit about lasers. So, what are some, do people know what's a characteristic of a laser that is different than a regular light bulb light source? It's really different. How is this different? How's this light different than if I just had a red LED? They have a very specific wavelength, right? So this wavelength is not. If you look at a red LED, or this is a red LED, right? The spectrum of the red LED covers a large wavelength range. If you look at, so it's like looks like this, right? If I look at a laser, like one of these, it's going to be a pretty, like almost a sharp spike just at that wavelength. What's another characteristics of lasers that's different than just regular light? I'll give you a hint. I'm going to go way back here. Okay. What happens if I point the laser to the screen from here? Right? It's still a point. It's a little bit bigger point, but it's still a point. So that is because a laser is a very convergent, it's a very set beam. It doesn't diverge. Right? If I take a red LED and I shine it from the back of the room, first of all, you probably won't see it because the light disperses, right? So lasers. Oh, and also, I don't know if people know, lasers is actually an acronym that stands for Light Amplification by Stimulated Emission of Radiation. So, but it has a well-defined wavelength, and it has a very low divergence of a beam. And so a standard red helium neon laser, I took that and I pointed it straight up at the moon. On the moon, it would make a spot about 1 mile long. If I took a red LED and I walked probably to the end of the building, you wouldn't see it. It would already be that. So just a couple things on lasers. They're divided by different classes. Class 1 lasers are safe under all conditions. You really don't usually see Class 1 lasers. You've all seen Class 2 lasers. This is a Class 2 laser. A Class 2 laser is safe because I'm not going to do this, but if I shined it all over your faces, if it shined on your face, you would blink before it would do damage. Now, if you're a horrible person and you're holding somebody's eye open and you shine it in their eye, that will do damage. So that's why this is a Class 2 laser. And then they go up. So Class 3 will do eye damage. So if I scan a Class 3 laser over your eyes can't blink fast enough and you'll have damage on your eyes. And then a Class 4 laser will burn skin. So a couple things on that. For lasers, safety. It's not just the power that matters, the wavelength also matters. So what you can do with a laser depends a lot on the wavelength. We talked yesterday about how optical microscopy it's good for looking at your samples, but it doesn't have, nanometer resolution. The typical higher resolution optical microscopes you look at is confocal. So I don't know if any of you have used a confocal microscope. Anyone have used a
confocal microscope? Has anyone used a fluorescence microscope? Yeah? So we've all used regular light microscope, yeah? Okay, good. So a fluorescence microscope, right, is you're looking at specific fluorescent particles. A confocal microscope is the thing that gets you the pretty pictures in your textbook. And it does that using a laser. So when you do confocal imaging, the laser scans across your sample, and that's why you get better resolution. So just so you know, if you have a regular microscope, these are kind of the parameters for the best resolution you can do. With a confocal microscope, you divide and get a little bit better resolution because the laser beam only has, there's like a point of focus of the light, so the light that's coming back is only from that point of focus. So when you look at confocal microscopy, if you look at regular microscopy, this is not maybe what you look like. If you look at a confocal microscope, you're only seeing the image at the focal plane, and that's why it has better resolution. I didn't want to bemoan light techniques because there are newer optical techniques that have close to nanometer resolution. They aren't so much commercially available yet. There's a lot of research in those. They're typically called super resolution optical microscopy. There's a whole bunch of different ways of doing it. Mostly it involves kind of tricks of the system to get better resolution. And so this particular one has a resolution of, I think, you can see here, it's 10 nanometers. And it's not that the light itself has that resolution. What they do is they process the image, and because they know where the light is coming from. They know it's coming from a photochemical reaction, so they can take the data, process it, and they know that for every point, it's actually coming from a 10 nanometer spot. So it's a processing step. So that's just because I felt like maybe yesterday I was being mean to optical microscopy. So there's some really cool stuff with optical microscopy, and especially if you're going to look for articles on some nanomechanics and stuff, they might be using these newer optical techniques. But optical tweezers use the fact that you can actually generate a force using light, so using photons. And you all know that this is true because you've seen pictures of comets, and comets aren't just a point moving, they have a tail, right? And they're moving in space, and as they go around the sun, the tail is always pointing away from the sun because the tail is made up of particles, and those particles are being pushed away from the sun by the sunlight. So that's in principle is how we use optical traps or laser tweezers. So you take your laser and you focus it to a small point. You use objectives like in the microscope to focus the laser. And what that'll give you is it will trap small particles in the focal point of the laser. This happens because of, I don't have too much time to go into it, but basically, so if you have a particle that's not in the, but is near the focal point, but not in the focal point, it will get sucked into the focal point due to optical forces. You can think of it a little bit like if you want, there's a couple ways of doing it. The easiest way, I think, is if you have photons, right, light, they are actually hitting something, so you can have an energy transfer, and that actually gives you a force. This is actually what they look like. So you have, it's kind of like an optical microscopy setup. I have the laser coming down, I have my sample here, and then I image on the backside, and then I can move things around. So if I can have a particle stuck in the focal range of my laser, I can then move my laser around and the particle will follow. So in the slides, I have more details on how those forces are generated, but didn't want to overwhelm anyone. So if you're interested, you can look in the details. So for the kinesin molecule, these are how the experiments were working. They had little beads, like glass beads, coated with molecules that would attach to kinesin, and then the kinesin would attach to the microtubule. And then you take the optical trap, you take your laser, and you put the bead inside the laser, and it is stuck. And then using that, you can measure how much force the kinesin is able to generate, because you can keep pulling until the kinesin can't go anymore, right? The other thing is, as you saw from the data, you can measure the steps of kinesin and get a sense of how big each step happens, because every time it moves, the bead is going to come out of the focal region of the laser, and you're going to have to move the laser to get it back in. So an interesting thing with kinesin, it's probably one of the most well-studied motor proteins. If you go back several years, there was a lot of debate in the literature about how kinesin works. The original hypothesis was that it's going to go along the microtubule like this, because when you observe them in a macroscopic sense, they're always going the same direction as the microtubule in one direction. And people were thinking, if the one foot has to somehow step onto the other side, how is that nothing preventing it from going back the other way? If you look at that, if you look at the data, if I'm doing hand-over-hand motions, right, every step I take is always the same length. If I'm doing like some of the dynamis this way, I get like big step, small step, big step, small step, right? So that's what they were interested in looking at in these first experiments, was kind of what are the step sizes to figure out how the heck this molecule works. And there was a lot of debate even after the first experiments came out, because, as was mentioned, these steps happen very quickly. And so some of the initial experiments, they were recording 8 nanometer step and 16 nanometer steps in the same experiments. So then their theory was, great, it means that we're doing this, twice this length, one. So what actually turned out is an instrumentation problem. As an electrical engineer, this is a principle that's very dear to my heart. If you have some kind of process and you're recording the process, you want to make sure that you're sampling your data fast enough. So if you don't sample the data fast enough, what's going to happen is sometimes I'm going to record one step, and then sometimes between the times the thing is taking a sample, I'm taking 2 steps. And so what was happening in the older instruments is the data acquisition wasn't happening fast enough, so that sometimes they'd record 1 step, but sometimes the molecule would have moved 2 steps before the instrument recorded. So this principle is called the Nyquist rate. So if you're sampling data, you want to make sure you sample fast enough to be able to get the right kind of data. So, and I think the data you had, the plot actually, most of the steps were 8 nanometer, and then one at the top you saw was about twice the length. So this is how they do the polymerase. So same thing, you put a bead inside the laser trap with a piece of DNA, and then you have your motor on a bead that's stuck, and then you kind of string it along, and you can measure how fast, how much force is generated, and how fast it can translate. One of the things that I think is cool is, besides measuring forces, you can use optical traps to manipulate and move things around. In my department, they use it to actually individually place cells on different areas. So here's my a schematic animation of how that works. And so you can use the laser trap to grab a cell exactly positioned to where you want, and then grab another cell positioned to where you want. And then you can make lovely patterns and look at things like neurons interacting with glial cells. You can also do fun things like play Tetris. This is just a GIF out of the, I have the link on the things if you ever want to see the whole thing, but this is using optical tweezers with glass beads to play Tetris. And yeah, so that just shows you kind of the power and how good and accurate accurate you can be with it. So a couple things on the limits of optical trapping and laser tweezers. So why would you do optical trapping and laser tweezers versus doing AFM versus doing something else? Optical traps are, or optical tweezers are very high resolution. However, they can only generate small forces. So an optical trap can generate at most about a nanonewton, maybe a little bit more, of force. So it works very well for these molecular motors that are using things at piconewton levels. The AFM, as we talked about this morning, has a kind of a resolution limit of about 5 piconewtons. So it's a nice, between the AFM and the optical trap, they kind of overlap in one regime, but the optical trap can measure much smaller forces. They just can't go as high of a force. The other thing, there's a limit to what you can trap in a laser. Typically, you can trap very small things, sub-micron kind of nanoparticles, up to maybe about 100 microns. So like a mammalian cell you can trap, but things bigger than that won't work. And the optical properties of the thing you're trying to trap matters. So it works well with glass beads, cells. Cells are a little bit transparent, so they work well. But if you're using like a gold particle, you can do a nanoparticle, but can't do a much larger particle. So you can change some parameters of your trap to particularly optimize to measure different things. The things you need to take into account when you look at optical traps and laser tweezers are the laser, what kind of laser are you using, so what the wavelength is, and kind of how tightly focused. So if you look at, I'm just going to point. If you look at the laser here, if the laser comes, coming this way, I collimate and I then focus it, I can make it very tightly focused, or I can make the focal beam like, right? And that will change how much force I'm able to generate in that focal region. If you're using laser tweezers and optical trapping, typically it looks kind of like this. It's very tightly focused. So you get the bead is going to be really stuck in the middle, but if you have a bead that's up here, it's not going to have enough force to get pulled into the center. So optical traps in this configuration are nice if you have a particle, I've trapped it, and then I'm trying to move it around. Or if you're doing the experiment with the kinesin, you have a particle, it's trapped, and then I want to see kind of small scale forces that occur right there. If I have something like a cell, and I'm trying to grab the cell, move it over, and I need a little bit more force generated, you're going to make a kind of a less tightly focused beam, and that will pull the cell a little bit harder, but you won't have quite the control. And so, yeah, so those are typically the parameters you can change. So how do I calculate force from these experiments? Right, so AFM, it was easy kind of to understand. I have a cantilever, it deflects. If I know the spring constant, I get a force. Now, with laser tweezers and optical trap, there's theory about what the force is generated, but you have to know about your laser, what your laser is, which you should know because you have an experimental setup, so you should know what the laser properties are. But you also need to know about the optical properties of the thing you're trying to trap in order to accurately calculate that force. And most of the time you don't, right? If I'm trapping a cell and I'm doing something with it, I don't exactly know the optical properties. So the way that people typically calculate forces in an optical trap is they do a calibration experiment, and they define a trap stiffness experimentally, kind of using Hooke's law. So they get a particle. This assumes a couple things, just so you have it. It assumes that you have a Gaussian profile or laser beam, and most of the time you do, but that's something you want to measure. So the way the experiments usually do is I have, let's say, one of these glass beads. I make it in the trap, and then I make the fluid start moving at some velocity, and then I measure how much the particle has moved away from the center of the trap. So with this, you should be able to calculate the trap stiffness because I know the force on the particle from the fluid. Because it's a sphere, right, so it has a radius. I know the viscosity of the liquid I'm flowing. I know the velocity of the liquid I'm flowing because I'm controlling that. And so that gives me the force from the viscous drag on my particle. And then I know how far from the center the particle has moved. And so now I just say, okay, if I pretend that the laser trap is a linear Hookean kind of mechanics, I can set this force equal to, the wrong way, to this. And that will give me my spring constant. Does that make sense? So it's a pretty straightforward measurement. You just need to do it before you do your experiment so you know what that stiffness is. The other thing is you need to remember if you're actually running an experiment, you need to do this every time you change the laser properties. So if you adjust the optics, you're going to have to redo this experiment to get the new stiffness of your laser trap. So once you have that, then you know that, okay, I know the force because I can measure how far off center my particle is, and I know how much force that is generating. So a question I get asked a lot is, this is great. This is like Star Trek. I have my beam that tractor beams, and I'm grabbing things and moving things around. Why don't we have tractor beams? So if we go back to, does anyone remember how much force is generated by a relatively large apple on my hand because of gravity? 1 Newton. The stiffest that you can typically make your laser trap is about 50 piconewtons per micron. And in general, the most force you can generate with a laser trap is 1 nanonewton. So to make a laser trap that would prevent, say, an apple from falling, I would need something like 10 to the 9 lasers pointing at the apple to get it to not fall. Now, the problem with that is that's not even correct. Because does anyone know what would happen if I put 10 to the 9 lasers on this apple? Yes, there is the heat. It will heat, right? So with small micro nanoparticles, we don't have to think about a lot of heat generation. With larger things, when you're summing all that up, you get heat. It's not as simple anymore. So that's why we can't actually move macroscopic objects with these optical properties. Because in order to get enough of a power, big enough of a laser to do anything with, you're generating so much heat that that's not doing anything else. This is, I borrowed from my colleague who has a really cool laser patterning system to show you kind of the things you can do with optical traps. So this is his system. The laser comes in, it goes through here, and then you can put a chamber with cells, and then you can use a old PlayStation video game controller to grab your cells, put them around, and put them wherever you want. And so this is just to show what it looks like when you have a cell in your optical trap. So you can see I have my cell, it's stuck in the optical trap, and I can move it around however I want. So this is their little system. They inject the cells here, and then they can pattern cells into all sorts of things. I know there were some neuro people, I don't know where you all are. So this is, they're doing studies looking at how neurons guide towards each other using this kind of technique. So this is kind of a schematic of how that works. So as I mentioned, in these kinds of scenarios, you don't want a really tightly focused beam. You want kind of a more slowly focused beam. So as a cell gets close to the wider part of the beam, it does get sucked into the beam and eventually pushed along the beam direction. Go, little particle. No, okay. So they're actually using this for cell sorting to determine cancer and non-cancerous cells without having to stain anything. So it is looking at the intrinsic, nano, mechanical, and optical properties of the cell. Typically for cell sorting with cancer, you get a biopsy from somebody, you dissociate the cells, and then you're going to have an antibody that specifically targets cancer to somehow fluorescently tag the cells that are cancerous, so that then when you pass them through a flow cytometer, anything that looks fluorescent is a cancer cell, and I put it somewhere else, right? So there's a couple problems with this technique, although it's a standard technique. The biggest problem is you have to have some kind of antibody that targets your cancer cells, so we need something. The other one is when I fluorescently tag my cell, I modify it. So it's really hard to do studies on patient cells because to sort them out, I have to bind them to different things, and then it's really hard to unbind them to those and then go study them. So this is a technique that basically they're going to have cancer cells go through and not cancer cells. And what they found was that two different types of cells, and I forget what they are, but one of them is a type of cancer cells. If you put them in the laser beam, they will have different interactions with the laser beam, and so the same amount of force will, they'll go faster, so they'll generate different forces in the laser. And so if you look at the normal cell, which is the TC cell, goes really fast in the laser, and the kind of genetically modified cancer cell is really slow. And so you can use this technique to sort cells based on something that isn't attached to them. And that's like their little trick. This is, I do cardiac cells, so this is using laser patterning to put a cardiac cell next to other cardiac cells. So if you're trying to make nice patterns of cells all together. I also wanted to show this because we talked a lot about stiffness of individual cells. So this is an adult cardiomyocyte, and you can see it's not round, right? It's like a log. It's full of actin, myosin things. It's like packed. And then look, then they start contracting. So we talked about contracting mechanisms. Once they're all together, they connect and they'll start contracting. So this is, again, just to show kind of the kinds of things you can do with optical tweezers. In order to do this, you might think, oh, I need 5 laser beams, because you need each particle or each cell to be connected with one laser beam to move it around. But what they actually do is they really quickly, they have one laser beam that they kind of flash between the different positions. So you can kind of do these things with one laser instead of having 2 separate laser systems to do them. So yeah, here's them taking those multi-micro beams to pattern things very accurately. I think I managed to stay on time. So yeah, and here they're actually building cellular structures that way. Yeah, so that's kind of an overview of optical tweezers. As I said, the paper, one of the 2 papers uses optical tweezer techniques. You'll see in that paper, they don't directly use the laser to pull on the cell. They attach particles to the cell and then pull on the particles. And that's a very typical thing to do with optical tweezers. If you read the review article from last night, there's a similar technique with magnetics. So you can take a magnetic particle, put it on your cell, and then use a magnetic field to move that particle around. So optical tweezers and magnetic tweezers use kind of similar principles for the experimental setup. You can generate more force with a magnetic setup than you can with an optical setup. However, you don't have as much control because it's very hard to move a magnetic field up and down. Magnetic traps and magnetic tweezers, what they typically do is called magnetic cytometry. They put a particle on the cell and then they rotate the magnetic field. So you rotate the particle on top and you can see how the properties change the rotation. But with optical traps, you could take that a particle and then use the laser to kind of yank on the particle. Are there questions? Does that kind of make sense? Are we feeling good? So tonight we have 2 papers to read, and then also pick a topic for your group thing. Look up papers, try to think to do that so that tomorrow we can help. If somebody's stuck or something, we can all make sure everyone has a good topic to do presentations on. Are there other questions?